introduce Maxime, who will talk on behalf of the DBCS collaboration about Eclipse Duos through DP virtual constant scattering.
Okay, so my talk will be about the 6GeV era of JLab and more specifically about the DBCS experiment that ran at 6GeV in the relay. So I think that you know that we are all here to study QCD in the nucleon. So you all know that at a large energy scale we can apply perturbative QCD because the Compline constant is small enough. But when we arrive at the energy scale of the nucleon, you have this rise and you cannot apply perturbative methods anymore. So to investigate the structure of the nucleon, you can rely on non-perturbative approaches such as Dyson-Schwinger equation or lattice QCD, but you still need to check the computation with experiment. So we would like to know how partons organize themselves in the nucleon. So the holy grail would be to access what we call the Wigner distribution that encodes the correlation between the longitudinal momentum of partons, their transverse momentum, and their transverse position in the nucleon. But so far, it is not experimentally measurable right now. So if you integrate your Wigner distribution of the transverse position, you get the TMD that encodes the correlation between longitudinal momentum and transverse momentum, and these TMDs are accessible through semi-inclusive deep inelastic scattering. If you take the Wigner distribution and integrate it over the transverse momentum, you get the generalized parton distribution that correlate longitudinal momentum and transverse position. And you can see that parton distribution function of form factors can be recovered from the DPDs. And my talk will be mainly about the DPDs and DBCS. So how to access the DPDs? DPDs are accessible through the deep exclusive processes. So for example, here you have this process. You have the electron that will interact with the proton by changing the R virtual photon. And then the proton will emit a particle. So it can be a photon, in the case of DBCS, or a meson, such like pi0 or rho. And the link between these diagrams and the DPDs is guaranteed by what we call the factorization. So take this diagram, which is the DBCS. You can write it as an infinite sum of different diagrams, and this infinite sum can be seen as a perturbative expansion of your amplitude as a function of 1 over q, which is the virtuality of your photon, incoming photon. Each of these diagrams, you can cut it into two parts. The upper part, which is a high energy part, where you can apply perturbative QCD. So you can make an expansion in power of alpha s. And the lower part, where here you cannot apply perturbative QCD, but this part will be described by your GPD. So this diagram is the amplitude associated to this diagram is a convolution of the upper part where you can apply perturbative QCD with the GPD. So I would like also to introduce briefly the twist. So for example, we have different twists, and when you have a diagram with twisted end, it will be, well, it will have a contribution higher. Well, sorry, I will turn it the other way. So if you have a diagram of twist n plus 1, this contribution will be suppressed by a factor 1 over q compared to the twisted end diagram. So this is the DBCS end-back diagram at leading twist leading order. So you have your virtual photon that will be absorbed by a quark inside the nucleon, and then this quark will remit a hard photon and goes back inside the nucleon. So you have q squared, which is the virtuality of your photon, with the Birken variable, x, which is the average longitudinal momentum carried by the quark here, psi, which is an average, which is a longitudinal momentum transfer, and t, which is the square momentum transfer to the nucleon. So again, the GPDs parameterize the DBCS amplitude, but not directly, but only through a complex integral, which is the convolution of your DPD with the hard kernel. So this number is a complex number, okay? We call it a Compton form factor, and it has a real part and imaginary part. I want to mention that GPDs are real functions. So experimentally, what we measure? We will measure the cross-section associated to E, P gives E, P gamma. So of course, you will have the DVCS that will contribute, but it is not the only process. You have also the beta Hitler, for which the real photon is not emitted by the proton, but by the outgoing or incoming lepton. Therefore, the cross-section that you measure is proportional to the square to the sum of the squared amplitude of beta Hitler and DVCS and an interference term. Okay? So we will measure a cross-section which is differential in Q squared, Birkenex, and T, and phi. This phi is an angle between the leptonic plane, defined by your virtual photon and your scattered lepton, and the hadronic plane, here defined by your virtual photon and your real proton. So you can make an harmonic expansion of this different contribution as a function of phi. What is interesting is that we know the beta Hitler because if I go back to the previous slide, it is a QED process, and to parameterize here the hadron structure, we just need the form factor that are accessible for elastic scattering. And what we don't know are the square DVCS amplitude and interference term. And the information about the compound form factors are hidden in this harmonic coefficient. So what is interesting in the case of photon electroproduction, so you have your DVCS harmonic coefficient that will give you information about modulus of compound form factors. But the main advantage of DVCS, well, photon electroproduction, is the interference term, where the harmonic coefficient gives you information about either the real part or imaginary part of compound form factor. So you can access the full information about this compound form factor using DVCS. So the idea to extract information about the GPDs and the compound form factors is to study this phi dependence and to extract these harmonics. And if you make some assumption, you can try to get there. So I will introduce a feat that usually is taken as a reference, performed by Kumericki and Müller. So basically, they extract the imaginary part of compound factor through beam helicity dependent cross-section or target spin cross-section. And then the real part are built using dispersion relation from the imaginary part. And so far, this fit was able to reproduce all the DVCS observables collected in other facilities or at class. So I will talk about two experiments. So there were two experiments running in OA at 6 GeV, one in 2004 and another one in 2010. So basically, the experimental setup is the same between the two experiments. So of course, since the initial state is electron-proton, we use the electron beam from Jefferson lab, which is sent in the relay, and in the relay we send it on the liquid hydrogen target. The beam was at that time about 80% longitudinally polarized, and well, this is the maximal beam current that we could have at that time, but we run only about, well, at a beam current less than 4 microampere, and the maximum beam energy was 6 GeV. So now the final state is made of a scattered electron, a record proton, a photon. So the scattered electron was detected. So here you have the beam, the target, well, the scattering chamber, and here we had a high resolution spectrometer to detect the scattered electron. So with the scattered electron, we can derive Birkenex and Q squared. And then we detected the photon using electromagnetic calorimeter made of lead fluoride, which was here. And so with the 4 momenta of scattered electron and photon, we can derive the two remaining kinetical variables, which are T and phi. So then, what about P? So P was not detected, but you can ensure exclusivity by looking at the missing mass. So here in black, you have the distribution of the missing mass associated to EP gives E gamma X, because you don't detect the record proton, and you can see that you have a peak at the square missing mass of the proton. So the game is the following. You cut on the missing mass, and you can write the number of events that you have below this cut as a sum of 4 contributions. The first contribution is the one you want to evaluate, which is the number of exclusive events. And you have some contamination coming from accidental events for which you have detected one photon and an electron, but they are not related to each other. And contamination coming from pi 0, so pi 0 decaying to 2 photons, and you may detect only one of them, and in that case you can take it as a DVCS photon. And finally, the last contamination is a semi-inclusive background. So you have to get low enough on your missing mass to ensure that this contamination is, well, it's very small, I would say 0. And then we have methods to subtract here the accidental background. So once you make this subtraction, you can see here the corrected distribution without the contamination, which are the blue dots. And we have our Monte Carlo simulation, and you can see that apparently this contamination is compatible with 0 if you cut at 0.95 dB squared. Here you can see, for example, also the distribution of events. So here you have accidental events, which are really close to 0 and 360 degrees because you are close to the beam in the calorimeter. And pi 0 are mostly contaminating the sample at 180 degrees because of the acceptance of the experimental setup. So these are the results for the 2004 experiment. So we have here a beam at Q square about 1.9 dB square. Birkenhead's central value is about 0.36 for 5 different values of T. And we have in red the beta-Heitler contribution, and in blue it is this fit taken as reference, and you can see that we had always a deviation at about 180 degrees. So about at the same time we released this data, Brown computed some kinematical power correction to the DVCS. And, well, I would say that it was conveniently filling the gap between the reference fit and our data point. And it was the main conclusion for all the beams we have extracted. So after having released this data, we were convinced that we need to include this kinematical power correction because they are sizable. So here it is a table summarizing the kinematical setting for 2004, and as I told you, we ran another experiment in 2010. So about the same Q square, so a bit lower here maybe because we are only at 1.5, 1.75, 0.75 and 2 dB square, and Birkenhead's about 0.36, well, still 0.36. But the difference is that we measure this kinematical point with 2 beam energies because we wanted to add a constraint on the DVCA square and interference contribution because they are beam energy dependent. Okay, so we wanted to add another constraint than only the phi dependence. You can also see that this kinematic in 2010 is really close from this one. So, for example, we had made a comparison between the two measurements we performed. So it's not the final result, but it was done doing the analysis. So it's about the same meaning. The points here are 2010 data, but when we extracted our cross-section for 2004 experiment, we had also some model. And you can see that the line, the blue dashed line, is on top of our 2010 experiment. So it is cool that we can check that the physics is independent of time. And also, at the same time, so after having published our 2004 results, Kubrick Miller did another fit, still at leading twist and leading order, and you can see that they were now able to reproduce our data. So, I need now to explain a bit what are this kinematical power correction because it is a big deal when we want to play with the beam energy. So, Belitsky, Muller-G did LCT well. They parameterize the DVCS amplitude with 3 kinds of content factors, which depend on the LCT of the photon. You have the first kind of content factors, which are I would say helicity conserved content form factor. So for which you have the helicity of your virtual photon, which is the same as the helicity of your outgoing photon. And this helicity conserved CFF, or the regular twisted 2 CFF, we are always talking about. Then you have contribution from the longitudinal polarization of your virtual photon, which is twisted free, so it is supposed to be suppressed by 1/q compared to this helicity conserved CFF. And then you have transverse to transverse helicity flip CFF, so your incoming virtual photon has an opposite helicities compared to your outgoing photon. And if you stay at leading order, these contributions are twisted 4. But what is interesting is that at next to leading order, so when you allow gluons to play, these CFF are in fact twisted 2, because they involve gluon transversity GPs. So Brown, to compute this kinematical power correction, did the same thing, but it changed the reference frame, because here the reference frame was a lab frame, but here it shows a frame where you have both photons in the same plane. And you will say, you can ask me, what is the difference? Well, the difference is there. So for example, here I have written the Muller content form factor, I would say, which is the usual convolution of your hard kernel with the DPs. And here it is a Brown content form factor, and you can see that we have the same first part, but then you have some correction which are twisted 4 correction. So this is the first difference, and then we have another difference which is purely kinematical because we change the reference frame. So we have to make some kind of a transformation to go from the Muller reference frame to the Brown reference frame. And the bulk of the kinematical power correction are in fact in these relations. So they are pretty straightforward if you want to take them into account in the analysis. So we have this chi0 and chi, which are proportional to t prime, so which is minimal minimal momentum transfer to the nucleon minus the actual momentum transfer to the nucleon over q, and chi, which is about what, which is same as twisted 4 correction. So let's now take a look at what are the consequences on the parameterization for DVCS. So here I will only explain the DVCS square harmonics. So if you only look at DVCS square, you have a constant term, a term along cos phi and psi phi, and then a term along cos 2 phi. So in the case you choose to play with the Muller content form factors and you make the leading twist in order assumption, you will drop all these calligraphic minus plus and 0 plus content form factors, and you will only keep this term here. So this means that your DVCS square amplitude will be phi independent because you put to 0 all the harmonics on cos phi and cos 2 phi, and it has a single beam energy dependence. So it is good. But if you want to take into account this kinematical power correction, they depend on the helicity of the virtual photon, and you can see here that well, sorry, I was a bit fast. If you make the leading twist in the order assumption, we have to neglect now this kind of content form factors. But using the math that I have previously introduced, you no longer neglect the calligraphic minus plus and the calligraphic 0 plus, which means that your DVCS square amplitude is no longer phi independent because you will have to keep the cos phi and the cos 2 phi harmonic, but also you have multiple beam energy which are dependence which are hidden in this y coefficient. And well, also it is something that sometimes we forgot, but by changing the beam energy, we not only change the contribution so between DVCS square and interference, but we change also the polarization of the virtual photon. So the size of the correction are significant, as I mentioned. So for example, it is chi0 here, which is evaluated at Birken is equal 0.46 for different value of t and a different value of q squared. And you can see that here you have, so here it is the kinematical range that we access with our experimental setup, which is pretty low t compared to sometimes class. And we can see that here we have a steep rise of chi0, and the correction is about sometimes 30%, which is significant. So if we want to separate and the DVCS square and interference, we need to take them into account, and therefore we need now to parameterize our DVCS amplitude with the Brown content form factors. So to extract these content form factors, we do a fit simultaneously on unpolarized and polarized data, because polarized data give you information about the imaginary part and polarized about the real part. Simultaneously on the two beam energies, because we take apart the two beam energy, and simultaneously on the free Q-square value, because here, well, I can neglect the Q-square evolution since we have a very low range in Q-square. So this is what we have. So here, the dashed red line is what I call the leading twist leading order fit, where I only keep the leading twist leading order content form factors. And in black, it is our here unpolarized cross-section, and here beam helicity dependent cross-section. And you can see that the leading twist leading order fit is not able to follow our data points. In gray, I will also, so it is a new fit performed by Kulinaki and Müller, and you see that now we still have this discrepancy that is appearing again at 180 degrees. So let's drop E and E tilde as content form factors, and let's introduce some higher twist contribution by taking these content form factors 0 plus, H0 plus and H0 plus. So this is the blue curve, and here you can see that we reproduce very well our data points. So here I did not display what I call the next to leading order fit when I want to introduce some, I would say, content form factor related to beyond transversity GPDs, but it gives an equally good fit with the higher twist. So from this figure, we say that we are sensitive to gluon in DVCS in our kinematics. And when you want to separate interference from DVCS square in these two scenarios, so of course they are giving you the same fit, but the DVCS square and interference contribution are different. So on the left, you have unpolarized cross-section, here on the top DVCS square, here interference contribution, and for the pink, we have the gluon transversity, I would say, GPD playing, and in the blue, I would say it is a higher twist scenario. So you can see that the DVCS square has a different shape when you do the higher twist scenario or the next to leading order scenario. Same thing for interference. And on the right, we have polarized cross-section. In blue, still the higher twist scenario, and in red, the next to leading order scenario. In the next to leading order scenario, the beam helicity dependent cross-section is a pure interference term, but it is interesting that in the higher twist scenario, we have some DVCS square contribution, which is fairly significant. And usually, right now, in our phenomenological studies, we are assuming that this term is purely an interference. So we have to be careful, because if it happens, well, if at some point we find that the higher twist scenario is the best one, we can no longer say that it's only an interference term, the DVCT dependent cross-section. So we come to my conclusion. So high statistical precision data are essential to get a 3D picture of the nucleon, and in fact, well, I think we have brought some new information compared to what has been collected so far. Kinematical power correction must be taken into account, because also I forgot to tell you that here I draw the curve at Q square equal about 4 dB square, and you can see that the correction is still significant. So you need to take it into account. Even at JLab 12 dB, I think. But what we can hope is that this higher twist and or next to leading order contribution will disappear at 12 dB square with the higher Q square. Although, well, I would be a bit sad, because from the gluons of 3 partons correlation, which are this higher twist contribution, they can teach us a lot about confinement and QCD inside. So we will have a rich program concerning DVCS at 12 dB with among the different experiments, we have 2 Rosenbluth separation in all B and all C, but also we have polarized target and also deuterium target. And also I would like to emphasize that already some data have been taken in array at 12 dB, and I cannot wait to see the first result. Thank you very much.
Time for questions.
you please show slide number 13?
Yes.
Here it is. So, your peak with DVCS signal actually embedded into huge background. And my question is, how well you know contaminating processes, and if you change with an uncertainty the contribution of contaminating processes, what effect would be on DVCS signal?
Well, here, so what we have done is to extract our cross-section at several values of missing mass square, you know. So we went up to 0.8. So here, you know, on the other side of the mean value. And on all this range, the cross-section was found to be stable up to about 0.0 GV square when it started increasing due to, we are sure about the CD's contamination that we did not take into account. So we don't know much about this contamination here, but we cut low enough on the missing mass to be sure that we are not sensitive to it. Yeah.
You just add the green. The green curve is derived, that is subtracted from the black, is derived statistically from the data. It's not an estimate. So the real contamination is given by those open blue circles.
Yes. Yeah, yes.
The blue circles is a true signal, and you can see there's a rather clear, coherent peak.
Yeah, sorry, blue circle is black minus green.
Minus green.
Yes. Black minus green.
Further questions?
Can you tell a little bit more what's in the KM15 fit?
Well, it's the same, but they took into account our 2004
It's exactly the same as the KM10.
but with the new data set released by Olay and class in 2015.
And also you made a statement at the end that you can learn something about confinement. Twist 3, is it just a qualitative statement? Or
No, it's just a qualitative statement, but I would say that if you want to understand QCD, you need to understand results. So I must say that during my PhD, when I was looking at all this leading to linear order diagram, it was a bit sad to not see gluons appearing. Because I really think that it's a personal statement, but if you want to understand QCD, you need to have an idea about what gluons look like.
Sure, but there are other ways to access gluons except with Twist 3.
Yes. Yes, I know, but it's kind of surprising that in this DVCS we are sensitive to these gluons in the valence region.
I think that's all the time we have for questions. Let's thanks Maxime one more time. Next speaker is Simon Taylor from Jefferson Lab, speaking about the first results from the spring 2016 run of PUX.
Is this high enough? So I'll be spending the next half hour or so talking about the first results from the Blue X experiment.
I think it's not high enough.
That's what I'm afraid of. How's this? Better?
Can you twist it backwards?
About this?
Yeah.
Oh, now I hear myself. Okay, so as I said, I'm going to be talking about first results from the GlueX experiment. And I'll start out with a very brief introduction about hadron spectroscopy, then talk about the photon beam in the GlueX experiment, and then I'll launch right into what we've been able to achieve so far. So it's well known that the quark model is a huge success in describing the hadron spectrum. But the interesting thing is that most of the hadron mass is not due to the quarks. So the gluons clearly play a huge role in the dynamical generation of mass. And in the theory of the strong interaction in QCD, in addition to the matter the visible matter that we're all familiar with, mesons and baryons, other configurations are also allowed. And the focus of the GluX experiment is to look at mesons that have excited glue in them. But it turns out that it's an exciting period for spectroscopy because these other configurations there have been hints of these have already been seen in the data. And for example, both LHCb and in this example I showed the results from BESS3 have seen evidence for tetraquarks. And perhaps the most exciting thing in recent years is the observation at LHCb of a pentaquark candidate going to PEJ psi. But I will be getting back to this a little bit later. But the main focus of the GluX experiment is to understand the meson spectrum. And in particular, that we would like to look for evidence for excited glue. And the way we would find a smoking gun indication that something interesting in this regard is going on is to acknowledge the fact that for regular QQ bar mesons, certain combinations of JPC are not allowed. But if you can excite the glue that holds the quark-antiquark pair together, then you have access to some of these exotic quantum numbers. And you can think of the so-called, in what we call in jargon, a hybrid meson in a kind of a quark model picture. You can think of it as a quark-antiquark pair with a valence gluon, a constituent gluon with JPC 1 plus minus. So there have been grand strides in recent years on the lattice, calculating the meson spectrum. And in the first two columns, I showed the calculated results for the non-exotic quantum numbers, where the familiar states that we're all pretty much well aware of, pions, nadas, and mesons, so show up. But I'd like to point out in the last column, there are also predictions for mesons that have exotic quantum numbers. These are the so-called hybrid mesons. And the goal of the GluX experiment is to start to map out the spectrum of these hybrids. And the first place to look is in the 1 minus plus column, which are expected to have the lowest mass. So the masses of these exotic hybrids are predicted in QCD to be on the order of 2 to 2.5 GeVs, which is very well accessible for us in the 12 GeV era. And models suggest that the decay widths of these hybrid mesons will be on the same order of magnitude as regular QQQR mesons. The models also suggest that the hybrids should decay to several channels. And the interesting thing about these channels is that these final states contain multiple pions and combinations of pions and adas. And because all of the masses are expected to overlap and sit underneath a huge background due to regular mesons, we would need to get a detailed understanding of the spectrum, we need to do a partial wave analysis. That's the ultimate goal of the GluX experiment. So we had a couple of successful runs so far. In the spring of 2016, we had a commissioning run, an engineering run, where we checked out all of the detectors, make sure everything is working, and this was successful enough that we took 7 billion events that were good enough for early physics results, and that's what I'm going to be talking about today. In the spring of 2016, we ran the first part of the so-called GluX phase 1 run, which is a low intensity run. And there we took about 50 billion events, which in our accounting accounts for about 20% of this first phase of GluX. And the data processing for the spring 2017 run is underway right now. And looking to the future, we expect to run the second part of this phase 1 in the fall of this year. So first I'll spend a few minutes talking about how we produce the beam. This is a photo production experiment. So the electrons from the rays track are directed towards a diamond radiator where a process of coherent Bremsstrahlung takes place, which has a characteristic behavior shown here as a function of a beam of photon beam energy. And then the scattered electrons are deflected by a magnet towards our Tiger spectrometer where we can measure the photon beam. And then the photon beam is directed along a vacuum pipe towards our experimental hall. And the first thing it sees is a collimator, which leads to an enhancement of what was called the coherent edge or coherent peak relative to this kind of 1/E non-coherent Bremsstrahlung background. And in the coherent peak, we expect about 40% polarization with the photon beam. And we can measure this beam polarization with a triplet polarimeter, which I show here. The idea is we could look at this triplet production, and what we see is a characteristic phi dependence, as shown here. It goes like cosine 2 phi, and this shape is calculable in quantum electrodynamics. And if we understand the polar response, we can extract the polarization of the beam. And that's what's shown here. And kudos to the Arizona group for producing a very fine device for doing this measurement. Then the photon beam heads towards the main hall and interacts with a liquid hydrogen target. And then the final state particles are detected in our GLOX spectrometer, where we have drift chambers for tracking charged particles, and we have calorimeters for detecting photons, and in the forward direction we have a wall of scintillators for time of flight measurements for particle ID. Well, here I show an example of the resolutions that we've been able to obtain so far. This is for the 2 photon invariant mass on both the forward calorimeter and the barrel calorimeter. As far as particle identification is concerned, we can use time of flight through that wall of scintillators to distinguish between the different particle types. And so here we can see clear separations between electrons, pions, kaons, and protons for positively charged particles. And if you squint, you can see even a hint of antiprotons showing up for the negatively charged particles. We can also use energy loss in the drift chambers to distinguish between protons and other types of particles. And finally, by looking at the shower energy relative to the track momentum for tracks that are matched to these showers, the E over P ratio, we can distinguish electrons from hadrons. Well, the simplest thing that we can do with the detector is to look for beam distinguishers for pseudoscalars. And we can take advantage of the relatively high polarization in the coherent peak. And we're oriented diamonds such that the polarization of the beam is parallel to the floor and perpendicular to the floor, and measure an asymmetry where conveniently annoying things like detector acceptance and efficiencies drop out. And for pseudoscalar production, for the production of pi zeros and etas, this should have a characteristic cosine 2 phi dependence. And knowing the polarization from the triplet polarimeter measurement, we can extract this beam asymmetry sigma. Well, the idea is that at 9 GeV, these pseudoscalar mesons, such as pi 0 and eta, are mostly produced in a T-channel process via the exchange of regions. And these regions can either be vector-like regions or axial vector regions. And it turns out that the beam asymmetry sigma sign and magnitude depends on the relative weight of the vector-like region exchanges and the axial vector region-like exchanges. So we identify our pseudoscalars by their decays to 2 photons, and here we see a clear peak for the pi 0, very well separated from the eta. But then for the eta, it's a little bit of background, which is quite manageable. Note that this is a log scale. from the decay of omega that goes to pi 0 gamma, where you happen to miss the detection of one of the photons. And shown here is the characteristic cosine 2-phi distribution that is expected for this reaction. So here is our result. This top plot here, this is for the pi 0, and this is for the eta. And what should be fairly clear from these plots that the sigma is very close to 1, which means that the vector exchange dominates. The other interesting thing for the pi 0 production is that previous experiments saw this dip at around a half GV over c squared, but we don't see this. Another thing I should point out here is that this is the first time this eta asymmetry has been measured at the Gluex energies of 9 GeV. And the results of these have been published. This is our first Gluex physics paper. Actually, it's the first 12 GeV era physics paper. And here is the reference. So we can extend this idea of measuring Bayes symmetries to the vectors. Here I show an example of the production of rho going to pi plus pi minus. And this is a comparison to a previous experiment from the 70s when they first measured this kind of thing, in comparison to the very, very fine bins that we can do because we have such a huge data set here. And so it's just very exciting. And so we can extend this idea to beam asymmetries for omega. Omega goes to pi plus pi minus pi 0 about 89% of the time. And it goes to pi 0 down to 8% of the time. And if you measure these beam asymmetries for these two decay channels, we expect the ratio of these asymmetries to be -2. And what's shown here is the data. And you can clearly see the signs are different and the scales are also different. And so what we actually measured was indeed very close to -2, so everything is working as expected. To understand the omega in more detail, we need to do some spin density matrix element measurements, and we have a student who's working on that. The next thing I'm going to talk about is actually kind of fortuitous, and that is the production of charmonium in the Gluex experiment. Because we have 12 GeV beam and we have a Bremsstrahlung distribution, we can have photons that go all the way up to close to the end point. And so that turns out to be very close to the threshold for the J-psi production, which is about 8 GeV. So we can cover this small range here. And this is interesting because there's a prediction by Brodsky et al. That suggests that if the J-psi is produced in a 2 gluon exchange versus a 3 gluon exchange, then the behavior of the cross-section in the threshold will be quite different. And so we can start studying J-psi gluon interactions for probing the gluon distribution of the proton for multi-quark correlations and so on. And the other reason why this is exciting is because of the observation in the LHCb of this candidate J-psi proton pentaquark. And the question we can ask is, can we see this in photo production? Because the mass that they found for the pentaquark would correspond to about 10 GeV photon. We used the entire 2016 data set to do this measurement. And the channel that we used for identifying the J-psi is the E plus E minus channel. This is a branching ratio of about 6%. We used E over P in the 4 calorimeters and the momentum from the tracking chambers to identify the electrons and positrons, and we also detected the recall proton. So we reconstructed the full final state, and because we know what the beam energy is, we reconstructed the full reaction. And because of this, we can start applying some constraints. So we applied a kinematic fit to constrain energy and momentum. And the end result of that is shown here, where in the E plus E minus invariant mass, you can clearly see a very nice peak consistent with the J-psi. sitting on top of a relatively small background due to beta height limit. So we use this distribution to estimate a cross-section, quote cross-section, because we're still working on the normalization and the understanding of the acceptance of the detector. But what I show here is our result with arbitrary units, and in comparison to the previous results from the 70s, and you can see the shapes agree reasonably well. So the plan is to combine the spring 2016 and spring 2017 data sets, and then map out this cross-section with real units this time. And then also we can provide an upper limit for the photo projection of this pentacord. Finally, I'd like to say a few words about how we're progressing towards the main program for the GlueX experiment. And as I said, the decay channels that we're interested in contain final states that have multiple pions and then pi zeros and etas and so on. So what I'm showing here is some spectra for the case where we identify recall proton with 4 photons in the final state. And if you look at pairs of photons, masses of one pair versus the masses of the second pair, you can see clear evidence for double pi zero production and also eta pi zero production. And it's a little hard to see in the center of this curve, so I made an inset. We also have evidence for production of 2 etas. For the case of the eta pi zero distribution, we see clear evidence for the scalar meson A0 980, and there's a tensor meson at the A2 1320 that shows up. And there are also possibly other features in this plot that would be interesting to ferret out. And for the 2 pi zero case, they have evidence for the F0 980 scalar meson and another tensor meson. There's also some other features here that could be interesting to study. Well, so the A naughts and the F naughts 980s are actually quite interesting because there's some debate of whether or not those should be considered to be QQ-Gord mesons or whether or not they should be considered to be molecules. If you add another photon to the final state, then we should expect to see the very well-established B11235 meson. So the B11235 goes to decays to pi zero in the omega, and the omega, some 8% of the time, decays to pi zero gamma. And so that's what's shown here. You can clearly see in the pi zero gamma mass distribution a clear omega peak that is coincidence with this peak that is consistent with B1. So this is behaving exactly like we would expect. Then for the 6 photon case, then we should see the well-established eta and eta prime mesons that came eventually to 6 photons. The eta goes to 3 pi 0 about 33% of the time. Eta prime goes to eta pi 0 goes about 20% of the time. And that's indeed what we see, that we have a very well-separated eta peak going to 3 pi 0, and a fairly well-separated eta prime peak going to eta and 2 pi 0. And in the eta 2 pi 0 invariant mass, there's another peak that is consistent with the F11285, or possibly there's another eta at 1295. And the nice thing about these distributions, especially for the eta, it's very well separated from the background, so it's suitable for a Dulles analysis. And with some work, we can also think about doing Dulles analysis for the eta prime. So finally, I'd like to highlight what's probably one of the more ambitious final states to look at. So that here we have many particles in the final state. So in addition to the recall proton, we've reconstructed 2 pi pluses, 2 pi minuses, and 4 photons. And the 4 photons that we can you look at the pairs of photons, a lot of them are consistent with double pi zero production, which means that you can start looking at reactions that have groups of pi plus pi minus pi zero and a second group of pi plus pi minus pi zero, taking advantage of the fact that the eta goes to pi plus pi minus pi zero and the omega also. And so looking at the mass distribution for one group, these 3 pi's versus the second group of these pi's, we see clear enhancements consistent with resonant production of 2 omegas, and if you squint, you can see that there's evidence for omega eta production. And I've made a slice here to make it clear that there is indeed an omega peak that's in coincidence with the eta mass. So the omega eta is interesting because this is one of the channels that we have that have been listed in my previous slides for searching for hybrid mesons. And again, as I showed earlier, that we see eta in 4 gamma. Well, we also see eta in pi plus pi minus pi zero and pi plus pi minus pi zero. So this is indeed a very exciting place to be, and we're continuing to analyze the data, looking for more and more interesting final states. So to conclude, the Gluex detector is very well suited for detecting both photons and charged tracks. We had a couple of very successful runs, and early physics has already started to come out. We've already published the pi zero eta asymmetries, and our plan is to publish the J side result by the end of the year. Finally, there's a rich spectrum of multiparticle final states that have already been seen in the data, so we're very excited to be able to get towards the search for hybrid mesons. So I didn't show any results from the spring 2017 data yet, but the calibrations for the first half of the spring 2017 data set are currently complete, and the first production launch has already been started, so we're eagerly awaiting the results of that. And to looking forward to the future, our next run is scheduled for the fall of 2017. Thank you for your attention.
The top questions?
I have a question on slide 17 about the pi zero asymmetry in comparison with the SLAC data.
Yeah.
I know the SLAC statistics are not fabulous, but I'm wondering, to say the average energy of the SLAC data is at 10 GeV. Do you have any idea how broad a range that is of the SLAC data?
I seem to recall that it's a fairly broad range, but I don't know off the top of my head.
I mean, I'm trying to understand whether there is a significant difference in terms of an energy dependence, or is it just statistics if I throw out the one point that's lowest, or extend the error bar by 2 sigma and say, okay, the data are in agreement.
I think that's a fair statement. I'd say that there's only a slight tension between our measurements.
But it's not necessarily tension at all if the energy range is significant.
Yeah.
So first of all, I think it's a great talk. With respect to Charles's point here, what's interesting, of course, is that the dominant theorists have followed that point, right? And so you're killing off at least 2 theorists with that, maybe 3. So then I had a question on slide 22. You kind of tease us all by showing where the 4450 would be. Do you have a plot which shows what it would look like?
Problem is, we don't know the reference curve.
No, I haven't seen such a plot.
Further questions? Okay, well, let's thank Simon again. Next up, we have Nadia Foreman from the University of Tennessee talking to us about short-range correlation studies at Jefferson Lab.
Okay. So I'm clearly Nadia Arrington, who was supposed to give this talk originally, but he had to cancel at the last minute. But not so last minute that he had actually made a talk. I'm going to talk, as Mark said, about short-range correlations, going tell you guys about all our achievements from the 6GeV era and where we're going in the next couple of years. So it's not going to be an exhaustive talk, except for me. Okay, so when we talk about short-range correlations, just to let some of the new folks know, like, what exactly are we talking about? So as you know, a nucleus is not a static object. It's dynamic. Those nucleons are on the move inside. So occasionally, some fraction of the time, you can get two or more nucleons that get close enough that the wave functions begin to overlap. So what that means is that their internucleon distance is smaller than the size of the nucleon itself, so smaller than a Fermi. So once they get close enough, they feel the repulsive core of the nuclear potential, and you end up with basically nucleons going back to back. In the case of a two-nucleon correlation, they have a very low center of mass momentum, but high relative momentum. So when we say we're looking for short-range correlations, experimentally we're actually looking for high momentum nucleons. And an easy picture to help keep this all in your mind is to think of it in terms of a momentum distribution of the nucleons inside the nucleus. So this black line here is basically what you would expect from a mean field picture, where I think it's a picture for carbon, where kind of the width of this momentum distribution is driven by the Fermi momentum for carbon. And the presence of these high momentum nucleons that are born in short-range correlations would basically extend this by having a high momentum tail. And in our picture, this high momentum tail would only be to these high momentum nucleons from this process. So if we're doing an experimental measurement, we're basically trying to isolate this area to study short-range correlations. So what have we learned from 6GeV era? So this is spoilers, everything I'm going to talk about. So we see a scaling of the cross-sections relative to the deuteron, nuclear cross-sections relative to the deuteron, at Bjorken x greater than 1. So this is the region that's forbidden to the free nucleon. This implies that high momentum tail is in fact the result of short-range correlations, as we think. We see NP dominance of short-range pairs. Believe it's the result of being dominated by a tensor interaction. We notice that there is no trivial nuclear dependence. It doesn't go as a function of A or as a function of density for either short-range correlations or the EMC effect. They're both plotted side by side here with just the right scaling factors that they show up on the same graph. So we learned this from high-precision light nuclei data in Hall C. And we also see that there's a suggestive correlation between the size of the EMC effect and the short-range correlation plateaus. So now I'm just going to go in a little more detail about how it is that we learned, what measurements we did and how we know these things. So Here, we're using electron scattering for these measurements, and by dialing down the q-squared to just the right range, we are probing nucleons inside the nuclei. So here's two pictures side by side, one for electron-nucleon scattering, which is probably most familiar to people, where you see the elastic scattering peak, you have your resonance region, deep inelastic scaling region. This is an old picture because we're using omega for energy loss. And it kind of looks similar once you stick a nucleus there instead, except you see slightly more structure. Your elastic scattering peak now is the quasi-elastic scattering peak. You're still scattering from a proton, but now it's a bound proton, and this peak is broader by the momentum distribution inside the nucleus. And then, in principle, you would see nuclear resonances for the other correlations. In reality, so I showed that as a function of energy loss, which is how you do the measurement, but all the data I'm going to show you is as a function of x. So you basically take this and turn it around. So the x greater than 1 parts are going to live over here. Nothing we do is going to look this pretty. These contributions are going to be fairly small, and they're going to be smeared. So in fact, the x greater than 1 is going to look kind of like this. That's the part that we're interested in for short-range correlations. So how can you do this? Well, we said we are thinking of it in terms of a momentum distribution, so why don't we try to measure momentum distribution? So that's really, really hard. This is an example of trying to extract the high momentum tail in an exclusive measurement. This is from an experiment a fairly long time ago, but it always says preliminary. So this is scattering off of helium-3, and this experiment measured the far into the high momentum tail, but the cross-section that was extracted, the points you can see this is a log plot, so it's 5 or 10 times higher than the expectation from calculation. The difficulty with doing exclusive measurements is your high momentum state can come either from the short-range correlation, an initial state, the thing you're trying to probe, or final state interactions, or meson exchange contributions. So you get this enhancement and you're not actually probing the thing that you want to be probing. So this is a difficult measurement. So this is another example kind of the same thing, where final state interactions and meson exchange currents overwhelm the tail. So why not try inclusive scattering, where we only detect the scattered electron? We then select our kinematics so that we're only probing initial nucleons whose momentum is greater than the Fermi momentum. So we're looking over here, and what that means, we're pretty sure we're looking at two-body physics because, in this region, the x greater than 1 region, it's forbidden to free nucleons. So if you find a nucleon there, it's sharing momentum with its buddies, so it's going to be a high momentum one, and it's hopefully will come from its tail. So, and the idea is we do a relative measurement. If these high momentum tails are a result of short-range correlations, then all the nuclear tails should look the same. The only difference is you can have more and more pairs as the nuclei get bigger. So if you do a relative measurement relative to the deuteron, because that's your first nucleus where you can have correlations, if this picture holds, you should see plateaus, cross-section plateaus at x greater than 1. So that's the expectation. But what we actually are measuring are cross-sections. So we go to x greater than 1. This is what the cross-sections look like. This is at a given kinematic setting. But we take a bunch of different nuclei. And you can kind of see that, and this is on a log scale. So these cross-sections are falling very fast. So this data took no time, and this data took some time. And we're going to basically look at cross-section ratios over here. And by taking ratios, we also take advantage of the fact that we're pretty sure that the final state interactions for two nuclear correlations will be confined to the correlation itself, the nucleons that were in the correlation. So by taking the ratio, that will, for the most part, cancel. So in this picture, our cross-section is basically, in this region, a sum of A2 the ratio, the A to D ratio, and then the probability, and then the cross-section for 3 nucleon correlations, 2 nucleon correlations, 3 nucleon correlations, and in principle so on and so forth. So this is where we're trying to look. And this is SLAC data from way before my time, and it actually looks pretty good and promising. The thing is, this is not how it was originally published. It was originally analyzed and published in terms of a Y-scaling picture. So Y-scaling has kind of fallen out of fashion. But basically, you extract a universal scaling function that's independent of kinematics. It's related to the momentum distributions, but you can't exactly get to the momentum distribution. But this is moderate Q-squared data from SLAC. It looks pretty good. This is helium-4 to deuterium, and this is iron to the deuteron. These look flattish, these look less flat. So the thing to keep in mind is it's not enough to just do this measurement and take the ratio. There is some kinematic dependence to these plateaus. This is early data from Jefferson lab at 6 GeV in Hall B. These are ratios, nuclear ratios to helium-3, but you're still taking them in the region where you should be dominated by 2 nucleon correlations, so you still expect to see a plateau, even though it's not a deuteron, it's in the denominator. So, and you have 2 pictures. One is for low Q-squared data, one is for slightly high Q-squared data, and you can see this ratio just keeps going up and up and up. And over here, all of a sudden, it's like, you flip the switch, and all of a sudden you see a plateau. So what's actually happening is you're seeing this, there's a kinematic threshold. So you're trying to probe a nucleon with a momentum that's at least the Fermi momentum, preferably higher. So we usually draw the line at about 300 or 350 MeV. So if I then just calculate the minimum momentum for a bunch of different Q-squareds and plot them versus x, you can see for x of 0.5 or 0.1, for Q-squared of 0.5 or 0.1, you can't scatter, you can't probe a high momentum nucleon until very, very high x. So if you were to take a ratio, you maybe see a point or 2 points, so you wouldn't really see a plateau. So if you want to have kind of enough of a lever arm, you have to move out this way, and that basically corresponds to Q-squared of about 1.5 or higher. So that's why we see the plateau start at about x of 1.4 for it. But this also clearly is telling you that if you're taking data at a variety of different Q-squareds and is due to these short-range correlations, you should see the onset of the scaling plateau change as a function of Q-squared. And this is our most recent and highest precision data from 6 GeV. This comes from Hall C. And we took data on a variety of different nuclei. As everybody always points out, the plateaus are sometimes very clear, and sometimes you have to be more imaginative to be able to see them. Because as you get to heavier and heavier nuclei, you get contributions from other things. You have the distortion of the cross-sections due to center of mass motion of the correlated pair, which is small and lighter nuclei, but get to be pretty significant. You might have bleeding in of non-negligible 3 nucleon correlation contributions. So, however, even if the shape is not perfect, we still are in the region where most of the strength comes from this 2-body interaction. So even if it's not flat, the ratio is still proportional to the it's a relative measure of short-range correlations. So, and just as I said earlier, we can actually also see this in the Hall C data. We almost always, those ratios that we show are the lowest value of Q-squared 2.5, but we actually took data all the way up to 7.4. It just doesn't have good statistics all the way out to x of 2. But, so you have helium-3 and carbon over here. You can see this Q-squared dependence that I was talking about, the red points, which is the lowest ones. You don't see like the approach to the plateau until later in x, whereas the high Q-squared points, it's easier to see, you can, I guess, see it easier in carbon. They kind of stack up because when you go into higher values of Q-squared, your mean field contribution dies off sooner, so your scaling plateau can turn on sooner. And a lot of people complain that Bjorken X is not really a good variable to look at. And the one that's proposed by Misak Sargsyan at Florida International University is this variable alpha. Intuitively, it is what X should be. It basically takes out this remaining Q-squared dependence, and basically the threshold, you can see the threshold for scaling ends up showing up in the same place in alpha. So when we analyzed this data and extracted our plateau values, we actually did our cuts in alpha. So that's what we know from inclusive experiments. That's where we get our relative measurements from. We also learned something interesting from knockout experiments. So this is where you knock out a high initial momentum proton and you look for the correlated partner and you see what comes out on the other side. So if we're missing momentum between 300 and 600 MeV, almost all the nucleons that were part of this two-nucleon short-range correlation were overwhelmingly NP pairs. So you knock out a proton, and 90% of the time on the other side, you see a neutron. And this is, the error bars are large, but this measurement has been, a follow-up has been done, and these results hold. So where all these short-range correlation pairs are, almost all of them are actually NP pairs, so extra piece of information. And this is understood in terms of this calculation by Villa and Valmoringa and others, is that in this region, we're looking between 300 and 600 over here, the PP contribution is heavily suppressed. It's due mostly to the tensor interactions, so we are only sensitive to PN pairs. But I guess the idea is that this 90% dominance will change as you go to, as you start to move to the right. And I don't think I have a plot of it, but there's a measurement in Paul A. Still large error bars, but it seems to support this, that the fraction of PP pairs grows as you move into higher missing momentum territory. So data mining using class has been very useful because there is information on lots of different nuclei collected over the 6 GeV era, and an analysis by Orr and Company shows that this NP dominance continues for heavy nuclei. They did the initial measurement for carbon, and then went back and analyzed iron, aluminum, and lead, and you can see that this is still the case. So this looks to be like universal behavior. So it's another thing we learned. So we also tried to look at the nuclear dependence of short-range correlations, but we haven't really figured it out. We haven't solved it. So you take the values of these plateaus and you plot them versus various things. I just chose A as an example because it's an easy one to understand. It's not, none of them give you a good linear relationship, so it's not a function of A, it's not a function of density, it's not a function of removal energy or anything like that. So we don't really still exactly understand nuclear dependence of short-range correlations. The best correlation that you see between these high momentum nucleon measurements is to the EMC effect, and this is my one slide on the EMC effect. These are measurements that came out of 6 GeV era in Hall C, very high precision on several nuclei. This was a measurement that focused on light nuclei, and this is done in the deep inelastic scattering region. You're still taking a ratio of cross sections, but here, the thing that it measures is that, hey, nucleons care about which nucleus they live in. The quark distributions are different if your nucleon lives in deuteron versus carbon. And the size of this dip basically tells you that's the size of the EMC effect. How much are the quark distributions modified in the nucleus? So this is basically the depletion of high X quarks. And that grows approximately with the size of the nucleus, but once again, nuclear dependence is not exact. So the best nuclear dependence for EMC effect and short-range correlations is actually one between themselves. This is basically a compendium of all the data we've taken. We also combine measurements from SLAC because they have targets that we didn't necessarily have. So, okay, this is suggestive, but not really conclusive. So what are we doing in the next few years to expand our knowledge of these things? So a big part of it is the tritium program in Hall A. They'll have the first deep inelastic measurements on tritium itself. There'll be first 6 greater than 1 measurements on tritium, which allows you to look at isospin and 3 nucleon short-range correlation sensitivity, because this will be done in concert with helium-3. So you're looking at 2 sets of nuclei with the same number of nucleons, but they're different nucleons. It'll also involve detailed extractions of proton, neutron momentum distributions, as well as high precision determinations of the charge radius difference. We're also hopefully going to get on the floor in Hall C in the next couple of years to do the next generation version of the inclusive measurements, looking both short-range nuclear structure. Once again, with our choice of targets, we want to study the isospin dependence as well as the nuclear dependence of short-range correlations. By going to higher Q squared at x greater than 1, and I'll show plots later, we also want to start studying port distributions at x greater than 1, which we think we can do. And of course, we'll also extract precision EMC ratios on new nuclei. So just a few more words about the JLab tritium target. This is its little container. This is some technical details. This slide I stole had a higher administrative current limit, so that's been lowered now to 20 milliamps. That doesn't sound right, it should be microamps, right? So this is coming to us from Savannah River National Lab, and as soon as it's done being used, will promptly be shipped back to Savannah River National Lab. And it's a high pressure gas target. So these are the measurements that I previously mentioned that are being done. So you have a relatively small amount of tritium, and it's all machined from a single block of aluminum. So it's been many years in the making, but it's very exciting to be able to do these measurements. So be able to hopefully probe the isospin structure of 2 nucleon correlations. And here this is an inclusive scattering measurement, so there'll be high statistics, small final state interactions, because once again we're doing ratios. This is very simple estimates for 2 nucleon correlation region. What we should see if these correlations are isospin independent versus full NP dominance, it should be a pretty good lever arm. We should be able to differentiate 1 from 1.4 in the ratios. And since these are light nuclei, A equals 3, few body calculations actually exist, so we can compare to theory predictions. So that's an exciting measurement. There's also an exclusive helium to tritium ratio. So this is also, once again, will be done for proton knockout, but no neutron detection in this case is required. So if there is NP dominance, even at high missing momentum, it'll imply that this NP ratio should approach 1. So it'll map out the difference between proton and neutron distribution up to and even a little bit beyond Fermi momentum. So those are the short-range correlation things going on in Hall A. In Hall C, we'll hopefully be running the next generation of the EMC effect and the inclusive correlation measurements in the next few years. So these are the combined kinematics for the 2 experiments. It's a Q squared versus X plot. You can see we're trying to push very hard all the way up to X of 3 with low super HMS angles. This will obviously be less than 1 part will be EMC measurements, and these will be our high Q squared X greater than 1 measurements. And as I briefly flashed up earlier, they do seem to have suggestive similar nuclear dependence that was revealed by the fact that we focused in the previous run on light nuclei. So beryllium shows up at a low effective nuclear density, but it has a larger EMC effect and a higher value of A2, the short-range correlation parameter, something that's more akin to helium-4 or carbon. And this is explained by the fact that while the beryllium nucleus is mostly empty space, most of the individual nucleons in beryllium live in an alpha cluster. So 8 out of 9 of them actually live in high-density configurations. So if it's this local density that's driving these effects, that makes sense that while its average nuclear density is low because it's mostly empty space, the local density is high, so you see an effect that's similar to nuclei that have higher densities. So we then, spend a lot of time thinking about what nuclei we want to do our measurements on for 12 GeV, and we basically came up with not all the nuclei on the periodic table, just a lot of them, but we were once again adding more what we consider to be interesting light nuclei to further flesh out this relationship, look at nuclear structure. But also, we want to do scans for heavier nuclei. Basically, it's an approximate scan in N over Z across several nuclei. So I think this is what we proposed to the ERR 2 weeks ago, and none of these should be problematic. They kind of fill the space of the periodic table nicely. So two nucleon correlations we've seen a lot of, we've gathered a lot of information on, we know a lot about. What about more nucleons in a correlation? This formalism for the cross-section, it says, hey, you have A2 over here, which is the ratio, relative ratio of cross-sections in the two nucleon correlation region, but it just keeps going. So in principle, you can have 3 or more nucleons in a correlation. And if we see the two-body interaction dominate in this region in X, if we keep going higher in X, we should see a second plateau, we think naively. The first measurement of this was published in 2006, and it certainly did look like you're seeing a second plateau at X greater than 2. So these are data from class. The ratio is 2 helium-3 of several targets, helium-4, carbon, and iron, and it certainly does look like that. And these data were taken at an average value of 1.6 in GeV squared. But then, so we release our data from Hall C, which is at 2.7 p squared on average. And while we agree perfectly in the two nucleon correlation region, the two sets of data points just fly apart after that. We, of course, the helium-3 data ended up being marginal, so we can't say that we do or don't see a plateau in a different place, but we certainly don't see one here. And I think these points I would still trust, so it looks like the ratio is definitely still going up, and there is nothing that even approaches a plateau before 2.5. So we're like, hey, what's going on? Maybe there's a similar threshold issue like there was with two nucleon correlations, where there is some Q squared you have to get to before you see 3 nucleon correlations. It's just, the math is not nearly as straightforward for 3 nucleon correlations. But it was explained by an analysis of Duck, Higginbottom, and Orr-Hen. So basically this is a bin migration issue. So we took our data with a high momentum spectrometer, which also has fairly good resolution compared to class. And you have to be careful when you're binning, when you're actually binning in spectrometer coordinates versus X, versus binning in X. You have to make sure that the size of the bin doesn't exceed the resolution of the spectrometer. So if you bin an E prime, basically all of these points that correspond to what we originally thought was a plateau basically come from 1 or 2 E prime bins that in reality correspond to a much lower X. So in that way, they then become consistent with the Hall C data. So we thought we saw a 3 nucleon correlation plateau, but we didn't. And then this was followed up by a measurement in Hall A 5 years ago, right before the shutdown, basically, that specifically focused on trying to find this 3 nucleon correlation plateau. So this is a ratio, they had a long target, so you didn't have an issue with statistics. There's a lot of helium-3 in there, and they extracted this ratio for several different values of Q squared. They're mostly comparable to the Hall B measurement. So this is a lot of information on the same plot, but basically you can tell that there's also no suggestion of a second plateau. This is still preliminary, but the paper should be finalized sometime this summer, so this is not going to change very much. But they don't appear to see a second plateau either. Another cool thing that's going to come out of this measurement is they also aim to study the isospin dependence of 2 and 3 nucleon correlations by taking ratios on calcium-48 with calcium-40, same number of protons, wildly different number of neutrons. This is a preliminary ratio. And depending on where, and this doesn't include a 5% normalization uncertainty, so the error bars are actually, I think, big enough to touch both lines, but they're likely to improve, and hopefully we'll be able to differentiate between the two lines. One is for NP dominance, one is for, no axis-spin dependence. But if we just look a little closer, can we, like if we think about, oh, we didn't see a second plateau, can we actually see a second plateau? Maybe we can't. So these are cross-sections for several different nuclei from the Hall A measurement, and the line is just a cross-section model that was used to do various fractions. It's basically based on Y scaling, so there is no specific 2-nucleon or 3-nucleon correlation pieces in the model. So when we take ratios to the deuteron, we, the smeared short-range correlation in a heavier nucleus is going to look similar to the deuteron, meaning that your ratio is going to be somewhat flat up until x of 1.8 or 1.9, and then the right about here, and then the cross section takes a dive because it has to go to 0 for the deuteron at x of 2. So similarly, when you take a ratio to helium-3, that cross section has to go to 0 at x of 3, and you can see that basically it's going down very fast. Starting at about x of 2.6. So you potentially have a very small region in X where if there were a plateau, that you could even see it. So it's not clear that there's enough of a range where the plateau would appear that we could pick it out and say definitely that's what's going on. There might be another issue. So apparently it's on a different slide. But we're going to try anyway. So the tritium measurements are also going to try to isolate 3-nucleon correlations in the ratio in a ratio of tritium to helium-3. The thing here is a little harder. With 2-nucleon correlations, you just have a back-to-back situation. Here you can have different configuration. But luckily, they would produce very different ratios. So by looking at these cross-section ratios at x greater than 2, you should be able to learn something about 3-nucleon correlations and which flavors they come in. And we're going to reach to x of 3. We're going to try to go there in Hall C as well with all these targets. And we might end up taking ratios not to helium-3 but helium-4 just to avoid this issue of the cross-section going to 0. But this is what I was alluding to. There might be a second problem. So earlier I briefly mentioned, hey, we have this other variable alpha that Misa calculated, which is much better for looking at 2-nucleon correlations. He also has a variable called alpha-3n, which helps you think about where 3-nucleon correlations should appear. And this one basically takes the 1 nucleon being balanced by 2 nucleon scenario, and it calculates what the minimum alpha would be. So he tells me that the minimum alpha is 1.6, which I should be able to see at q squared of 3, but the other thing is that you have to wait until basically the 2-nucleon contribution dies way off, so that you want to not just be able to be in a region where you're sensitive to 3-nucleon correlations, but where you're dominated by them. The same way that we go to x of about 1.4 to do the 2-nucleon correlations because we don't want to be seeing any of the mean field strength. Similarly, you have to go a little higher if you want to be sure that you're just hitting 3-nucleon correlations only. And that happens, he says, closer to 1.8, which is a higher value of q squared, which we can't get to in our next set of measurements. But maybe he's wrong. And maybe it sets in earlier. So this is where we are. This is what we've learned from the 6GeV era. We have quite a few experiments coming up in just the next couple of years, both inclusive and exclusive on a variety of different targets. Hopefully we'll learn a lot more about short-range correlations and their nuclear dependence. And hopefully we'll have new results in the next few years. Thank you.
We have time for one quick question.
It's very nice summary, but there are a couple more experiments that are coming up that are going to look directly at the the EMC effect is a function of nucleon momentum in the nucleus. Yep,
So
exactly.
these are my backup slides because I focused on short range correlations, so I didn't want to, but Larry's right. There's a couple of experiments that are going to look at deep inelastic scattering by tagging high momentum struck nucleons and looking to see what happens with that spectator nucleon. So this is one of these. I don't know how soon in the future that's coming. There is another in medium nucleon form factor measurement as well. So like I said, it's not exhaustive.
No, to look directly at how short-range correlations of the EMC effect are related rather than just measuring.
Sure.
Let's thank Nadia one more time. to have Anna Hayes from Los Alamos with us today. She's going to be talking to us about applied nuclear physics.
Okay. All right. Thanks very much. Okay. Well, thank you for the kind invitation to speak on applied nuclear physics. So I'll mostly be talking about lower energy nuclear physics. So that's where most of the applications come from. And Larry just asked me if I started in applied physics, and the answer is no. In fact, I don't know anybody in nuclear physics who's in applied physics who started in applied physics. So most people come from fundamental nuclear physics and get involved in various things. So the field is very interdisciplinary, and in general, one is working with people in other fields, medical physics or nuclear engineering, plasma physics, and so on. And so, as I say, it's not something that one is trained in. It's more that we apply nuclear physics to try to solve other general problems. So I'll try to give you a feeling for this, but let me just start by saying, if you look back at the work that was done from the very, very early days, in fact, this is not so early, it was in the 1940s, but nuclear physicists have always had this attraction to solving problems for society in general. So this is actually a photograph of the first reactor. It was designed by Fermi and Szilard, and if you want to get into nuclear engineering, i.e. how do reactors work, I strongly recommend that you read their original report, because they worked out all the physics for this. So what we're looking at these are small spheres of enriched uranium, and this is embedded in graphite. And so the purpose of graphite is to moderate the neutrons, get them down to low enough energies so that the reactions that dominate are fission on uranium-235. And so the design of this is very, very clever, and it's all worked out here, but it's modern reactor physics basically follows the same principles. What you're trying to do is design things so that the neutrons produced at fission here have a higher probability of interacting with another sphere than interacting with a material that's not causing fission. But anyway, today I thought I would talk about more modern applications. The number of applications is absolutely enormous. People work on all sorts of things. There's energy problem, both fusion research and, of course, fission for reactors. Nuclear medicine has made tremendous strides in the past decade or so with radiopharmaceuticals and medical imaging, and that's really transformed the field a lot. Another area that's very heavily populated by nuclear physicists is security. And this is both national but international security. And we're, of course, very worried about having a terrorist nuclear attack, which is addressed by nuclear forensics. That would be to analyze it. But perhaps more important is to try to prevent it in the first place, which is the whole field of nuclear non-proliferation and border defense. And there are many people have applied their research concepts to these areas. And then, of course, there's things like supercomputing, data manipulation, and so on, and all of that has also had big impacts on several applied fields. And there's sort of a study of much of this, or discussion of much of this, in the decadal study for nuclear physics. So, as I said, it's not really possible to cover everything in the field. So what I'm going to do is just give you a feeling by going through the various examples and hopefully attract some people into the field. Okay, so let me start with nuclear fusion. So in nuclear fusion, the role that nuclear physics plays is mostly in the diagnostics. So as you may know, I'm sure you know, the National Ignition Facility at Livermore is trying to achieve fusion ignition and has failed, and it is in fact mostly the nuclear diagnostics that explain this failure. So it's now accepted in the community that the main problem that NIF is facing and actually doesn't know how to overcome is that the implosion is not symmetric, it's highly asymmetric. So what you're trying to do is you have a pellet of a DT fuel, starts out about 1 millimeter, and then you try to compress it down a factor of 30. And before they did the experiments, the theorists did all this with their nice codes and said, oh yeah, this is definitely going to ignite. But it turns out, I mean, after the fact it's easier to understand, but it turns out that if you have a very slight perturbation on the initial drive, you can't drive something in a factor of 30 because just conservation of orbital angular momentum, any component of velocity that's not going radially inward, suppose it's going translationally, that has to increase. As the radius goes down a factor of 30, that velocity component has to increase a factor of 30 just by conservation. So the first indications of what was going on were done by the detectors that are placed around the NIF chamber. So there are a number of detectors. They're both neutron activation and also neutron time of flight. And what they do is they measure how many neutrons are coming out of the capsule as a function of position. So of course, I shouldn't say of course, but the 14 MeV neutrons coming out of the DT reaction come out in all 4 pi, so this should be totally symmetric. And relative to one central detector, I believe it's this one, the measurements go from about 0.9 to 1.1 of that. And so that indicates a significant asymmetry. And the question is, how is this asymmetry causing this deviation? So the second nuclear diagnostic that is used does a neutron image. And the image is quite asymmetric. The red region is what's burning. It's known as the hot spot. So this is where the 14 MeV neutrons are produced. The kind of green, or whatever color that is, area, that's the cold fuel that surrounds the hot spot. So what's supposed to happen is this burns, it gets hot, and then the alpha particles produced dump their energy into this cold region, and then the whole thing goes poof and we have ignition. But in reality, the cold fuel actually never burns at all. We never get burned in here. And so the neutron image then explains this result. It's highly asymmetric. And so if the 14 MeV neutrons going out see a more dense material in one region versus the other, they get more downscattered. So by comparing the downscattered neutrons in the 6 to 12 MeV region, they deduced that the capsule is highly asymmetric and is in fact completely consistent with the other measurements of the yield at various angles. Another measurement that is driven by nuclear physics is to measure the timing of the burn. So this we do by measuring the gamma that comes out of the DT reaction. So this is a 16 MeV gamma from DT goes to the excited state of helium-5. And this shows that typically what's seen, this is done by a Cherenkov detector, and the full width half max is about 150 picoseconds. Now that's about 5 times longer than was predicted if you ignite it. And the issue is, basically, once you get, if you really could get something to ignite, it really just goes very fast. What's happening is we're getting a much slower burn that never actually propagates into the main fuel region. Another thing that nuclear physics does in the fusion is we look at very rare nuclear reactions. So it turns out that the prototype detector for the Majorana double beta decay experiment, a copy of that was used to look for these very rare reactions. So now one reaction we're looking at is this neutron or alpha that's born in this hot region. Then on the way out, it can scatter off any D or T ion in the cold region. And then that ion moves forward with some kinetic energy, and it undergoes a DT reaction before it loses its kinetic energy. And so when that happens, you produce neutrons above the 14 MeV peak. And so the interest in this is the failure of NIF is also interesting physics in itself. So, we always, make lemonade if possible from our lemons. And so there's a whole sort of subfield that studies this plasma region because it turns out that it's quantumly degenerate. It has a very high density and the temperature is well below the Fermi temperature. But the difficulty in trying to look for these rare reactions is you can imagine that they're typically, they're called reaction of flight neutrons, but they're typically about 10 to the minus 4 to 10 to the minus 5 of the total spectrum. And so to see these, above the background that the 14 MeV neutrons are producing, you need a very specialized detector. And this is done by actually, there are thulium and bismuth foils put outside the capsule which have threshold reactions. And so this detector that was designed, as I say, for Majorana has been very successful in this program. And there's a lot of study of stopping powers in degenerate plasmas. And so that's a whole sort of subfield unto itself. So I apologize, I'm going to be skipping from topic to topic and not necessarily covering everything, but let's go to nuclear forensics. And so this is a very challenging problem. We hope that we never have to use it, but the issue is that you want on a very short time, if there was a nuclear attack anywhere in the world, you want on a very short time scale to be able to answer a number of questions. So, of course, things like, what was the design, where might they possibly have gotten this from, and so on. So the main way this will be done is that the debris from ground zero or whatever will be collected, and you look at all the transmutation, you look at the unstable actinides, and from that, you can deduce what the neutron fluence must be. And so, well, suppose you were trying to figure out, it had uranium-235, and then that had a uranium-238 case around it. Just to give you a feeling for what would happen is you'd look at the neutron fluence that the uranium-238 saw, and deduce that's higher than the uranium-235, so therefore the 238 must be in the case, and so on. So it becomes a very detailed project. But there's a whole science behind this, and we have national exercises. We also have exercises with the British because we exchange weapon secrets with them, where one team sets up a fictitious set of data like this that you would see, and then the other team has to they're given it some length of time, and they have to describe what they think the device must have been. And so, as you can imagine, this takes time because you have to gather this highly radioactive debris, then it has to be chemically separated in order to do mass spectroscopy to determine these actinides. And so, there's also a need to go to a much faster but less accurate, I mean, you get nothing for free, but you go to a less accurate way of doing this, but get information as quickly as you can. So for that, it's been proposed that you use what we call blocked fission fragments. So that's just a terminology to mean the nucleus that would normally beta decay to you is stable. So you're only produced directly in fission, as opposed to having a whole sequence of beta decays that lead to a fragment. And the reason for doing that is that anything that's blocked is typically highly sensitive to what was fissioned. So cesium-136, if you only had fission, 1 MeV neutrons, its ratio, R ratio, I'll explain what that is in a second, but it's 2. Whereas if you had 14 MeV neutrons, which means it's a thermonuclear device, the number would be 45. And then, plutonium is 22 for pure fission versus 2, and 164 if it were a thermonuclear device. And that's to be compared with something that has a lot of beta decays leading to it in fission, where this number hardly deviates. All these numbers are very close to 1. And then this is more examples. Iodine 130 is blocked, iodine 135 is not, and so you see this pattern in general. So the idea is then that what would be done is that instead of actually collecting the debris on the ground, you would fly into the plume and take many samples, and you want to look at things that are volatile, such as cesium. So the questions that you're trying to answer very rapidly, the main question you're trying to answer is, do they have another one? And so if you want to try to figure out whether another device is possibly in the hands of these people, you need to figure out, was it a uranium or a plutonium device? Was it a thermonuclear? If it was thermonuclear, it would have to have been stolen. It's highly unlikely anyone would be able to make a thermonuclear device. Only very few nations know how to do this. And so we actually, I should say this R value we do is it's the ratio of the isotope to molybdenum-99 divided by the same ratio relative to reactor thermal. And that's used to cancel out, you want to cancel out all uncertainties. And so from a measurement of cesium-136, so there's a whole program working on trying to show that we could do this within 1 to 2 days. So here, for example, what you do is you would grab, so you would take many samples by flying into the plume. So these data are fictitious, okay? But let's say you fly into the plume and you take 3 data sets or so forth. Then the R value for 137 we know has to be close to 1. So therefore I can read off the R value for the 136 in this device. And I get a number close to 2. And I just remind you, 2 happens to be what you would get if it was a pure fission device for uranium-235. And 22 is what we're looking for plutonium. So suppose the data showed you this, then you'd immediately say, okay, this is not a plutonium device, it's a uranium device, and it's highly unlikely to be a thermonuclear device. That would give you some number much higher up here. Another thing is, suppose you find some number that's intermediate, you're somewhere up here on the graph, then you can actually determine what fraction of 14 MeV fissions occurred. That's telling you how much it was boosted by thermonuclear reactions. So basically, for plutonium, it has to be somewhere between 22 for unboosted and 164 for all 14s, and you just get a linear curve, and you read off from this how big a thermonuclear device that was. And needless to say, we know what other nations have. We don't tell you how we know that, but if such a thing happened, this would immediately pinpoint, if you saw that it was what we call boosted, and say it's 20% of the fissions are from 14 MeV neutrons, that would tell you an awful lot of information about what had been exploded. Another related program, this is more to the non-proliferation end, trying to prevent such activities, is considerable amount of work is done on trying to detect the illicit production of weapons plutonium. So any nation that signs the non-proliferation treaty, well, you're either a weapons nation such as the United States, Russia, China, who don't have to agree to exactly the same inspections, or for most nations in the world, they signed the non-proliferation treaty and they're allowing inspections. So you'd be looking to see that somebody is making weapons plutonium, removing the plutonium from the reactor without declaring it. And so basically, to say that one of this is that the plutonium ratio is about 6% for weapons plutonium, and that's only dependent on the neutron fluence. And so from just knowing reactor fluences, the maximum they go up to is about 5×10⁻14 neutrons per square centimeter per second. That tells you the time scale that you'd have to be pulling this out, the length of time you'd have to irradiate it for, and that's typically would have to be larger than 100 hours. So let's take an example. Suppose you declare yourself to be a medical isotope facility, and we're trying to determine whether you are simultaneously producing weapons-grade plutonium. Well, it turns out that the noble gases that are released in reprocessing, several of them are unstable. And so, as I said, weapons plutonium, you would typically have to run for considerably longer than 100 hours, whereas medical isotopes you only run for tens of hours. And so you could clearly distinguish these two. And there are different, for example, different xenon ratios. And so it really has to do with using nuclear isotopes to tell you the irradiation time and tell you whether what's being reprocessed is consistent with what's declared. There are a number of things on muon imaging. A lot of this gets to the news. It's very interesting. So this is to use cosmic ray muons. The first one here is to detect illicit material crossing borders. And it's very simple, but very clever. Basically, you measure the muons that come in at the top. A truck would have, the trucks would drive between two detectors. And you measure the muons that come in at the top of the detector, and then you look at the deflection of these coming out the other side of the truck. And you simply use the fact that the scattering depends on the Z of the material. And so if you see large scattering, there must be a very high Z material in there, as opposed to, say, bananas or something that would have small scattering. So it's not that you would detect, so you have a constraint. You can't hold up commercial traffic and we'll do a very detailed nuclear physics experiment. You have to do this. It has to be practical. So the idea is that you're only looking for this large angle scattering. Once you see it, then that truck would be pulled over. But but otherwise, you can do all of this in less than a minute to just determine there is no large angle scattering. A similar trick is also being used. This was done by the Canadians. This is to verify that spent fuel hasn't disappeared. So spent fuel, of course, is put in some storage containers. Very often it's moved from one containment system to another, depending on how old the material is. And so here they did a set of experiments and a lot of simulations. They're looking at, this is for can-do storage, where bundles along one specific region have been removed, and then you look at cosmic ray signal, and they're easily able to detect that one column is missing, and this was for doing detection over the course of 10 days. Another thing you've probably seen in the news is using cosmic ray muons to look at, determine the state of the core, the central core of reactor number 1 at Fukushima, and the images clearly suggest that the core is missing and that it must have melted down into the bottom of the containment vessel. And that's consistent with, people's estimates based on how the reactor would survive under these conditions. Totally different example. This is work. A lot of this was done by Lou at Argonne and others. This is looking at basically climate-related stuff. They're looking at how water is circulating around the Earth, in what patterns and on what time scale. And the idea is that you look at the noble gases. So if the water starts in equilibrium with the atmosphere, the ratio of argon-39 to all argon, or krypton-81 to all of krypton, is just determined by the atmospheric value, which is determined by cosmic rays. However, once it goes down under the Earth into groundwater, for example, radioactivity starts to determine these ratios, and from that they're able to tell the patterns and how long it's taking water to move from one part of the Earth to the other. And so, for example, the atom trapping techniques that are used to search for shift moments, CP violating shift moments in radium, for example, use the same technique and detector system to look at argon and krypton ratios, because they can see ratios that are extremely small, 1 part in 10 to the 16. So moving on to nuclear medicine, this is a tremendously productive field. And so, I'm sure as everybody knows, that the major contributions that have been made in the last decade are in imaging and in the way in which radionuclides can be deposited on tumors. And so 3D imaging is the one thing that has come a long way. You use positron emission tomography and look at the back-to-back, or almost back-to-back, 511 photons that come out. And so they can do a 3D reconstruction, and this has been very valuable, of course, because they don't just tell you the size of the tumor, they can tell all sorts of things about the tumor and how well it's responding to treatments. The other thing, and this is, again, a very clear example of where collaborations with other fields are extremely important. So in collaboration with the biochemists, they've been able to attach the radioactive nuclei to molecules that will bind to very specific tumors. And determining what will bind, of course, is the biochemistry, and determining what are the nuclei that you want for a given treatment. I mean, very often what you're looking for is something that's radioactive and has a very short mean-free path. And so this has become very popular, and very specific nuclei are chosen for specific cancers. In fact, there's still work ongoing. This is driven very much by the basic research community, trying to look at better detectors for this. This is using liquid xenon, for example, to improve things like to improve the resolution, the spatial resolution, and the energy resolution. And people are looking to try to get at the level of about 3 times better than current detectors. So, that's very exciting stuff. It takes, I'm not really in this field, but my understanding is it takes quite a while for the nuclear physics to propagate to the user in the medical community, because everything is very, has to go through strict requirements. But we've been very successful as a community over the past few decades in really impacting the whole medical community field. Okay, many more examples. Nuclear astrophysics. It turns out that a lot of people who work in the nuclear data business for the applied programs also work in the nuclear data for nuclear astrophysics. So nuclear masses, thermonuclear and neutron-induced cross-sections, weak reaction rates, level densities, beta decays, fission yields, and so on. And so there's a whole nuclear data community. There's in the US, there's Los Alamos, Brookhaven, Oak Ridge, and LBL all contribute majorly to this program, and they provide the nuclear databases that are used. At the computational level, also, nuclear astrophysics has had a big impact too. NIFT is a good example. As you can imagine in astrophysics, if you want to do galaxy formation or stellar formation, you better not be violating orbital angular momentum conservation. To reproduce the shape of galaxies, of course, this strictly has to be conserved. And so some of the early work that explained why NIF, for example, very, very small perturbations in the initial drive of 10 to the minus 4 would lead, this is a computation, but would lead to highly distorted final radii. So they start with a sphere, and they put a very small perturbation on, and then you upload the sphere by a factor of 30, and you find that these distortions come out. And so this was a lot of interaction between the nuclear and astrophysicists that helped resolve what was going on at NIF. And actually, I should say, an unpopular statement of the Weapons National Labs, but the codes that are being used for nuclear fusion have a long way to go to catch up to this. So the advances in computational physics, I think, are a new arena in which they'll be driving applied physics. Okay, one of our favorite topics, the reactor neutrino anomaly. So it turns out that, I mean, the reactor neutrino anomaly is interesting, of course, all unto itself. But it turns out that the fission fragments that determine the antineutrino spectra that are used for neutrino oscillation experiments have a huge overlap with the nuclei that are determining decay heat. So decay heat is the heat that you're getting from the radioactive decay of the fission fragments, and it's very important in reactor physics. So when you turn a reactor off, the decay heat is what's left, and you need to know that your fuel's not going to melt down. So this is taken very seriously. A lot of work goes into producing decay heat and producing a database that the reactor community could use. And so they make measurements there of the total heat that's coming from gammas and from light particles. And it turns out that the high precision spectra that were measured by collaborations such as Diane Bay and Reno and so on really influenced these, and a number of fission fragment yields were changed as a result and gave better reproduction of the decay heat. And in fact, there were things like, one of the nuclei that dominates is yttrium-96, and Jeff is the European database and NDEF is the US. They didn't agree on the fission yield for this by a factor of 2, and it was all the studying this anomaly that led the community to realize that these yields needed to be updated and looked at very carefully. And of course, they're very difficult to measure. I mean, to just go in the lab and do a fission measurement and measure these yields is quite difficult because these have very short lifetimes. So the integral data that you get from neutrinos turns out to be extremely influential in this area. This is another very nice application I'm sure most people have read about, the geoneutrinos. So, for example, Camland constrained the geoneutrino contribution from the uraniums and thorium, not potassium because that has the energy is too low. But the issue is, of course, how much of the Earth's internal heat is driven by various processes, and you want to know how much is coming from radioactive decay in the nucleus, of the Earth, radioactive decay of the nucleus in the Earth. And so, the total energy is 46 terawatts, and it's getting the budget between, the geophysicists spend a lot of time trying to understand how much is coming from the core versus the mantle versus the crust and so on. And so Camland and Borexino put limits on this, that the total amount of the 46 terawatts that's coming from radioactive decay is 29 plus or minus 9. And I believe the core, the source from the core was less than 3 terawatts. And so that's, again, another whole field and involves, neutrino physicists and nuclear physicists have to collaborate with the geophysicists to really understand the problems. And if there were a future directional information, that would put far more stringent constraints. And so, in a sense, applied physics then helps to direct some of the things that neutrino physics would like to do. So we could stay here all day. There are a number of extremely exciting applications. As I said, I started out in neutrino nucleus physics. I still do that, but I can assure you when you get into applied physics, it's extremely time consuming. There's so many exciting problems. So let me just scan through a few, and this is not doing justice to the field. There's so many things. But one thing is what they call neutron diagnosed subcritical experiment. So, as you know, with the exception of North Korea, most of the world has agreed that we will no longer test nuclear weapons. And so to certify, the United States wants to go to these experiments where you have a subcritical system and you implode it, but you zap it with neutrons and measure the criticality, measure the gamma rays. From the gamma rays coming off the device, you can tell the criticality. So the issues that people look at are, as plutonium ages, does the criticality change? And so these experiments will be able to determine that. And for this, actually the parity violation, NP to D gamma, the techniques that were developed in that whole experimental program, those experimental techniques are used to measure the gamma production when you zap a ball of plutonium with neutrons, out comes a pulse of gammas, and those techniques were used for that. And that's an ongoing, and in fact that's a very much a growing program in the United States. There are other things such as neutrino monitoring of reactors. I personally am somewhat skeptical, but is nonetheless worth looking at. Okay, enhanced detectors for non-proliferation. So many fields within nuclear physics have contributed to this area. And so you're looking for things you like, very good neutron detectors at borders and so on. And there are ways, also there are issues of looking at plutonium deposition treaties. So these are treaties where we would agree with Russia that they would dispose of much of their weapons-grade plutonium by burning it in a reactor. When that plutonium comes out, then you want to verify that it was burned. And so a number of ideas come from the nuclear physics community as to what you would detect just by scanning over the spent fuel to verify the plutonium composition of NOx plutonium that's been irradiated. And then finally saying that the fundamental physics community, looking at things like radium-225, they work very closely with the isotope production community. Most of the isotope production done in the United States, which is formerly part of the US nuclear physics budget, but that is mostly directed at producing medical isotopes. And again, there's a strong overlap between the basic community and the applied community. So I think I'll finish there, and as I said, this is just a survey of some areas. There's tremendously more areas, and the selection here, is just ones I came up with, but I'm sure there are many people here who work on different applications. And I hope the message to younger people is that there's really a lot to be done in using the nuclear physics techniques you're aware of to apply them to various problems in society. Okay, thank you.
Time for questions.
So is most of this work being done in national labs or in industry? Where should someone go to find a job?
Okay, if it's security related, it's often dominated by the national labs. For medical nuclear physics is of course dominated by industry and the medical community. So I think the answer is really it depends on what problem you're addressing. But there's a lot of collaboration between the national labs and universities and so on. So it's mostly open. If you want to know details of what you're doing in forensics, then it becomes classified, but most of the research is open.
I have a follow-on. So in this climate in which pure research jobs might be hard to find, what would you say the prospects are for employment in these applied kind of areas?
I'm not in the employment business, but yes, for example, our group at Los Alamos, I'm in the theoretical nuclear physics, well, I'm in it's actually nuclear particle astrophysics and cosmology group. And so, we're going through research at the moment for applied physicists. For those of you who postdoced at Los Alamos or were students at Los Alamos, probably know many of your friends who went to one of these national labs as postdocs and decided to stay. You know, he liked the area, whatever. But yeah, I mean, certainly there's a tremendous need for, I think, young and senior nuclear physicists, and a lot of people balance their time between two fields. They do some fundamental and some applied. And so, yes, I would say that there's very much openings for going into applied physics.
Further questions? Let's thank Anna. Next up we have Jonathan Creel from Jefferson Lab, who will be giving us an overview of the cryogenics at Jefferson Lab.
Good morning. As he said, I'm Jonathan Creel from the cryogenics group here at Jefferson Lab. First, let me apologize for the tie. I knew better and I did it anyway. Sorry about that. Anyway, so I was asked to give kind of a high-level overview of the cryogenics facilities here, maybe talk about a couple of subjects that people might be interested in. It's not meant to cover all subjects. So this is basically the footprint layout of the facility. And the takeaway from this slide is that we have basically 5 major cryogenic installations. We have the CHLs 1 and 2, which are the central helium liquefiers that supply coolants to the LINACs and to the LERF. And we have the ESR, the in-station refrigerator, which supplies 4K and 15K to targets and magnets down in halls A, B, and C. We have the Hall D refrigerator, which supplies 4 Kelvin exclusively to the solenoid, which is in Hall D. And we have, of course, the cryogenic test facility over here at the test lab that supplies coolants for their needs in testing. There is only one cold transfer line on site. It transfers coolant from CHL to the in-station refrigerator as needed to support extra capacity down at the in-station. There is no cold transfer lines that go in any other locations on site. Now I'm going to there's a lot of numbers in here. I'm not going to go through a lot of this stuff. You can read it later if you're interested. But this is a comparison of the original central helium liquefier that was installed at CBAF back in the early 90s. It supplies about 12.5 kilowatts of 35 Kelvin and about 4.6 kilowatts at 2.1 K. It also has some liquefaction capability. Kind of the takeaway from the next 2 slides are, in order to do this, we use about 5.5 megawatts of power on this plant. The second plant is the new central helium liquefier. It is based on the newer technology, the newer things that we've worked in our group to try to push forward. And kind of the takeaway here would be to show you that it produces a little bit more shield capacity and a little bit more 2K capacity, but it does it at 3.8 megawatts. Well, the difference between those two is about 1,700 homes. That's about how much power we're talking about. So it's a big number. So we're quite proud of that. The in-station refrigerator is a machine that was originally installed for the SCAR project back in 1978. It ran for a very short time. It was decommissioned. We eventually brought that plant here and installed it down to service our halls A, B, and C. Originally, in the original CBAF plan, there was just one cold transfer line that went from the CHL down to the in-station, and it supplied all of the needs for the early work that was going on down there. This plant, kind of the takeaway from this is it's basically a 1,500 watt plant at 4K, or you can do a mixed mode of around, this is just another endpoint, but you can do up to 800 watts at 4.5K plus about 1,200 watts at 15K, depending on what targets that are being run down in the halls. It can map out to a lot of configurations in between these two. And We also have, it doesn't say it on the slide, but we also have, again, that cold transfer line where we can transfer up to approximately 20 grams per second from the central helium liquefier down to the in-station refrigerator to boost our 4.5K or our 15K capacity, depending on what the needs are down there at the time. All of our facilities are basically, they run pretty much 24/7, and they supply the coolants to the various loads as needed. The other facility we have is the cryogenic test facility. Actually, it's something I just noticed. This is not the right, this is not the correct presentation for some reason. I don't know why, but I'll keep going anyway. I'll add stuff as I get in there. This is not the one that was supposed to have been uploaded. But anyway, at the cryogenic test facility, we have several different plants down there to supply coolant needs for the CTF, for the test lab. And we have a brand new machine, which I'll talk about a little bit later, but it'll supply about 700 watts at 4.5K and about 7 grams per second of liquefaction. That's this new machine that's right here. It's a Linde L280. The old plant, which we had been using for many years, is the 750 watt 4.5K machine. The difference between these two machines is this one has reciprocating expanders. If anybody's ever seen these, they're kind of like a car engine. They have pistons, they have valves, they have crankshafts and all of that. These are very maintenance intensive. We have to shut them down periodically because it's basically like thinking of your car. If your car engine sat out in front of your house and ran at full power all the time, it would need a lot of maintenance. The new machine comes with twin turbines, which are very maintenance free. They are on gas bearings. They don't require a huge amount of maintenance, that sort of stuff. Then it just gives you some numbers on what the power requirements were. Now the Hall D refrigerator is an exclusive refrigerator down at the end station all by itself. It's a small CTI M2800 machine. It's also a twin turbine, and it's about a 170 watt machine. So if you think about equivalent power, the CHL plants are maybe around 18,000 watts at 4K equivalent, and this one is 170 watts equivalent. So we're talking about gigantically different power levels. This plant provides coolant exclusively for the Hall D solenoid, and it's had a varied life. So originally it was built and installed at the Princeton Plasma Lab back in the 80s. Then in the late 80s, it was brought and installed at the JLab Cryogenic Test Facility. It was actually the first machine they had over there. And then we reinstalled it down at the Hall D refrigerator area and are using it now to supply coolant for that magnet. So what are some of the recent upgrades that we've done? Well, for example, we're constantly looking ahead to try to figure out how we make our system more robust, how we increase our availability, and those sorts of things. During the 12-jet project, we had asked for 6 giant warm compressors for the new CHL2 plant. But because of budget constraints and other things that happened during the project, one of these got down selected. Well, it was the spare compressor. It's the one that allows you to do maintenance on the other ones while you continue running beam. So it's a pretty important piece of the puzzle for us. So we were able to get this machine funded, which, like I said, this is the wrong slide set, so I'll add this. But it was funded through this Strategic Lab Initiative project, which is an extra funding line that comes out of DOE, which is not related to our normal funding budget. And it allowed us to add this $1 million plus machine to now give us redundancy. And so now we have the ability to start this machine, shut off the other machines for maintenance while we're in the middle of running without having to go to 2 Kelvin, which is the kind of the mode we were in before. If we ever had a major problem with this, we would have gone to 2 Kelvin. The new machine that we just installed over at the cryogenic test facility also came out of the SLI program. They gave us funding to upgrade over there so that we could keep pushing forward and giving the test lab more capabilities and allow them to do other projects that they're interested in. One of those, for example, is the UITF, which is the upgraded injector test facility. So basically it's a twin turbine machine. Here it says 9. It's because the guaranteed mode was 7 grams per second, but we've actually completed some recent testing where this machine is capable of much more than that. This is a big difference in liquefaction mode over what the original plant was, as you can see at Fort Keller. Again, it has significantly reduced maintenance requirements, and we are actually using this machine right now to support ongoing VTA testing and testing on the LCLS-2 cryo module, for example. So maintenance is a big deal for us. It's the thing that allows us to confidently say our machine's going to be running. And so we perform significant amount of maintenance on our machines in the background without people really knowing what's going on. Some of the maintenance we can do without impacting the beam schedule. Those are things where we have redundant machines, like that compressor I was talking about a few minutes ago. And so we're constantly doing maintenance on the compressors and round robin through them to try to keep things up to a very high availability. Some of the maintenance requires shutdowns. And there are things like, for example, every couple of years we have to shut down a system so we can go in and do maintenance on all of the electric power systems, the things that people don't think about, like the distribution boxes, the cabling that runs between all of the various loads on site. In order to meet some of the latest NFPA safety requirements, maintenance has to be performed on those things to keep them up to snuff, to reduce the problems that might come up with arc flash incidents, for example. We also have big maintenance items that impact us, which are things like, these are flooded oil screw compressors. So in order to pump the helium, we have to basically flood the helium and oil mixture together. Then we run it through the compressor, and then we have to get out every ounce of that oil before it goes into the cold box, because everything that's not helium at 4.5 Kelvin or 2 Kelvin becomes what? A solid, right? So we have to get it all out. So we have to perform things like, we have these giant carbon vessels that are the last filter for the helium before it goes from the warm compressor system into the 4.5 Kelvin cold box. And this carbon is good for about a 7-year cycle. So we have to periodically shut down the system, take all the carbon out of these vessels, replace it with new carbon. The other big maintenance drivers for us are things like control valve maintenance. A lot of people don't think about these giant pneumatic control valves that control the gas flows around our whole system. They control the gas flows into the cold boxes, back to the compressors, out to the gas tanks, and out to the loads. Well, these things have soft parts in them. They have O-rings, they have seals. Over time, those wear out and they have to be replaced. They also have metal parts that are constantly rubbing against each other, and they have to be replaced or these valves will start leaking. And so we have to perform maintenance on those things every few years. And these are things that we keep in the background constantly going all the time. Typical maintenance cycles for us might look something like this. We have 2 CHL plants. So during the summer, we have gotten into the mode of normally we shut one of those plants down and keep the other one running, with the plan being we would alternate between them to allow us to keep up with the maintenance on them. This summer, for example, we had the CHL2 off, and that allowed us to install the new compressor, because in order to do that, we had to cut pipes and weld and do leak checks and all those sorts of things. Down at the ESR, this says planned summer of 2018. On the other slide, you would have seen it actually is, it's planned generically for 2018, wherever it fits best into the physics schedule. That's not up to me. But we'll be doing things down there, for example, like replacing the carbon and control valve maintenance, and we're also looking really heavily at, we've got some systems on site that if everybody knows what KMAC is, it's very old controls technology. It seems to be a real thorn for us as far as where a lot of our failures are, and so we want to convert those and get them brought up to a better system. The Hall D refrigerator is actually off right now. We shut it down for the summer. We're keeping the solenoid at 80 Kelvin, and it's allowing us to get some contamination out of the cold box and the magnet, and to do some repairs on the turbine inlet valves. CTF was recently off during the spring, and it supported the installation of that L280 cold box. So now we'll talk about a couple of things that people probably have close on their minds maybe, but everybody knows that, you know, a couple of years ago, we actually had a failure of one of our cold compressors. So if you think back to the CHL1 system, we have two 2 Kelvin cold boxes. Inside of those cold boxes, we have 5 cold compressors in each cold box that produce the pressure ratio stages needed to take the coolant from around 2.1 Kelvin in the tunnel up to about a temperature of 30 Kelvin, where we inject it back into the 4K cold box. One of those cold compressors, in particular CC4, failed, and it failed at high speed. We had had a power outage on site that took down all of the equipment inside the fence for a number of hours. It was a failure that occurred off the facility. And normally when that happens, everything shuts down properly. There's safe modes and all of that sort of stuff. So what ended up happening on this compressor is when we secured the system and we restarted it, about 2 hours into our pump down of the 2 Kelvin cold box, this cold compressor stopped spinning abruptly. And when we finally pulled the machine apart and pulled it out, this is what we saw. I don't know if you can make this out, but it's supposed to be a ball bearing set. So this is the remnants of the outer and inner races and the balls that were on the ball bearing set. So it destroyed the ball bearing set. It also gouged some of the surfaces on the inside of the stator and the rotor. And so what we did, we were able to pull from luckily from our history. So when we did the S&S project for Oak Ridge, we had built and designed them a 2 Kelvin cold box, which looked remarkably similar to ours. And we had bought some extra compressors that were interchangeable between our system and theirs. And so we went to them and asked to borrow this cold compressor, and that was installed in our machine, and we got the physics program back online for that next fall. We had, when this occurred, we switched to a 6-jet program. We reconfigured several big U-tubes over a period of about 2 weeks and went to a 6-jet program. And then later, after these repairs were done, we were able to come back up for the 12-jet program that we had in the fall that year. We did send this compressor off to France, and after some extensive work, it has recently returned. It has not been put back into our machine yet because we have some additional work and planning left to do on that. So even more recently, in March of 17, we also had an odd failure occur on cold compressor 5. Both of these cold compressors are in the same cold box. So this is the cold box that kind of was mothballed, so to speak, and put offline for a period of about 15 years. And then we brought it back online when we were doing the 12-jet project. So the 2 failures I'm talking about both have to do with that same cold box. Anyway, so while we were running, one of the cold compressor 5, stopped running. And after we went in and investigated the problem, what we found is there was actually a broken wire inside the cold compressor housing itself. And this cold compressor was the one that had the least number of operating hours on it of any of our cold compressors. It had only been ran for a couple of years. It had been sitting in storage basically since the early 90s. And then we pulled it out of storage and used it in this machine when we did the 12-jet project. So this is likely something that akin to infant mortality. When we inspected it, it looked like maybe they had made a mistake when they were soldering the pins up, and this wire broke off right here. But we have completed the repairs on this, and we have energized it and spun it up to high speed, and it seems to be perfectly okay right now. So we're making plans at this moment to reinstall that compressor back into the machine as we speak. We're working on that. And we will be working toward getting that 2 Kelvin cold box back online this summer. So the takeaway from that last slide is we had a problem with the cold compressor. We found and repaired that one, and we believe the 2K cold box will probably be back and ready by the end of July. And we'll get it back up and running. So again, this is not the right slide set. You may want to have them find the right slide set and put it in because people may want to look at it. There's more information in that. Is there any questions I can answer?
Sorry that we were
No.
mix up with the slides. There's time for a few questions.
You're not allowed to ask questions.
I think at the time that the first CHL was put in place in the 90s, they advertised that the largest refrigerator of its kind in the world.
Say that one more time.
The largest refrigerator of its kind in the world?
Yeah, for 2 Kelvin.
For 2 Kelvin.
For 2 Kelvin.
So how does the present CHL 1 and 2 compare to other facilities now?
We still have the largest 2 Kelvin, especially when we doubled the system. For example, if you look at S&S, for example, their machine is similar on the outside to ours, but it has about half the amount of 2 Kelvin flow coming from the tunnel. The LCLS2 project is going to probably be up there and rival us once it gets to running, if it goes to its higher power mode.
So what do refrigerators say, 4K?
Yeah, so I'll give people a 2-second overview, right? So a refrigerator is, for us, is basically this thing that makes stuff cold, right? But the central helium liquefiers are made up of a bunch of warm components, like giant warm compressors that compress the helium, build up the exogenol. And then it goes into a 4 Kelvin cold box where it gets cooled down, obviously, at 4.5 Kelvin. But then it goes through a 2.1 Kelvin cold box, which is the thing that's actually connected to the LINAC. So it's a multi-stage system with a whole lot of operating parts in it that all have to work in order for it to function correctly. And so at our facility, we have 2 separate complete refrigerators, that one on each LINAC is the 12 JEB configuration. And so for us to run 12 JEB, both of those plants have to work. And we normally, aside from the problems with the SC1 cold box, our normal availability for the other equipment is actually quite high. It's very high. But we have had some issues with this cold box, and we are moving. My follow-up slides that are in the right presentation would allude to the fact that we have recently received money from the Department of Energy to move forward with the design and building of a replacement 2 Kelvin cold box, which would then take over this position that this one is in. And then we would use parts from the other one as spares for the other cold box that's currently running. We have a team of engineers working on the design of this new cold box. It's going to be based on the cold compressor technology that we're using right now for the FRIB project and for the LCLS2 project, which is significantly different than the cold compressor technology we have in our machine. In our machine, the cold compressors are nitrogen cooled. They're mounted inside the vacuum space, which makes them really hard to get to when you have problems. On the LCLS2 machine and the FRIB machines, the cold compressors are mounted externally, like turbines, and they are water cooled. And so you can actually get to them and switch them out if you need to and perform maintenance and those sorts of things.
Jonathan,
Yes,
a very general question. Where do you think the field of cryogenics is going? Because my observation is it seems that there is, the fundamentals of the technology, they don't seem to change a lot. The system becomes they continue to be very large. They continue to be relatively hard to maintain. If something breaks, you have to wait for years to get parts. How do you think that qualitatively the thing could be done better?
Right. Well, I'm going to answer that in a very generic way, okay? Like I said a minute ago, for the most part, everything other than the 2 Kelvin cold boxes have been very reliable. There are spare parts available for them. They tend to run for very long periods of time with little trouble. For the most part, if I were to show you the availability numbers for all of our equipment minus the SC1 cold box, they're incredibly high. And we go to great lengths to try to maintain them very high. This cold box has been a little bit problematic. I personally believe it has to do with the fact that it sat unused for so many years. Things just don't react well to that. But in general, the big machines are going to be what they are. They're very large machines. They require huge pieces of real estate, huge investments. And where the kind of technology is heading, though, is to make them use less power, less water, less LN2. If you looked at the first slides on there, we ended up with extra capacity at a significantly lower, let's call it carbon footprint for that machine. And that's where the real money is going right now into researching. It's building things that are much more efficient. And the more efficient things are, you can make the model in your eye that they also use less power, which means the demands on the equipment are lower, which should help with the availability and make things better in the future. The two Kelvin cold boxes, like I said, we're looking at to design for FRIB, LCLS2, and now us, are a lot better in that the cold compressors for the original machine were designed, I don't want to use this term loosely, but I'm going to say more like a science project. They were, in fact, in the world, there are only 16 cold compressors that look like ours, total, 16, that's it. And so they were more like that. What the model is going to now for cold compressor technology is more like what Linde and Air Liquide use for their turbines, which is more of a modular setup, where the pieces in the turbine are modularly replaceable. They all have very similar designs, so you can pull the mag bearings out of one and put it into another. They all fit. There's only like 2 sizes of each of the major components, and they're all externally mounted, which is a really critical thing to be able to turn around when you have a problem. Because all systems eventually are going to have a problem. It's trying to design the system so that you can work on it quickly. And that's the problem we suffer from here, is when we have a cold compressor issue, we have to warm the whole thing up by pulling out these giant 9 1/4 inch U-tubes. They're huge. Then we have to crane the lid off of the refrigerator, and then we get to go inside and actually see what's going on. So we have to deal with that a little bit. Did that answer your question? Okay.
So Jonathan, your response to Alton, surely LHC must be a much bigger plant than...
Not in the 2 Kelvin round, right?
So the total is larger, but each plant is smaller.
Right. So I guess it depends on how you ask the question. Yeah. Each plant is larger, but yeah. Correct.
Let's thank Jonathan one more time. Next up, we have Chris Cuevas from Jefferson Lab, and he's going to talk to us about DAC and trigger hardware systems for the future experimental programs in the 12J era.
Hello. Try to cover quite a long time frame, but I'm going to focus when I get into the talk. For most of the electronics we designed past CD3. So from 2008, when we received requirements and we knew what type of detectors were going to be built for the new end station, Hall D, and of course the upgrades to the other halls, most of this work got started. So I'm going to roll the credits first. A lot of these guys in the group, there's others that were hired and left for other good jobs, but just to list some of these fellows that we have: Fernando, Ben Rado, Cody, Thank It Engineer Day, if you see them. Most of the designs you'll see in this are a product of their work. Of course, the technical staff that supports all the CAD, the high-speed modeling, the parts creations, the building, the assembly, the testing. So I just want to give them credit first. And again, the focus of the talk is covering front-end readout electronics. I could talk for an hour just on preamplifiers and detector electronics, but this is the focus, is for the data acquisition front end. Again, a brief history. I'll go over system architecture, show you a little bit of our circuit board catalog and how many boards we have to support the 4 halls. Experiment examples. Of course, 1 or 2 slides on performance, and show you a glimpse of what we're doing lately with some of the faster technology and moving a lot of the electronics, the data acquisition electronics, right to the detector front end. So, we've come a long way. First beam in 1994. We supported a lot of things back in the day for FastBus. We built custom trigger applications in Hall B, primarily with VXI and some higher speed VME boards back in the day. And we also built custom electronics for drift chambers, different types of detectors that were in the 3 halls, A, B, and C. Of course, we had to integrate a lot of commercial electronics, LaCroix, Kane boards that were used for readout, and support all the cabling or interface type of electronics. So again, before CD3, 2000, 1999 even, we were already researching FPGA technology, what was going to be the platform, what were we going to go to. And since we had a lot of experience with VME and VXI, a new technology was coming out from the VME International Trade Organization, or VITA, that they came out with VME with serial extensions. And they added a connector between the P1 and P2 on the back plane. This allowed us 10 gigabit links from each VME slot to a central switch slot. If you know anything about VME, you know that each slot has to communicate with the CPU in the master slot. That takes time. It's not a fast way to transmit data, even though it was more than sufficient to do things back in the early experiments. I'll show you some requirements in a second. So we had the idea of transferring trigger information on the back plane. Remember with the old FastBus, you had to create your trigger logic as fast as you could, delay the analog signal in cable, and then send them to the ADC so that the trigger would open a gate and you could measure the charge of the pulse. So it was a little old-fashioned, but it worked quite well. So what we've done is we have 8 microseconds of front-end buffer on our fast ADCs, which sample signals at 4 nanoseconds. We built these devices on a VME 64X or VXS format and added the high-speed serial connection. We also added pipeline architecture. All these boards are sampling at 4 nanoseconds, so we have very tight synchronization, clock distribution system, and we distribute that over a parallel high-speed fiber link for TXRX with up to 10 gig per link, so you get an aggregate of 40 gigabits per second. Let me move on to the next slide. And again, keeping up with FPGA technology, I'm not a salesman, I'm agnostic, but we do use mostly Xilinx equipment, FPGAs. There's a few boards that have Altera devices. One of the reasons quickly is back in I think 2000, Xilinx just supported the I/O quantity that we were looking for. That was the best choice, so we stuck with Xilinx. And just to give you again some history of electronics, 19,000 logic cells in a Vertex 4 device. It was pretty advanced. It had 16 lanes of gigabit links, with a maximum of 6.5 gigabits per second back in the day. That was pretty good for the price as well. And I'll show a latest design. We've jumped to Vertex 7. There is an ultra-scale family, but it has 80 serial transceivers per chip, and it bumps up to 13.1. I think one of the amazing things is the 550 million logic cells. It's a 2,000 pin FPGA. It's a long slide. Again, CD3, this was given to us by Hall D primarily to achieve a very high average trigger rate. High luminosity photons in the Hall. And we had to support an L1 trigger rate, again, up to 200 kilohertz. So our front-end boards had to be able to store information for 8 microseconds and read out that information at 200 kilohertz rate. It was a tough design goal, but we managed to do it. And you can see our scheme for developing front-end crates, and it's very scalable. You can see the number of crates that they have. This is an older slide, but it holds true for the quantity of crates. We could go to 128 crates. fairly low cost considering the scale of all this. And we have very strong firmware engineers in the group. We've developed a very strong relationship with the with the data acquisition group for firmware. All this firmware is now downloadable into the boards, so you don't have to remove the boards to upgrade if you want to put a new algorithm in, those types of things. And of course, all halls are using this equipment. So a quick slide show fundamentals of how this is done. Say a PMT signal, detector signal is acquired at 4 nanoseconds in the flash ADC. So every 4 nanoseconds you get a 12-bit value. What we do here, and this is the key, is we spy on this data in what we call trigger pulse processing. That data is sent down the backplane now over our high-speed links to a central switch slot. So it's collecting all this information from an array or detector signals. Then the real data is just stored in a pipeline buffer, waiting for the physics event trigger to come. And once the triggers are happening, then this data is sent through timing algorithms, sent through pulse processing algorithms, and that's the information that gets transferred for a readout. So again, the trigger information is passed as quick as we can upstream to a global trigger processor. I think I'm getting ahead of myself. But so basically it's a board, it's a crate, and this is a subsystem, and then a global, and then the triggers go back to the front end, and we have a complete data acquisition system. So this is an example from Hall D, again an older slide. I want to point out that there's very large systems for drift chambers, high channel counts, from the CDC, from the FDC. These detector signals aren't part of the trigger. They don't have a trigger, they're not in the trigger decision. The equations aren't written for those signals. But of course they are read out when a trigger comes through. So for the tagger, for the calorimeter, where you're summing signals, we have a crate trigger processor. And again, that information from the crate systems are sent forward to the global systems. There's a lot of acronyms in our world, so this is a subsystem processor. We have a crate trigger processor, and of course just front-end modules. And I'm going to say this board is the flagship board that's made all this possible. And you can see two large Vertex 5. These are 2005 circa series parts. It allowed us to have 16 flash ADCs, 12 bits from each of those chips to the front end here, a high-speed bus between the two chips, and then a gigabit link from each of these boards in the crate to the central crate. We won't go through this impressive list of specs, but you can see it has 2-edge SST readout. We've got several modes, probably many more than this now, on the front end chip to process that analog data. This board's been used at Brookhaven. This board's been used on just about every experiment at the lab, for Charles Jebb at least. So again, here's a little more breakdown of the crate trigger processor. Now, under the hood there's two large, they're LX series Vertex 5 parts. And if you notice that this is not a VME connector. So this is the board that sits in the central switch slot. And all these boards up to 16 feed that central trigger processor through the high-speed serial lanes. And since there's 4 lanes per slot, you get an aggregate bandwidth that's very high. And then we have parallel optics in the front, and you can see the 8 gigabits or 1 gigabyte per second goes forward to the subsystem processor. And again, while signals are coming into the front ends of each of these, there's an 8 microsecond buffer on each channel on the flash port. Is there anything else that's, no. So this is jumping ahead close to 10 years. And what we did, let me go back to this real quick. This is a switch slot, and Xilinx, of course, these are Vertex 5s. Well, we have installation, we got to put crates together, we got to test, we have a lot of things to do to get 12G GeV running in Hall D. That was the primary goal when we first started this. So all of this was designed. Meanwhile, the FPGA world, electronics, as you know, probably was iPhone 2 at this stage. I don't know, what is it, iPhone 9 now? So this advanced. Xilinx didn't stand still. So we actually made a board, and what's under the hood here, you can see the extremely large heat sink, because there's just one giant Xilinx part under here. It's a Vertex 7. It has 80 transceiver lanes to drive many more ports on the front end. So what happened to the crate trigger processor mainly merged into what we call just a VXS trigger processor. It can do both. It can do the crate trigger processor algorithms, collecting information from all the slots. It also functions as the global trigger processor. And that helps out significantly because we can load, there's also an independent Zinc chip. It's a system on a chip. It's a separate chip from the Vertex 7. So we load CODA, which is the software that runs data acquisition around, for each of the end stations. So a CODA readout controller is running on this Zinc processor. It's Linux. It's a Linux OS that runs. So this has two functions. We haven't tested it for the readout yet, even though I think that's going to be close. It still functions primarily as a trigger processor that runs CODA. And you have many more ports in which to deal with different detector elements or transferring of data or trigger information. Let me go back one more time to just show you. The first generation crate trigger processor only had one fiber link because the number of transceivers on these Vertex 5 parts was much less. And they weren't as fast, they weren't as powerful. What else did I miss on this? Yes, and we also added now a readout path. So the information that's passed on each of the payload slots to the central slot is not only trigger data, but we could easily achieve readout from each of these boards. We don't have to use the VME bus to read out the data. So when a trigger event comes, that information, the data, not the trigger data, but the data, readout data can be passed through Ethernet at this rate. So we can easily surpass the 200 megabytes per second readout limitation on VME. So here's just a simple table which shows you the quantities of boards we have in the halls now. Don't pin me to the ground, but I think these are fairly accurate. Halls A and C, you can see, don't have as many channels in their halls, so the quantities are much lower. We're up around 600 to 700 boards for the flash board because they're the front-end device from PMTs and most of the detectors. And I didn't cover most of the trigger interface boards because there's just not a lot of time here. You can see trigger processors. And one thing that might not be obvious is in Hall B, in Hall D, they used the crate trigger processor. They came online first. So the design morphed, we changed it. So now in 2017, the trigger processor is in Hall B. So that's the difference here. They needed 30 in Hall D, so they have a 2009 design. In Hall B, we're 2016, 2017, they have a 2016 chip. So it's a different design. And just to give these boards credit, again, these boards are not in the trigger, but they're significant amount of work, especially in Hall D. There are some custom boards for Hall B, but since we have such a nice backplane format, a nice standard in VXS, these boards were developed so that they're not in the trigger, but they're readout boards. They're in the front end. They have, for example, this F1 TDC chip. There's two models. One's a 48-channel board at 150 picoseconds, and one's a 32-channel at 57 picoseconds. This Flash ADC 125 megasamples per second is also a custom board, 72 channels, which is very impressive, 12-bit, and it mates with a custom ASIC for the CDC and FDC detectors in Hall D. And in Hall B, same thing. The Silicon Vertex tracker, you decided to use an older ASIC. It's the Fermi, I'm going to forget that one. Fermi Silicon Strip readout, there it is. ASIC chip, and we interface with that to a custom board that has Xilinx, and it's a VXS board, of course, strictly used for. That's not true. This one also has trigger output, so it has readout plus we put some bits in there for trigger. And recent design of a drift chamber readout board to completely replace its fast bus. There's 264 boards total, 252 in the system. And it's a 96 channel, 1 nanosecond TDC that's in a 6U format. That's another very impressive amount of work. So here's a little slide, one slide only on performance. Recent, Dave Lawrence gave me this slide showing at a high intensity review that, they're able to run 90 kilohertz, 100 kilohertz, have approximately 28 VX readout crates. Very high lifetime. You can see the total amount of data collected, and everything's running quite nicely. I think the high intensity run was optimized, so I don't think you're going to get more than 100 kilohertz trigger. I could be wrong on that. You can ask me a question afterwards. But anyway, we've had remarkable success. I'm going to jump ahead to moving readout and smarter electronics right down on the detector as close as we can. In Hall B and Hall D, we have the advantage of low beam currents, so radiation levels are much lower than they would be in high intensity running in Hall C and A. So this device here is a small Artix FPGA. This is a very small Finisar part, just one TX, one RX, running it up to 10 gigabits, but we run it at 2.5. So if you look at this rich, I don't have any mechanical dimensions, it's quite large. There's going to be 25,000 pixels. There's 391 64 anode PMTs. Each one of these boards can read out 192 channels. What you see here is not, there's 3 tubes that can fit on this tile. And one fiber that links to our, again, VXS board, and each one of these boards can handle 32 of these boards. So it scales up quickly, and we only need 5 of these boards to read out that many channels. I think that's pretty nice. Here's another example of the drift chamber readout board. Every triangle or every wire chamber in Hall B has that many anode wires. So this is a 96 channel, 1 nanosecond TDC. Again, VXS format. Data can be read out through VME. Trigger information can be sent to the VTP. And you can now see tracks. You can put multiple tracks together, multiple super layers together. And of course, globally, there's 18 drift chambers in Hall B, so we can now have a full tracking trigger for the entire detector. And I stole this slide because they cleaned it up. This is a very good slide, given at the trends in computing. And you can see starting down here, we can now, we haven't done this yet. We're going to be getting to this point where we can use the VTP to read out the boards in the front end. So through the use of a VTP, the data, we won't rely on VME data. We can read these boards out through the VTP and can pass to the trigger grades, in the global. We can also use it, of course, to send trigger data to the global system as well. And you can see the advantages: 0, very low dead time, and VME bus and some of the controllers they're becoming obsolete, and they're just no longer in the data path. Again, a dual edge SST readout is going to get you 200 megabytes per second. Each link from a board to the VTP is close to 10. So there's just no contest there. We can easily read out each board or multiple crates much faster with this method. A lot of flexibility. We haven't even touched bases on a lot of the firmware capabilities of this hardware. We don't have enough time. Got this under. So for me, I think most of the guys, it's been a delightful journey, to use electronics, thing I've studied forever. You know, pipeline electronics for all experiments is a dream come true. We've gotten rid of some really old electronics, unlike maybe Jonathan's system. I'm designing something with no moving parts. The maintenance comes into firmware, keeping these things up to date. Now, once in a while, you'll get something to burn out or fail, but we have plenty of spares. That's really nice. And keeping up with the technology is not an easy thing to do, especially with limited budget scenarios. You know, making the decision to go to VXS was a really good choice. It offered, at one point, we were a little, not scared, but the industry took off. I think it's also changed from now. There's not very many groups out there that use VXS except for us. We're one of the largest users of that type of technology. Again, keeping up with the FPGA technology is not an easy task. This enormous drift chamber system is complete. Only one sector ran for KPP data run, so in the fall, we'll have all 18 running. The rich detector assembly is going quite well. The electronics has been finished for probably close to a year. There's final assembly in the clean room now. We've got SSPs ready to read out that. This same scheme will be used for the readout of the GlueX dirt detector. They have photomultipliers, dirt bars, if you will, and multi-anode phototubes. And of course, I didn't have time to cover a lot of topics. We still maintain all the fast bus, or anytime someone has a KMAC module or a NIM module, we can still fix that, no problem. And I put a link here, all the manuals, and there's explanations of some of the firmware algorithms and things like that. That's all we got.
We have time for just a couple of quick questions.
So FPGAs are proliferating, both very close to the detectors and in this whole chain of the acquisition. What tools do we have to program these FPGAs and to learn how to program the FPGAs?
It's a great question. For students or for anybody, you can download it right now. If you go to Xilinx, they have free web packs. So they get you started, you download the web pack, and you get programming with either schematics. You can draw a schematic for your logic and it'll build code for you. You can type VHDL code to learn that language. Xilinx offers a very nice high-level, what they call HLS. It's a high-level synthesis package. That would be something to jump right into, especially if you're well-versed in C, C++. You can write code. You have to write it a little different or think a little differently because FPGAs operate on all code simultaneously, basically. It's not a sequential type programming language. But that's a quick start. They offer it free, and you're able to program, a finite list of their parts. You can't. Once you go to a higher level part, you need to buy the license because it won't compile for you.
Well, let's thank all the speakers in this session. Just a reminder that we'll be back at 1:30, which is in an hour from now.
How's it going?
Good, you?
Fantastic.
How are you? Good to see you. You're looking well. And what do you think about your daughter?
I am on the one hand more than moderately proud that she set her sights on something like that.
Yes.
Scared shitless. I'm actually lying head first.
Yes, I understand we've thought about this quite a bit. It's, I don't think you have mine. I am in the store. Empty folder, that's bad. Well, it's on my computer. I wonder if it needs to be in a different port. Funny that it recognizes things, it doesn't recognize anything in there. funny because I know it's on here.
You can't see it?
And it says there's nothing on here on this drive.
I'll poke my head.
All right.
You want anything to eat or drink, Charlie?
Oh, no, I'm fine.
All right.
You're a computer guy, Harry. Maybe you can answer this question for me. Having had hard drives on laptops die, I have learned that they are the weak link on a laptop. And you can replace them with solid-state drives that have basically
No moving parts.
well, a very long life. And on the scale of my remaining life, probably long enough, okay? What?
Fast access.
Yes. And so there are guys that do this for $100. You know, the drives are cheap, but they can't transfer the programs. Now, I am told that the computer people know how to make a clone of what's on your computer, and you could put that on the new hard drive. Can you tell me where I might get that done? Or two ways to go?
The two ways of doing it, if you have a desktop, that program is called Post. Actually, there's a free program called Easy Units.
I would love to hear that.
And you go there and say, oh.
Because I really would like to do that.
If you were here, I would just say, give it to Eric Werlau, and
Yeah, I'm sure. It's,
I mean, if you do come here for there are lots of free programs, and I use EasyUS and it works very well. I did that when
yeah, I would, if you would send me the info, I would
and
appreciate
our
it.
operating system goes.
Yeah, that would be a, so I'm gonna do what you just did.
yeah, and I'll join me out here. I can grab a water and stuff. So
Yeah.
I can get your-
Okay.
Maybe it needs to be in a mode where it's in slideshow or something. Well, it's there, right? It's gonna work, right? But maybe I can make up something. Did it work? Okay, fine. Installation.
Hi, Chris.
How's it going?
Good. How are you?
Very good. Looking forward to this. Come to find out what's on this or whatever. R&D we're doing. It's a secret. I hope we make a list.
It would be like this.
You're not filming that, are you?
Me?
You're not
Yeah,
filming
it's
that,
on.
right? It's on?
Yeah.
Live feed?
Yeah.
Great.
I don't even know what you just said. But
Good.
It's probably funny.
You got the...
I'll rewind it later. Check it out.
Wasn't too bad.
Okay, good. Now, maybe we need a blinking sign.
Yeah, is that a little red light on there?
Make sure it works, because there's lots of movies. There was something else. There was another conversation going on earlier. I was like,
Yeah, actually, that's not a bad concept, right?
Yep.
Yeah, on air. People know that don't trust the boss.
Yeah.
You on air now?
Yep.
All right, step out.
Only a cursory glance.
Okay, so someone should go over this in detail.
Yeah. I'm planning to mostly recycle my slides first. I've given the same or similar talk a lot venues recently.
Not too worried about
I'm planning to use yeah, I don't know. Look at the abstract deadlines coming up.
Yeah, that's right. So if you were going to do a super big
I don't see why we can't, but I know the Hall A and C business meeting, I think overlaps with CC meeting time. So and I definitely, yeah, it would be good to have some coordination on GFP. Yeah, it looks like, yeah, the whole AC business meeting is 10:30, exactly, so.
All right.
Hey, how are you doing?
I think that's Jerry.
Yeah, right. Yeah, there is.
Yep, I gave a talk this morning. So. He's not first. Stewart is first. So we need Charles' talk. There's no Charles. No, wrong Charles.
No, that's nuclear physics days.
Yeah, it was also my first time.
Maybe they'll come during the coffee break.
It came this year I got
okay.
I'm missing things.
You know what that, right? It's 41 p.m. The folder.
21 program. Okay, day. Okay, thank you.
Say so.
Oh, you are. I'm trying to nominate someone, so I know the rules.
It's the PDF.
45 minutes. I think that's supposed to be like 35 plus 10, probably. How long do you think you're going to go for? 40. Okay, so I'll give you a 5-minute warning and 35 minutes of that.
It's a PDF file.
If only, but only if you look in this direction.
Yeah, I'll try. Make it full screen. Great uninterrupted commercials. It's good. See you. Hey, how are you? Good. Why don't you go to edit? No, you
Oh,
okay.
Can we check Stuart's up again since he has animations?
Should be. Of course, all the moving it around.
Yeah, that's fine.
We have, I guess it's time. There's 30 seconds. I'm excited about it all day. I don't turn it on until I have it on because nobody wants to listen to me fiddle with it.
What you think? I offered the gun to Ferdy, he never even replied. I still get emails.
Alrighty, we're ready to begin the afternoon session of the last day of the user group meeting, and we're very happy that Stuart has agreed to give 2 talks. We'll be focused on accelerator R&D. So let's begin.
Thanks very much. We have a clicker.
Yes, and I'm holding it.
Great, thank you. Thanks to the organizers for inviting me to say a little bit about accelerator R&D. This is a very broad topic. It's a little bit like saying give us a talk on physics. So I'm this will reflect my own personal perspective, particular areas in the field of accelerator R&D that I think are very exciting. So I'll just say right up front, I'm not going to cover all of accelerator R&D. There's almost certainly some great topic that you yourself might be interested in that I'm going to breeze right by. Another difficulty with this topic is how to diagonalize the field. The field is extremely broad, which is one of the exciting aspects of the field and one of the reasons it's very fun to work in the field of accelerator R&D. But sometimes it's difficult to categorize and diagonalize the work that we do in this field in a way that is readily explainable. So again, I'm taking sort of a personal approach to that, and I've chosen to diagonalize the work we do in accelerator R&D really along 3 axes. We're motivated to reach higher beam energies. That means developing ways to accelerate particles in smaller physical spaces. When we make accelerators smaller, we also usually make them cheaper, which has a lot of benefits on applications. Higher intensity, often we're happy with the energy, we just want more of it for whatever the science driver is, whatever the application is. A lot of times we're happy with both the energy and the intensity, but we want to package beams in a smaller area in phase space for one of a variety of reasons. We want to do this in the electron-ion collider because hadron beams, large phase space colliding with electron beams that have small phase space don't give you good luminosity performance. So part of the job in an electron-ion collider is cooling the hadron beam to reduce the phase space. In photon sources, we do exactly the same thing because ultimately we want to produce very high brightness X-ray beams. There's some drawbacks from this perspective. You see, I don't have a column that says higher and higher luminosity. Luminosity is embedded, inherently in all of these 3 topics. We want luminosity at high energy. A way to get luminosity is higher intensity, but we have to be very careful about controlling the phase space area that the beams occupy to achieve high luminosity. So let me just say a few general words about each of these areas kind of one at a time. So the quest for higher energy is pretty obvious, motivated in large measure by particle physics and the desire to reach the terascale. If there's some hint of physics beyond the standard model that comes out of the LHC, of course we want to be able to go there and explore it. And there are two ways for accomplishing that. We can collide leptons, electrons and positrons, or mu plus and mu minus beams. I'll say a little bit more about that later. Or hadrons, proton-proton collider like the LHC. You take a look at the collision energy, the so-called Livingston chart of energy versus time. Of course, over 50 years, you see a very steady growth, increase in energy in each of these two approaches. But, you know, honestly, we've fallen off of that track in the last 10 or 15 years. Is there a way to get us back on that track? That's one of the key drivers. These high-level science drivers turn into a set of R&D goals that then motivate research on particular technologies. So to get the high energy, we need significant advances in accelerated gradient. If we're building a collider, of course, that high energy beam has to be delivered in a way that we can produce luminosity. And in some cases, even in a fixed accelerator, a fixed ring, you have a ring. The question comes up, how can you collide higher energy beams within that ring? So that motivates technology development in a bunch of areas. High field superconducting magnets, improving the reach of conventional, I call it conventional in quotes, microwave technology, so particle accelerators that are fed by microwaves that are confined in resonant cavities to accelerate a beam. And then another stream is very interesting, I'll spend a little time on that, is making use of very strong electromagnetic fields through mechanisms other than confining microwaves in pillbox cavities. What about using electromagnetic fields that are produced in plasmas? A lot of interesting work there. Now it's interesting that although you can sort of talk about one high-level science driver, this research that goes on ends up benefiting facilities that may have nothing to do with that original motivated input. Light sources benefit from these same developments in technology, because if you come up with technology to make a more compact accelerator, there's ways to generate photons using that technology in a smaller footprint. Electron-ion colliders will make use of many of these very same developments, developments in high-field superconducting magnets we need right away to extend the energy reach of an EIC. And then the motivation, as I've written it here, of course, is the highest energy colliders possible for particle physics. Another interesting element of this whole circle is that in the end, someone figures out how to make money based on that technology. So someone figures out a way to make money by solving a problem that is important to people. And that could be a problem in industry, a problem in medicine, a problem in national security, applications completely unrelated to the original science driver. Again, another aspect that makes accelerator R&D a very interesting field in which to work. When you're talking about high intensity, that's pretty obvious. This is, let's just use the words intensity frontier science, whether it's nuclear physics or particle physics. Basic material science using neutrons. So if one wants to use neutrons to understand materials, most of those experiments are neutron starved. So one needs high intensities to generate higher and higher fluxes of neutrons. A lot of the R&D thrust in this area relates to increasing the average power of beams that can be delivered. That's one of the very strong drivers for work that is carried out here at Jefferson Lab to accelerate continuous wave beams of electrons, protons, particles. In other words, CW superconducting RF. When one goes to higher and higher intensity, inevitably one runs into fundamental limitations from the physics of beams, beam dynamics itself, cramming enough charge into a small enough volume. Space charge effects and other effects end up limiting performance. These goals motivate technology. I already mentioned continuous wave superconducting LINACs, sources and injectors for very high average current, very high average power. High power synchrotrons are a very important topic if you're talking about neutrino physics, for instance. And high power target systems are really a key technology development that's important for many of these topics. And honestly, it's reaching the point where in the field, it's sort of a battle between the ability to deliver high power and the ability to accommodate high power or make use of it in a target system. So these things get very complex. This particular one is a picture of a CAD drawing of a liquid mercury target that uses flowing liquid mercury to generate neutrons. There are concepts for free-flowing mercury for particle physics applications in neutrino factories and those sorts of things as well. So we're reaching the limit where it's hard to use solids when one is delivering these very high power beams. More and more we need to go to liquid systems. Facilities that benefit include what we do here at Jefferson Lab, proton accelerators, hadron accelerators across the full range of needs in particle physics and nuclear physics, spallation neutron sources for material science. And because we're talking about continuous wave linear accelerators, the developments in SLAC for a continuous wave X-ray free electron laser build right off of these sort of developments. The applications of these are pretty exciting as well. Isotope production, if we have a way to generate very high power beams, there are a number of interesting isotopes that we would like to produce and harvest. Advanced nuclear systems, this is a little snapshot of a subcritical reactor driven by a particle accelerator in Belgium called MIRA. They're concepts that have been around in the United States for a long time. Radiography using protons, electrons, photons, so a number of applications when one is talking about very high intensity beams. Beams of the right energy and of the right intensity, there's a benefit to squeezing them down and cramming those beams into smaller and smaller areas in phase space. Some of the big drivers here in materials science are the ability to deliver X-rays to very, very small spot sizes, where we're talking about maybe 10 nanometers or a few nanometer spot size. For diffraction, for imaging, for spectroscopy, for materials discovery. Here's one example of a simulation of what one can do with a few nanometer spot related to a national security application. There's concern about rogue circuitry in integrated circuits. And how do you know if one is ordering critical integrated circuits from a foreign vendor? How do you know there isn't rogue circuitry in there? So believe it or not, there's a program to develop very small, tightly focused nanometer scale beams in order to validate circuitry from the point of view of looking for rogue components. And to be able to do that, one has to do elemental analysis and penetrate into circuitry on elemental analysis on the nanometer scale and penetrate into circuitry deeply on the micron scale. Facilities benefiting are, again, across the range of applications. For electron-ion colliders, as I said, we need to cram more and more charge into a smaller area in phase space. A lot of this development really has to do with concepts that involve generating very low emittance beams, accelerating those low emittance beams, preserving that very small emittance, and using that small emittance in order to generate very bright beams of X-rays. Some concepts that, well, I should say more about this in a moment, feeds directly from this is the notion of a compact light source. The holy grail here is a light source that fits on this table rather than a light source that's 1 or 1.5 kilometers around. A light source that fits on a table can fit in the basement of a university. So there are many groups that are looking at concepts for tabletop light sources and miniaturization of light sources. So let's start with energy. Approaches to high energy in the field. Now we really hear about sort of two streams. The first is along the lines of an international linear collider. So colliding electrons and positrons at 500 GeV center of mass. maybe if the physics is there, upgradable to a TeV. It's hard to do this in circular rings because of the limitations from synchrotron radiation. The power generated by the beam simply in the guide field is a very strong power of the energy, so that becomes quite difficult. Therefore, the linear schemes are, at these sort of energies, are the way to go. Even there are two approaches, one superconducting linacs firing at one another, another normal conducting linacs firing at one another. There are ideas that are further out to corral positively charged muons and negatively charged muons into rings and build a muon collider. That is a real challenge from the point of view of handling and manipulating the phase space of muons that are born with a very large phase space area and bringing them down to phase space areas that can be contained inside an accelerator. Along the path of hadron colliders, one hears a lot now about the potential of an FCC, a future circular collider. So, you know, here's a map. There's the LHC. Concepts for a future circular collider of 80 to 100 kilometers are out there. This would bring the center of mass energy from 14 TeV in the LHC up to 100 TeV. Even with this large ring, though, one still needs 16 to 20 Tesla dipole fields, which are enormous and out of reach using today's technology, at least from the point of view of accelerator magnets. So when we talk about different approaches along these two streams, there's a heavy emphasis, of course, on superconducting RF technology, something the Jefferson Lab knows extremely well, and the Jefferson Lab has been involved with, obviously, since the early days. The normal conducting approach, there are a few ideas out there. Here's one taken from CERN, the CERN Compact Linear Collider. That's an interesting approach of using two beams. So there's a drive beam that transfers power in this power extraction unit into the accelerating structures themselves. So this is a transformer of very high current, low energy beam, extracting RF power and instead using that to excite accelerating cavities to bring electrons up to very high energy. Superconducting RF cavity performance in many ways has been motivated by this quest for higher and higher energy, and Jefferson Lab has played a very important role in this. This is a plot that Rong Li has prepared and maintains, showing accelerating gradient in megavolts per meter as a function of time. And you know, Jefferson Lab has played a role really in all phases of this, so it's something that we're very proud of here at the lab. Here's the original CBAF goal in the mid-1980s in terms of accelerating gradient. Here's the CBAF 12GeV upgrade goal, just short of 20 megavolts per meter. Here's the LCLS2 goal at about 16, 17 megavolts per meter. Jefferson Lab is busy building LCLS2 cryo modules right now, and that will be the world's first continuous wave free electron laser based on superconducting technology. Looks like my battery is out. There has been a dedicated program going back maybe 15 years or more at this point on really pushing on cavity gradient in single cell and multi-cell superconducting cavities. So the blue and red curves show the developments that have been accomplished over the last 2 decades in getting very high gradient performance out of single cell cavities, in trying to translate that high gradient performance into multi-cell cavities, where now multi-cell cavities are going up to gradients of 40 megavolts per meter or so. Thank you very much. It is just a statement of fact now that almost any accelerator that people talk about building nowadays is going to rely on superconducting RF technology. It's just clearly the way to go for many reasons. One of the strongest reasons is that one can build continuous wave accelerators to replace accelerators from 30, 40, 50 years ago that were pulsed in nature. The whole reason that we can accommodate continuous wave acceleration is that superconducting materials have about 5 orders of magnitude smaller RF electrical losses than copper systems. That allows high gradient continuous as opposed to pulsed operation, which opens up this whole field of continuous wave beams of protons, ions, continuous wave beams of electrons that are used for a number of applications. The other thread there, so we need superconducting RF for an ILC type collider. We need very high field magnets for an energy upgrade to the LHC, for a future circular collider, even for an EIC. We need ultimately to reach higher energy, the capability of going beyond the materials that are routinely used today. Proton colliders are limited. In fact, the LHC, Tevatron was limited. The LHC is limited by the magnetic field that we can achieve in real accelerator magnets and by the tunnel size. So those are sort of the two knobs that one has to work with here. A high energy LHC would take a 14 TeV center of mass up to 28 TeV center of mass, but it requires going from today's 8 Tesla LHC magnets to about 16 Tesla in the future, something we're unable to do. A larger ring requires those same 16 Tesla magnets, but with a much larger, 3 times the circumference of an LHC to start to get up to 100 TeV center of mass. So this plot shows some of the common superconducting materials that are in use and that are being studied. So this is engineering current density, amps per square millimeter. So numbers we want to shoot for in accelerator magnets are in this range of a kiloamp per square millimeter, or at least many, many hundreds of amps per square millimeter. Here's niobium titanium. That has been the material of choice since the Tevatron was built. You see it's starting to run out of oomph here as we approach 10 Tesla or so. Niobium 310 magnets. Niobium 310 has a critical temperature around 18 Kelvin. It can, and a higher critical field. Niobium 310 magnets are already in use today in the LHC interaction region quadrupoles. At Fermilab over the last several years, a dipole magnet capable of 11 Tesla field was built as a prototype for CERN. And you can see the performance of those magnets should extend up to maybe 15 Tesla or so. Going beyond there, we're running out of room very rapidly. There's a lot of development going on both in basic R&D and in industry on high temperature superconductors. So the class of high temperature superconductors discovered in the late 1980s are copper oxides. There are 2 that are under considerable investigation now. Yttrium barium copper oxide, IBCO. It comes in a tape form that has quite high quite high current densities that can be accommodated. Bismuth 2212. This is so-called BISCO, bismuth, strontium, calcium copper oxide, that has the potential for going out to extremely high fields. The current carrying capability is limited, so there's a lot of R&D underway right now to increase the current carrying capability of this type of superconductor. This is starting to make its way into industry and NMR magnets, very high field NMR, so there's a lot of activity on that front. Another stream that gets away from conventional technology completely involves the use of plasmas and exciting plasmas in ways that generate very strong electromagnetic fields that can be used to accelerate beams. So up to this point, all accelerators really use radio frequency microwave sources to power resonators, either superconducting or normal conducting, to establish either standing wave or traveling wave longitudinal electric fields that are then used to accelerate beams. It turns out, though, that in a neutral plasma, if one drives a high-intensity relativistic electron bunch through the plasma, the electrons repel free electrons in the plasma. They create a core, a hollow core of ions. The ions move much more slowly, so they're sort of frozen in place. And that creates extremely strong accelerating fields, tens of gigavolt per meter, up to 100 gigavolts per meter. That superconducting RF chart I showed a minute ago went up to 50, 60 megavolts per meter, so it's 1,000 times higher. There's also the advantage of some focusing field as well. So if one can manage to plop electrons right into that spot, one gets an extremely high accelerating gradient. So there are two ways to do this, and there are two streams of this research. One is to excite a neutral plasma by the beam itself, as this cartoon shows. If one can arrange to inject the beam one wants to accelerate at the proper phase right after the drive beam, then one can achieve very high energies. Another approach is to excite the plasma with a laser pulse. That laser pulse does exactly the same clearing. It creates a hollow channel here in the plasma. And it turns out in that scheme there are enough free electrons that are actually trapped right at this accelerating phase and accelerated up to extremely high energy. And the gradients one targets in these schemes are at least a gigavolt per meter and upwards of 100 gigavolts per meter. One way to think about this, if you think about today's microwave-driven superconducting cavity, what we're doing in one of these plasma accelerators or beam-driven accelerators is reproducing this accelerating structure. These are individual cells resonating, reproducing that structure in the plasma itself. So what's created in the plasma for a length of time measured in picoseconds is a miniature accelerating structure. So one sees over 100 microns, little individual buckets, RF buckets, into which electrons are either trapped or can be injected. And in those individual RF buckets, the beam is then accelerated to extremely high energy. Here's one example, a recent example of a 9 centimeter long plasma cell accelerating beam to more than 4 GeV. So here at CBAF, of course we do that 12 GeV, and we have to take many laps going around. This is 4 GeV in 9 centimeters. This is, in spite of these great successes, early days for this kind of research, because one needs high beam quality, one needs small energy spread, one needs small emittances, small transverse dimensions. One also would like to have high efficiency in this project, in this process. These processes are quite low in terms of their efficiency. So there's a long way to go, but nevertheless, the fact that we can produce a few GeV beams in a few inches is really amazing. And in fact, it opens up the possibility, even now, for very compact applications of this kind of technology, where one may not need the highest beam quality nor the highest intensity. Here's a simulation of this effect. So what you're seeing is a laser that excites the neutral plasma. You're looking at electron density oscillation in the plasma. And the way this plot is produced, I think energy is going up here. So you see some electrons trapped and shot out right there at very high energy. So this is the mechanism of a laser creating an electromagnetic wave. These are called wave field accelerators, creating an electromagnetic wave in a plasma. There are enough free electrons that are trapped in this little RF bucket and accelerated to extremely high energy. The same approach, not using lasers, but using a beam, has been demonstrated at SLAC with a beam a 42 GeV beam, a portion of which was accelerated up into the 80 to 90 GeV range. So an energy gain of about 40 GeV over, I guess the length isn't on here, I think it's about a 1 meter long plasma cell. So this is 40 gigavolt per meter acceleration. You can see all sorts of issues here. I mean, this is just using beam particles that happen to be at the right phase, and that those small number of particles that happen to be at the right phase are in fact accelerated. This is a long way from turning it into an actual beam. So a lot of the R&D thrust here is how do you arrange a drive beam and a witness beam in the right phase in order to just accelerate the witness beam and end up with beam quality. Charles, I think yesterday mentioned the CERN approach to this thread of research, the so-called awake experiment. And the idea being pursued at CERN is to drive this plasma cell with a proton beam, which should work just as well as an electron beam, and inject electrons at just the right phase, again, to get accelerated to very high energy. So there are many approaches for this. One exciting aspect of this is the opportunity for applications, even now being in quotes, maybe in the next 5 years or so, for very compact next generation free electron lasers. Again, back to the sort of tabletop free electron laser, or tabletop X-ray source approach. So this has been proven and demonstrated already. In fact, here's a little phase contrast image of an insect taken with laser-generated electrons by Wim Lehman's group at Berkeley, the example I showed of the 9 centimeter long plasma cell earlier. Some other exciting potential applications are the notion of placing a laser plasma accelerator rather, right at the tip of an optical fiber and using that for arthroscopic delivery of radiation dose directly to a tumor. So the idea here being you accelerate a beam of electrons right inside the body through this laser plasma mechanism, and what's required is a fiber optic bringing laser light and helium gas into a little cell. There are ideas around compact accelerators for security applications. There are ideas about laser-driven proton and carbon therapy where one starts out with a laser and uses a foil, and the laser-foil interaction itself generates MeV or hundreds of MeV hadrons. Regarding high intensity and high power, there are a number of applications and reasons one wants to go to higher and higher power proton beams, hadron beams, ion beams, electron beams, applications in energy and the environment, isotope production, national security, and then of course the discovery science applications that we're most familiar with. If you ask, when was the birth of this concept or notion of extremely high power accelerators, it goes back a very long way. It goes back to the early 1950s. This is a development that is not even that well known within the accelerator community. It was classified until the late 1970s or early 1980s. And it was an effort in the 1950s to build a particle accelerator, believe it or not, that delivered 160 megawatts of deuterons for the purpose of breeding plutonium, uranium-233, and making tritium. So this is a drift tube LINAC. It's a gigantic drift tube LINAC. It's says on here somewhere 60 feet in diameter. That diameter was chosen because after World War II, there was development in radio frequency sources, and they had a 12 megahertz source, and they wanted to build an accelerator around that 12 megahertz source. So there are railroad tracks that go through the middle of this thing to install this accelerator. You can see another version of this drift tube LINAC with people inside the tank, shining up the drift tubes and trying to make it work. they learned a lot about fundamental limits of accelerator technology, the importance of vacuum, the importance of high vacuum, the importance of surface cleanliness, the importance of surface roughness, all sorts of things. But you know, it harkens back to another era that the government set aside, actually authorized in 1950, $500 million for this weapons program based on technology that was, you know, brand new at that time and had a very long way to go. Since then, I think we've recalibrated our goals in terms of beam power. This shows a plot of proton beam power of existing and planned facilities. This chart's a little complicated. It has average current along this axis and beam energy, so lines of constant power are shown as diagonals. 1 megawatt is sort of state-of-the-art today with the spallation neutron source. The European spallation source is setting their sights on multi-megawatt proton delivery. Accelerator-driven systems for subcritical reactors require 30, 40 megawatts of proton beam power. So there's a tremendous amount of effort across the energy range for particle physics, for materials science, for applications, and so on. When one increases the beam intensity, one inevitably runs into limiting physics. This is known as collective effects. The simplest to understand is just the direct space charge effect. You cram enough charge into one space, any individual charge feels the field of the surrounding charge, which tends to blow up the beam. There's indirect space charge, where the field of the beam responds to the image charges that the beam drags around as it goes through the beam pipe. There's interaction of the beam with its surroundings. That's known as wake fields, where one bunch in a beam excites electromagnetic fields that influence the trailing bunches. The beam may interact with electrons or ions that are in the vacuum system itself. The beam, a positively charged beam, may collect electrons around it and lead to an instability. And then there are mechanisms where the beam emits tremendous amounts of radiation. That's actually the mechanism for free electron lasers. There are a number of superconducting RF R&D thrusts that are aligned with reaching continuous wave operation for electron beams, hadron beams, free electron lasers, and so on. Some really exciting work that's been going on in the context of the LCLS-2 project is increasing the quality factor of superconducting resonators by large factors above what was just the state of the art a few years ago. So some tremendous results in increasing quality factors. This is very important because the size, the capacity of the cryogenic plant goes as the inverse of the quality factor. So a doubling of quality factor has a big impact on the cost of the project and the complexity of the plant that has to be designed. Some other exciting developments are turning toward new materials completely, niobium-310 being one example. I already talked about that in the context of superconducting magnets, but it's really under exploration now in the context of superconducting resonators. One potential for this sort of R&D is if one can actually come up with a superconducting system that operates and can operate CW without requiring a 2K cryogenic plant, that opens the possibility of cooling a system using cryocoolers. So now we have a superconducting accelerator system that looks in some ways like a superconducting magnet system that is cooled by cryocoolers. All sorts of potential applications open up from that stream, ranging from removing pollutants from stack gases using particle accelerators. This is a picture of a pilot plant in Poland that has actually pursued this sort of technology. Treating water, purifying water, treating sewage, believe it or not, treating medical waste, and then a whole host of industrial processes that rely on electron beam driven chemistry for making products. Let me turn to the final topic of higher beam phase space energy. There's higher phase space density. There's a tremendous amount of effort that's going on in the accelerator community in very high brightness sources of photons, of X-rays. They come in 3 flavors. The first are developments of conventional storage rings, taking them to the next step. The second is really centered around free electron laser technology and free electron laser developments. And a third around energy recovery LINACs. Again, Jefferson Lab plays a big role, has played a big role in each of these. There are a number of developments that are underway in the field: high brightness electron sources, techniques for seeding free electron lasers, developing undulators. They're the magnetic structures that generate radiation in free electron lasers. Of course, we need advanced computation to be able to pull this off. And again, this theme of continuous wave superconducting RF acceleration. If you take a look at the photon beam brightness landscape, this is a pretty good snapshot of our understanding today. So this is average brightness. It's in units of photons per second per phase space area as a function of energy. So the LINAC coherent light source at SLAC looks like this, the blue curve. The next generation of storage rings, these look like conventional storage rings, but they're quite different. I'll explain the differences in just a moment. Have a brightness profile that looks like this. It's better than LCLS2. The peak brightness of LCLS2 or free electron lasers is higher. The next generation free electron laser being built out at SLAC, LCLS2, which Jefferson Lab is involved in, takes about a 3 order of magnitude jump in average brightness. It takes about an 8 order of magnitude jump in peak brightness because these pulses are so short. Pulses from these lasers are reaching a few femtoseconds at this point. And then there are plans to go beyond. To make all this happen requires very high brightness electron sources, requires preserving that emittance, requires very careful design of undulator systems, and so on. The mechanism of radiation generation in a free electron laser is an interesting topic in and of itself. And here at Jefferson Lab, of course, we have a lot of experience with this. There's a process for generating radiation that goes by the acronym of SASE. It stands for Self-Amplified Spontaneous Emission of Radiation. And the mechanism works like this. One introduces a high-energy relativistic beam of electrons into an undulator magnet system. The electron beam, of course, undulates back and forth. That undulation results in the emission of radiation, synchrotron radiation. That emission of radiation interacts with the beam itself in a way that bunches the beam. This is an example of a collective instability that's used to good advantage. The beam is bunched through virtue of the interaction of the emitted radiation with interchanging energy with the beam itself in a way that bunches the beam. That bunched beam emits more radiation coherently, and this is a positive feedback loop that builds upon itself and generates very high gain. So you can think of this as an amplifier system where one starts out with a little bit of noise that eventually is amplified to very high power with gains of a million or a billion. Here's a little simulation that shows this at work. It shows the microbunching effect at work. So what's shown here is momentum. So let's think of that as energy. These are electrons. This shows position measured in fundamental wavelengths. So one unit here might be 10 angstroms or something like that. One is seeing the beam itself bunching, forming microbunches, and each of those microbunches radiates like mad because it's coherent emission of radiation at this point. There are enough electrons gathered into one wavelength that that whole unit of charge emits radiation coherently. The peak current is shown here. Again, this is sort of like, well, related to gain anyway. There's 6 orders of magnitude boost in peak current. One issue with that approach of self-amplified spontaneous emission is that it's a stochastic process. It grows out of noise. It takes some initial emission of radiation that then gets amplified. So from shot to shot, one has a very large variation in energy, and the bandwidth on a given shot is very broad. So there's a lot of work going on now to come up with schemes to seed this process in such a way that one can reach Fourier transform limited pulses in time and in energy. So again, another exciting area of research. I'm getting the hook out here, so I better head to the finish line. There's a similar revolution going on in circular storage rings right now with so-called fourth generation light sources. Light sources have been increasing in brightness. These are traditional, this is what you think of as a light source, a circular ring. The brightness of which has been growing by several orders of magnitude about every decade. And we're about to take the next step up to the fourth generation of light sources that takes beams that look like this and really compress them into teeny tiny spots. At Argonne, supercomputing is a big thing. So I used to love to show this plot to my supercomputing colleagues. You ask, how have supercomputers developed over the same period of time? Well, this is the growth in compute speed in megaflops per second over time. This is the growth in X-ray brightness over time. So accelerator community has done quite well. One implementation of this is in the advanced photon source upgrade that makes use of this concept of so-called multi-bend achromat lattice to take beam profiles that are several hundred microns across today and squeeze them down to just 10 or 20 microns in the future, increasing the brightness and coherent flux by nearly 3 orders of magnitude. The final topic in increasing phase space density is very important for us here at Jefferson Lab and for an electron ion collider, of course, is cooling. One problem with hadron beams, proton beams, muons, is that they can be born with very large phase space area, and one wants to compress them somehow into a smaller area to deliver useful luminosity. So a tremendous amount of R&D going on here in terms of sources, guns, kickers, and concepts for carrying out this cooling approach in very advanced designs that rely on energy recovery limits. So in summary, accelerator science, from my point of view, is an engine that really powers much of discovery science. The accelerators of tomorrow, there are a lot of challenges out there that the field is trying to reach through a number of pretty exciting approaches from the point of view of R&D. And one of the exciting things about this R&D is that while directed at discovery science, there are all sorts of applications with the potential to really benefit people's lives in direct ways. And one, in many respects, can expect to see those applications come along even before we reach these enormous energies, for example, from laser plasma accelerators for colliders. Thank you.
Anyway, we have negative 2 minutes for questions.
It should be enough for 2 questions. Anyone? Anything at all? Yeah, Matt.
You know, the tabletop plasma Wakefield accelerators have been talked about a long time.
Yeah.
Do they exist anywhere? I mean,
so I showed a phase contrast image taken from a laser plasma accelerator. So that's real.
Right.
It exists. Now, you know, all the issues I talked about, there are issues with beam quality, the energy spread is large, but it's good enough to deliver that image. We have to be careful when we talk about tabletop, because literally the plasma cell is on a table. The laser to drive that sucker is, is very large. It's not the size of this room, but it's maybe 1/10 the size of this room. So it's pretty big. But a lot of what is being piggybacked here is the enormous development in laser technology. So there are now 100 kilowatt lasers for industrial, for drilling applications, for instance. It's not in the regime we need for particle accelerators, but they're very high power lasers, and they're commodity fiber lasers, and one of the big challenges now is how do you stack up racks and racks of fiber lasers in a way to deliver very high average power. Yeah.
Actually, it was about the same question, so I'll elaborate on it. So, rightfully, this has been an incredible, progress in the plasma accelerator techniques, right? But by the same token, it's true that the first time I heard it was 1982.
Yeah.
Right? And there has also been an enormous amount of resources that actually went into in terms of funding of this accelerator R&D. So from one point of view, it's great and it's inspiring. On the other point of view, it's also, I feel a little bit disappointed by the fact that we have FCC in front of us, right? So if as a community we really believe in that, then we should either get in serious, we're really trying to plan something along these lines, because we are still planning an accelerator like the FCC that is, it's going to happen 30 years from now with perfectly conventional technology, right? So I know I'm just ranting, but what's your view about it?
Yeah, my view is we first have to go to much nearer term targets that are well before, anything resembling TV or multi-TV electron-positron collider based on lasers. The early targets are things like free electron lasers. It's already to the point where one can not only imagine, one can build, it doesn't compete anytime soon with LCLS, but one can nevertheless produce beams of sufficient quality to use for some FEL. Very low power, this isn't a high power FEL, but you're at that point. Some of these medical applications are pretty interesting as well, because you certainly don't want high intensity medical applications. You want small intensity, but delivered in just the right spot in a compact, cheap source. So, my point of view is this. I have this exactly the same issue you do of talking about this technology in the context of we're going to build the next collider based on it. I'm not sure to what extent this is taped, because I have a lot of friends working on this stuff. But there are issues of beam quality. There's a big issue of efficiency. So the efficiency of wall plug power to laser to electrons that come out is not great. And it's a long way from where it needs to be to turn it into a high luminosity, high energy collider. So I think these other targets are much more relevant, and I think the field would serve itself well by focusing on those, actually.
Any more questions? Let's thank Stuart again. All right. We are now moving into the award section of this session. And Jeremy from Sura is here to present the awards. Did he give you this? It has a thing on the side for power.
Okay. Good afternoon. I get to do the fun stuff. But I'm not sure. Hearing Stuart excited about all this may in fact be the ultimate fun stuff. JSA awards presentation. Let's see if I can make this work.
Yes.
That way. This section, we're focused on the JSA Outstanding Nuclear Physicist Award. This is an award that was established back in 2011. It's a 10K award that was underwritten by the JSA Initiatives Fund. It's awarded biannually, so we had one in 11. Count, 13, 14. Oops, 15, and this is 17. So this is the fourth round of outstanding awards. And this year, the decision was made to split the award between Charles Broussard and Charles Sinclair. And you see the citation, let's see, pioneering work in the implementation of the polarization transfer technique to determine proton elastic form factors, and Charles Sinclair for his crucial development of polarized beam, electron beam technology, which made such measurements and many others possible. So these two gentlemen, Charles Broussard is Professor Emeritus at William & Mary, and Charles Sinclair says retired, but many years working here. Bob, you chaired the committee that made this selection, and we're very pleased that these folks are with us today, I believe. Are they? In the audience? Yes. Yes, they are. So we're going to ask them to come down, and we are going to present them with their awards. And we're going to ask the chair of the user group, he would come. Bob, we'd like for you to come, too. We'd also like for Stuart, and I guess myself, to do a photo op with these folks. So, Bob, you were chair of the committee. Would you like to do the honors of the presentation?
This is for Charles Broussard. And this is for pioneering implementation of polarization transfer technique from the proton elastic form factors. Charles Sinclair for the crucial development of polarized electron beam technology, which made such measurements in many years possible.
Sinclair, gentlemen.
Everyone walk over here. Otherwise, you can right like that, your forehead. Perfect. Come forward just about a foot. Or about a foot. And pretend like you know each other. You can turn toward each other a little bit. Okay. If I can get a big smile from everyone. I know. And a few more on a different setting. Get what we can. Again, smile. I know it's hard. Thank you very much, Sean.
Oh, guys, don't go away. It comes with 5K. We're going to split it this year. One for you, one for you. Congratulations, and thank you very much for being part of all your contributions. So now, Charles is going to make a presentation, I understand. I can't go wrong, it's supposed to. Come on down.
That's right. Both of the winners will give talks. We're starting with Charles Broussard.
Give the first one.
My voice is.
Paul is a winner also.
Yes, I'll use that.
Do you hear me?
Yes.
Good.
All right. This is always your hand.
Okay.
I have already paid taxes.
Good afternoon. As you now know, I am Charles Broussard, William & Mary Professor Emeritus since last year. And I am pleased to be here to accept reward for outstanding nuclear physicist award, from JSA. And the title of my talk is An Unexpected View of the Structure of the Proton from JLab. Now, as an introduction, I want first to thank the people who have made all of this possible. And in particular, I want to mention Professor Lina Punjabi, who has been working with me from the beginning, has presented the first two proposals, the second one having been approved in '93. The first one, we were asked to prove that we could use a polarimetry, and has never stopped to be an active member of this collaboration. Then, of course, there has been Mark Jones, Ed Brash, and Lubomir Penchev as postdoc originally, now senior physicist at JLab, and a number of graduate students that are listed here. I want to acknowledge the support of JSA, of Jefferson Lab and William and Mary, grants from NSF and DOE. All of those are thankfully acknowledged. Needless to say that without the work of Charles Sinclair, this experiment would not have happened. So, I have a little bit of a problem here. I should go up the stairs to see what is on the board here. Okay, it's all right. So the physics I am going to be discussing has to do with the elastic form factor of the proton. So what are nucleon elastic form factors? In reaction like EP goes to EP, elastic, just change of kinematics. How do these reactions inform on the structure of the proton, and how are they measured? Traditionally, of course, it has been through cross sections, and I will show results. The new method, which has been becoming possible thanks to JLab, although experiments of this type have been done already before JLab become functional, is polarization transfer or asymmetry. Show results, and then conclude by outlining a small range of things that we have learned on the proton from those results. The title of our first proposal was Electric Form Factor of Proton by Recoil Polarization. Specific. But before I go into that, I'm not assuming that everybody in this room knows what a form factor is, although perhaps I'm wrong. But they were introduced by Hofstadter, Nobel Prize, by writing the cross-section for elastic electron-proton scattering as a Mott cross-section, which is for massless electron on spin 1/2 structureless nucleon, times an integral over the volume of the target, of the proton, for example, of the charge density, times exponential of IQ.R. And you wrote that as sigma naught times form factor to the square. This expression can be rewritten in the way here, and you clearly see that this is a Fourier transform of the charge. So that was a general concept. Now we have more form factors than that, but that was the beginning. In order to go further, we have to make an assumption that the process in question can be reduced to one photon exchange, to the one photon exchange process, where you have an electron that emits a virtual photon, which interacts with the proton, and, and that's the reaction. To write the cross-section, we need to calculate the matrix element of the current. For the electron, which has no structure, let's just get, gamma mu, oh, I'm lost. One more. Gamma mu, but for the proton it's more complicated because the proton is not just a Dirac particle with unit electric charge and a Dirac magnetic moment, but it has an anomalous magnetic moment, strongly anomalous, 3 times as large as the Dirac value, which induces a spin flip. So the current has to be written here with 2 terms, one similar to that of the electron, and the other here which implies a spin flip. So we have two form factors, F1 and F2, which are called Dirac and Pauli. Okay. Now cross sections can be written in terms of F1 and F2, but that's pretty cumbersome. So we have another set of form factors that are linear combination of those that I showed you. One is called electric, and it's essentially the difference between F1 and F2, but F2 is weighted by, where is my factor? Oh, by tau, which is a dimensionless form momentum transfer square, and the other is the sum. Then you can write the cross section as sigma naught times Gn squared plus Ge squared, but G squared is multiplied by this epsilon, which is a kinematic factor, or the linear polarization of the beam electron, and divided by tau. So there is this kinematic factor here. Of course, the mode cross section I don't have to go into. And the procedure then is to transform this expression into what a reduced cross section, which looks as simple as that. All the kinematics and sigma naught are on the left. And so you see that if you plot sigma reduced versus epsilon, you get a straight line with an intercept which is tau times Gn squared and a slope which is G squared. And this is a typical experiment, relatively recent, in the range of 3 GeV square momentum transfer. So by the 1990, before we started, the data for the electric and magnetic form factor looked like what you see here, where what has been done is divide the form factor by this dipole form factor, which behaves like 1/2⁴ at large Q squared, and sort of makes things constant. It's an empirical factor, but there's some physics in it. If you look on the right for Gm, it looks fairly decent, fluctuation of 10% until you reach 10 GeV squared, where things change considerably. But for the electric form factor, the situation is confusing. It looks like one can get different values depending on what experiment one does for the same value of Q squared. That is basically what motivated us at the time. Something must be wrong with that. So, the second technique, which uses polarized electron, had been actually discussed in the literature a long time before we got involved, 1958. What inspired us and instructed us was a paper by Arnold, Clarkson, and Rose, written in 81, which discussed, in particular, polarization experiment for the neutron form factors. So what you have is a polarized electron. H is a helicity, which is one way or the other. Here it can be flipped frequently, like 30 times per second. Very useful. And in the final state, the proton, which was unpolarized, become polarized with two components, one in the direction of the momentum and one perpendicular to it, but in the reaction plane. This is two-body kinematic. You can't have anything going out of the plane. And those two components are on the right. One of them is a product. Oh, sorry. Oh, you have seen the whole talk, no? One is the product of G and Gm, the other is Gm squared. It doesn't take too much work to realize that if you divide one by the other and turn things around, you can obtain Ge over Gm as a ratio of Pt over Pl and just kinematics. This is a very useful formula, as you will see. But the most important feature of the polarization technique is that you are dealing with Ge and Gm, not the square. And you will see why that is actually important. So in our first proposal, we thought we would get Pt and Pl, calculate Pt over Pl, use a good database for Gm, obtain Ge. That was the motivation of the proposal. In the second, we say we are going to measure G over Gm directly as Pt over Pl. That has the advantage of significantly decreasing the systematic errors. In particular, you become independent of a number of things like radiative correction, fluctuation of the beam intensities. You don't need to know the analyzing power of your polarimeter because it cancels out, and so on. Little did we know, as you will soon know, if you have not read our papers, that at the highest Q square that we reached some years ago, GE is actually contributes only 1 part in 1,000 to the cross section, not much over. Okay, so how we do this? We have a proton starting here. We use a spectrometer. Longitudinal component of the polarization is in the direction of motion. Therefore, in the dipole field, which is horizontal, it precesses, and you get a normal component in the focal plane, say, and the other, being parallel to the magnetic field, does not precess, and so is conserved in first order. So up there you install then a polarimeter, which is a simple device in principle, which is a big piece of material. We originally used graphite, then we switched to CH2, preceded by trackers, wire chambers, and followed by trackers. Following the scattering, we measure the phi distribution, the azimuthal distribution of the protons. And what is written here is what we expect for the probability of detection for both beam helicity, F plus minus, is given by this expression. PT, which is essentially the original PT, you have a cosinus phi, and for PM you have a sinus phi. AY is here, but we'll get rid of it. And so with F plus and F minus, if you take the difference of them, you obtain this expression here, which, as you can see, is actually a phase-shifted cosinus distribution, or sinus distribution, phase-shifted. And you see that directly here. This is data taken at 2.5 GeV squared for a number of values of this kinematic factor, which means it's constant Q squared, but different energy of the beam and different scattering angle, that they all cross at the same place. This phase shift here is a direct measurement of PT over PL, actually. It's easy to see it here, but when you go to 8.5 GeV squared, it's not so easy to see it. But it's still measurable. All right, I backtrack a little bit to tell how we built the necessary equipment. For the first experiment, we installed the polarimeter in one of the HRSs in hole A. This is the focal plane of one of the magnets in hole A. We installed front straw chambers here and here to track the particle in, a big block of graphite at the time, and then batch chambers. The front one were built at William and Mary, and here is a picture of it. You see the chamber in the back. These were drift tubes. And these are the students and postdocs who were doing those chambers. The big ones that are bigger were actually built at Rutgers. For the first experiment, we could use a second spectrometer in hole A to detect the electron, but only in that one. In the last experiment, we switched to hole C because of the high momentum of the proton was no longer possible in hole A, and installed an entirely new polarimeter made of two big blocks of CH2 here and here with drift chambers, two of them behind each one of the blocks. So it's a double polarimeter to increase the efficiency. And on the right side, we had to build an electromagnetic calorimeter out of lead glass bars, which we borrowed a large number of them, 1,700. And all of that actually worked. And these are the results. What you see here actually is the first experiment, which was already somewhat shocking, as it did not seem to agree with Rosenbluth result available. This is not all the Rosenbluth results, by the way, but the more recent ones. In the second experiment in red, the difference became unavoidable. And in the third one, we go almost, but not quite, to 0. There is another point which we call 2 gamma. We'll talk a little bit about it later at the end. But other than that, I will just say that the Rosenbluth data required a fairly large radiative correction, up to certain.
We can't hear you anymore.
Oh.
Can I see the thing just in case it died?
I could hear myself.
I could hear you too.
Oh,
But
okay.
yeah, it's getting angry.
Of course, we will give it time.
Seems open. Oh, okay. This is one. These. Yes. It's a full collection of batteries. Yes, and it's green.
It works?
Yes.
It works. I was talking about additive correction being as large as 30% and subject to some uncertainty, whereas for the data from the polarization ratio, it was established quite early by FNSF that because of the nature of the observable, which is to be a double ratio of form factors, so radiative correction are very small, percent level. Okay. Well, this one is not working anymore.
Just change that one.
It is flashing.
It's still working.
Still working?
Just literally just put in new batteries in this one. Seems okay.
Seems okay. Okay. Yeah, it's okay. Okay. So now to discuss those results, here I show you a number of theoretical, the result of a number of theoretical calculations. It is to be said that even before our experiment, theoretical predictions were that in fact this ratio should be decreasing and not constant. But this was ignored, and I just quickly tell you that, of course, the oldest model for this reaction, oh no, I jumped. Were the vector meson dominance models, starting with Lohmann and others. Then we have the constituent quark models, which became relativistic. Then we have the Dyson-Schwinger equation approach for non-perturbative QCD. And then we have generalized pattern distribution, which are interest. Some of each one of those are shown on this figure. They tend all to agree with the data at the beginning, but they somewhat disagree as far as the large Q-square behavior is concerned. Shortly after the third experiment, Jim Kelly performed a very difficult calculation to actually obtain the charge and magnetization density out of the form factor. The problem is relativity. The way things are written are clumsy. Won't find that relation I showed you between density, charge or magnetization density, and the form factors is valid really only at very low energy. So this picture was interesting, but then came Jerry Miller, who told us, no, that's no good. You have to go to the infinite momentum frame, send the momentum, then the form factor is related to the transverse charge density, where B here is the impact parameter. and not R, okay? And then the relation is that the density, the charge density, is the Fourier transform of F1, okay? But that is on the infinite momentum frame. So it's a two-dimensional charge density. Here is the relation between form factors and GPDs, which is interesting. It shows here, for example, that F1 quark by quark is related to the H and F2 to the E function of the GPDs. And if you parameterize the GPDs by such functions as shown here, as was done by Guidal, then you see that in fact the relation between the two observable works largely. This is G over Gn. So the line is calculated from this parameterization of H and E. And this is Gm over Gd. There has been, since 1973, an expectation that at some value of Q squared, the form factors should behave like 1 over, well, let me go in detail, have a predictable Q square dependence, because in the perturbative domain, what is going on is that the virtual photon is absorbed on one of the leading quarks, and for the nucleons to remain together, it is necessary to share the momentum transfer with the other two quarks, and by exchange of a gluon, so two gluon exchange, makes the 1 over Q to the fourth factor. So F1, this thing is horrible, really. Where am I now? Yeah, okay. 1 over Q squared, 1 over Q to the fourth for F1. F2, because of the helicity flip, requires another Q square, so the prediction is that Q square F2 over F1 should be a constant. The data before the JLab experiment suggested that this was true, and it happened very early, 3 or 4 GeV squared. But now, as you can see, the polarization data is not so fast. Wherever it is above 10 GeV squared. People have modified the prediction to take into account the orbital momentum of the quarks, and came out with prediction like this. But the fact is that we are not in the perturbative domain yet. So in this case, we are in the non-perturbative one. And that's why non-perturbative model have been discussed intensely in recent years. In this approach, dress quarks are due to dynamical chiral symmetry breaking. A lot of work has been done by Craig Roberts and his group at solving the Dyson-Schwinger equations, which is, I understand, no easy job. To go quickly, one of the outcomes of this calculation shows that the mass of the quark it increases as the quark slows down to reach a value of the order of a third of the mass of the nucleon, due to gluons coming out of the vacuum and sticking to a bunch of quarks. So this is so-called the fact that quarks acquire a cloud of gluon surrounding a low momentum quark. From this approach, a recent calculation by Roberts et al. And Segovia, which was refreshed a few days ago, shows very good agreement with the data up to 8 or 9 GeV squared. Suggests that actually we would be crossing the zero line not very far from where we are, but there are other predictions. Since a few years, and the first paper published by Cates and others, we are looking into quark flavor separation, namely obtaining the form factors of the quarks, up and down quarks, the dress quarks. Here I use a notation where I call them with a little f, and if you assume Charge symmetry is expressed here. The fact that an up quark in the proton has the same form factors and a down quark in the neutron, and it's the other way around. If you believe this should be true, then you can easily derive this expression here that allows you to obtain the flavor-separated quark form factors in terms of the measured and Dirac and Pauli form factors. So, just to be short, I have no idea where I am with the time, but I'm okay. Here, among things predicted by such models is the fact that in the nucleons there are to be an important component, which is a diquark. Now, the diquark can be either axial vector or scalar. The thing is, when the photon gets absorbed on a diquark, you are not going to know whether it was a scalar or an axial vector, therefore you expect an interference effect. And the result of that prediction was that F1 of the down quark in the proton should have a 0. So if we calculate F1 up and F1 down, I show only those, which requires a little bit of imagination because we don't know the form factor of the neutron, the electric form factor of the neutron beyond 3.4 GeV squared, but you can extrapolate a fit, or you can use a prediction from the DCS breaking prediction, you obtain a 0 crossing in either case. Now, the question, of course, is what about this difference between Rosenbluth result and polarization result? They seem to be incompatible past about 3 GeV squared. As far as I know, the first to suggest that we should look further, namely two-photon exchange, were Guichon and van der Weyden. If you start looking at that, a typical diagram is here. Two-photon exchange means there is an intermediate state here, which is which can be the proton, but can also be any one of the excited states of a nucleon, which are compatible with spin and parity conservation. So, calculation of this process is not simple. I'm sorry, when my fingers are too big for this device. So, there are a number of calculations. Some of them appear to be explaining the difference, but there are big differences between the different theoretical calculations. I enumerate some of them here. The first one was by Fanasef et al. There's no doubt for an experimentalist that this means you have to measure. We have to measure something to see whether we have significant two-photon effects or not. And the best way to do it, in principle, is to obtain the ratio of electron to positron proton elastic scattering. 3 such experiments have now been completed. Unfortunately, and for practical reasons, I am sure, they do not go beyond 2 GeV squared momentum transfer. And things start really to diverge right about there. So they do not answer the question. These experiments do not answer the questions. Here at JLab is what I had called before 2 gamma experiment. We have wanted to prove at the highest possible Q square we could, which was only 2.5 GeV squared, that if you vary epsilon, the result for this expression, which is nothing but Ge over Gn with a mu, if there is no two-photon effect. We measure 3 points with great precision. The error varies typically plus or minus 1%. And we find no effect. There are a number of theoretical predictions here that are shown here. In fact, the absolute value is renormalizable. I am told And the size of the effect is not incompatible with the uncertainty that we have on this slope. But these effects are very small. However, it is only 2.5 GeV squared. So we do not have any information on two-photon effect experimentally beyond 2.5 GeV squared. I have another view of things which I will present to you. I am asking myself, is it not simply that because GE or GM becomes so small at the largest Q square we have reached, you simply cannot see it in a cross-section experiment. You can rewrite the cross-section, changing nothing but we're taking, in fact, GN squared in evidence, and then you have 1 plus a correction term, which is G over GM to the square. Okay? This is exactly the same formula that I showed you before, but trying to see what is the behavior of this GE over GN squared. And here you have it. From 0 to 10, it starts here at about 1. Of course, it goes to infinity at the origin because of the tau. But it reaches 10 to the minus 3 here. 10 to the minus 3. So in order to see GE at such Q squared, you must be able to see something which is a correction to the form factor of the order of 10 to the minus 3. The typical error bars of the cross-section measurements are here. And you see that at 10 to the minus 1 doesn't decrease anymore because of the size of the error bars. So what I am suggesting is that, in fact, there is no disagreement really, but an inability of seeing such a small contribution by GE to the cross-section. Throwing the two together perhaps is better. Okay, let's see. I will conclude. Of course, this was drastically shortened. I got only 30 minutes instead of 3 hours. And, I hope to have given you a feeling about what has happened during the years where we measured form factors by the polarization ratio technique. And I hope to have given you an idea of what the field, how the field evolved following our results. With Nina Punjabi, we have Scholarpedia paper on the web since 2010, and it has been visited 35,000 times. I don't know who is doing this, but right.
All right, do we have questions? Starting here.
I think around slide 14, where you were showing the analyses of Jerry Miller and Jim Kelly, you said that, so the Jerry Miller plots which showed this interesting feature of the negative charge at the center of the neutron. You said that you have to go to the infinite momentum frame to construct that picture, but really it's in any frame, but you have to integrate over the longitudinal coordinate. So it's the transverse density in any frame.
Okay, thank you.
Did I see the hand over there? No, well, let's thank Charles again. And we'll come back at 25 after for the second prize talk and more prize talks. All right.
Not a fan of this, huh? All right.
Probably right now. I remember.
What's the difference between
But open in our, this context, really just bothers.
Miss Stella seems to talks.
One of my colleagues, Nobel laureate no less, said to me, why would I be in a place
I guess the question on that in other words, I think, I've prepared a few slides. It seems to me it would be, when I think about tomorrow's meeting, my goal is for them to hear what I'm thinking about future situations, what I see as the issues. And it seems a little artificial waiting to the director's report to get into this. We only have one. I don't so that's what I'm trying to understand. I would fully expect this.
I don't anticipate. But it's you and I.
These two slides.
So this.
Yeah. Maybe we can rename it.
I guess for me, it's more a logistical question. I'd like some feedback from the board on the way we're thinking, the issues we see. I'm going to go through some risks. Does the board have suggestions, things we're aligned to that we ought to be worrying about? I'm going to go through some opportunities. Maybe there's some opportunities. So I'm wondering if it's worth, in some sense, flipping these things, if you see what I'm getting at, to kind of tee up some discussion by going through slides.
And seeing if there's perhaps some things.
Otherwise the first half hour could just be a little free form without much kind of.
So the emphasis is on the you. The emphasis
So are you
is on
saying
the
that
you.
we line up two?
Might make more.
We have one, we need one more. That no one knows who it is.
Yeah, something like that.
That works, that works. If there's any concerns that the board has, it will bring it.
Yeah, so I'm going to do the last one.
Okay, so we need to for smooth transition. It's her, she's the last speaker.
Sorry.
All right. It's not the one that says just install Ubuntu, is it? Oh, okay.
basically the focus of my presentation. That's the thing I'm concerned about. Do that early. That's all we got some time to discuss. Is that okay? That helps.
Hey, sir, how are you?
For him, 30 seconds. Yeah.
This is the next time.
This is the next time. He's the second.
Sure,
Yeah.
please do.
One small, okay. Most people will.
All right.
Few factors. Don't have any orders of magnitude.
It's not for free.
There's really
In some sense, but superconducting lets you do things you will never be able to do. In addition to this, I think. But yeah, you're right.
I have sitting in my office
And low grade. Yep. More copper. Yep.
No, I mean, as a matter of fact, one of the things I was remembering.
Well, and there's the same, we went through the same back and forth on the splicing process. One GE maybe was the great, it seemed silly to go over its last copper proton rather than the world's first superconductor proton. Yeah, interesting stuff. Well, yeah. I mean, fully is exactly right. It's been a lot of things going on. You may hear from, high energy colleagues that that's going to save the day. OPT, not in any of our I was glad they invited me. KK was very, he had heard me give a talk at the ABS meeting. He was very enthusiastic. He did the program. It was good.
officially listed.
Okay.
Do you mind if Paul joins us? What time do you want to go? Okay. You don't have any,
I'm free.
you're free.
I'm off the user group.
Oh, okay, so this is like,
So I don't
if
have
you
to go
weren't,
to the
you would have
tonight's
to.
meeting.
No, you don't, so. All right, I've got a, where do you stay?
Here.
You're, all right, I've got a minivan.
So what? A minivan. Okay. You know they gave me a Camaro last week. The choice was minivan or Camaro.
How long did you think about that?
The guys behind me were like, take the minivan. He literally brought up 2 sets of keys, which implies there were only 2 cars. There was a line of more than 2 people. Not perfect. The minivan, no one
They just have a surplus of minivans. I got your level for you. All right. Okay, good. Okay.
This guy retired, he's outspoken.
I'll give it a period.
If you could do one.
All right. Let us now begin the last session of this user group meeting. And now we will hear from the second Outstanding Nuclear Physics Prize winner, Charlie Sinclair.
Okay, you will now hear from a real retiree. So, no color, few pictures. Actually, when I first learned about this award, for which I am most appreciative, I probably got asked for a title, and I didn't have a lot of time, and so I thought, well, I'll talk about what I thought I got the award for. And somewhat later, I sat down and started to think about what the content would be, and I realized that there's no way I could even go through a bulletized list that describes these things in the length of time I have. So I'm not going to talk about that. What I'm going to try to do is give you a little bit of history, some of it you may not know, and then walk you through, and it'll be just a handful of high points, I hope, or low points, in the development of polarized sources for these machines. I have to say, it's been sort of a 30-year war, and you'll see that as we go along. So, starting with a little history, how do we know about electron spin? Everybody remembers that Gauss-Schmidt and Uhlenbeck proposed it, but like so many of these things, it didn't spring out of whole cloth. Many people were thinking along the necessary lines. They were unable to fit the spectra of single electron atoms and get the right answers. And Pauli, as he was struggling through figuring out the exclusion principle, came up with this comment, published it, and it's interesting to me because it's the, oops, is this the light? Yeah, the weak light. Anyways, he had recognized that the double valuedness that was necessary couldn't be described classically in his words. Fast forward a little bit into the next year, and Ralph Kronig actually proposed the idea of a self-rotating electron with spin 1/2 and a G factor of 2 in January of 1925, a solid 6 months before Gauss-Schmidt and Uhlenbeck. And he was excited because he realized this would give at least, if not the correct magnitude of the splitting, the correct pattern. And so he flew it by Pauli, who didn't think it was a very good idea, and he ultimately decided against publishing it. Next we have Gauss-Schmidt and Uhlenbeck, and they came up with basically the same idea that Kronig had, and they published it. And after they published it, they spoke with H.A. Lorentz, who was a classical physicist par excellence at the time, and he told them all the classical reasons why this couldn't work. And they quickly scampered back to the journal and tried to pull the publication, but it was too late. So, as I said, this spin 1/2 electron still failed to give the correct magnitudes of the atomic splitting, but at least it gave the correct pattern, and it remained for Lester Thomas in 1926 to do the calculation relativistically correctly. And when they had this, you had all the tools to calculate the spectra of single electron atoms. This was really a considerable leap forward. So, another couple of years, and Dirac introduced his famous and revolutionary equation describing the quantum mechanics of an electron in a Lorentz invariant way. And that naturally led, it just fell out of the equations, as you probably all know, a spin 1/2 electron with a G factor of 2. Promptly on the heels of that, Mott, the next year, published a calculation of the scattering of a Dirac electron off from a nucleus. And his goal, his stated goal, was to determine whether this, what was then an unusual G factor of 2, could you determine the G factor of a free electron by using Mott scattering. That's what his interest was. And the reason is that it was already known at that time that you can't separate electron spins with electromagnetic fields. There isn't any magic combination of electromagnetic fields that you can pass a beam of electrons through and have the two polarizations come out separated. Not possible. So it turns out Mott's solution was correct, but difficult because the scattering amplitudes come out as a conditionally convergent series, and it turns out pairwise terms in that series almost cancel. So you have to sum an enormous number of terms to get a decent answer. And this was before the age of the digital computer. So you had to calculate by hand, which meant that everybody calculated at 90 degrees because that simplified the terms. And they could do just a few energies. That's the amount of wisdom that was known about the scattering cross-section and the subsequent polarization. And there were a handful of early attempts after Mott's calculation to try to measure this. It's not an easy measurement, and it certainly wasn't easy in the days then with thicker foils and terrible vacuum systems and lousy detectors and so forth and so on. Finally, 1943, Clifford Shull, who went on to win a Nobel Prize for neutron scattering, reported a Mott scattering asymmetry measurement, which was at least in agreement with the then calculations for Mott scattering. And at that time, Mott scattering was the only way people knew how to make polarized electrons. So you can quickly understand experiments using polarized electrons were almost non-existent. Maybe the first one of any consequence came in 1954 when a group at Michigan actually polarized an electron by Mott scattering, put it into a solenoid, and let it spin and precess for a long path, and then measured the precession with a second Mott scattering. And from this, they got the G value of the free electron, and it was 2, just like theory said, and that's where things sat. So here we are, another decade and a half after that measurement, and nobody had yet made a way to make a reliable beam of polarized electrons. It had been suggested back in the early 1930, actually. People had pointed out that you might not be able to separate electrons by spin, but you could separate neutral atoms by their electron spin. And once you've separated off neutral atoms by that electron spin, you can then photoionize it. Photoionization is an electric dipole transition, so it's not expected to flip the spin, so you get a beam of spin polarized electrons. That's the scheme. And various people tried it. There's actually a bit of a tragic tale. A young fellow in Germany reported success with this method, and it turns out he was awarded a gold medal by the German Physical Society for this, but he dry lapped it. And there's some belief that he took his own life as a result of this. In any event, he died soon after in a bad traffic accident, which some people think was deliberate. Anyways, people were at work, and finally, in 1969, a group at Yale managed to separate lithium-6 atoms by the electron spin and photoionize that. And they made a source that made 2 × 10⁸ electrons per pulse, 78% polarization, which is not too bad, at a 10 hertz rate. And they proposed to build a source for SLAC with 5 times the intensity, somewhat better polarization, and 18 times the rate, which would be enough to do an experiment. This would be a polarized electron, polarized proton experiment. They were trying to look basically at the spin structure of the proton. And this was back in the good old days. The experiment was approved, and SLAC agreed to fund that thing. So, fast forward 4 years, by the summer of 1973, that source was in bad trouble. It was considerably distant from meeting its specs. It was not in a situation that the lab would have allowed it to be installed on the accelerator. More importantly, weak neutral currents were reported in neutrino scattering early that year. And that meant, because it was in agreement with Weinberg-Salon calculations of the day, that meant that you would expect to see parity violation in electron scattering. And a lot of people realized this early on. There was a lot of enthusiasm for that. We at SLAC understood that even if the Yale source fully met its expectations, it was not able, in a feasible amount of time, in a feasible experiment, to actually observe this parity violation at the level of the weak interaction that was expected. And so SLAC began to think in terms of a so-called follow-on polarized source to specifically investigate parity protection. So we set about 73, 74 looking at alternatives to the Yale source, and we looked at a number of them. I won't go into any of them, other than to mention the bottom one. The first three up there all used magnetization to align spins, and that meant to flip the spins, you needed to flip the magnetic field, and that's not good in terms of systematic effects if you're trying to measure a parity violating asymmetry, which in those days was a part in 10,000. This latter effect actually had been demonstrated at Bonn, and the spin from a Fano effect source can be reversed by reversing the polarization of a light beam, and that you can do with good systematics. Anyway, several of us marched off to various labs, all of them in Europe, working on these developments, and we put a tremendous amount of effort in 1974 into this, and we finally reached the conclusion that we could make a Fano effect source that could deliver 10 milliamps of basically 100% polarized electrons, and that it was optically reversible. So we put in a proposal to do that in late 74, telling basically, actually I'll mention this again at the end, it was basically a different day in the labs then. It wasn't so much a proposal to do this, it was a statement that this is what we want to do and you can afford it and you should approve it. And it went to the lab director, not to any program committee. So where was gallium arsenide? We all know that electrons come from, polarized electrons come from gallium arsenide. And I've looked back very hard, and the very first reference I could find to such a source came from when I visited ETH in September 73. This guy, H.C. Siebem, who I believe made the first successful polarized source, the one that demonstrated that the previous first-timer had dry labbed his results, told me his ideas. And at that point, my old friend Dan Pierce was doing a postdoc with Siebem, and they presented a paper at a Swiss Physical Society meeting describing getting a beam of polarized electrons from gallium arsenide. So, where were we? In 1974, November of 1974, some of the older of you may remember the so-called November Revolution. That was the year of the November Revolution. So we submitted a letter of intent to study parity violation using a cesium Fano source, 1st of November. We ran the first high-energy polarized electron beam from this lithium source made by Yale into the first high-energy electron polarimeter in End Station A at SLAC on the weekend of November 9th and 10th. And during that weekend, somebody came rushing into the counting house where I was and said, they've discovered a new resonance at Spear. And turning back to my bubble chamber days, I can remember explicitly thinking, you know, they've got some bump that's 50% above the continuum and 250 MeV wide, and here I am measuring the polarization of the first high-energy polarized beam. Needless to say, that resonance was rather more exciting than that. And towards the end of that month, a preprint on polarized electrons from gallium arsenide arrived from Switzerland. And talk about rapid reversal. That's one thing in the old days was always talked as being important for a polarized source, that you can rapidly reverse the polarization. So this preprint from sort of completely flipped our Fano source plans. In early January 75, we had told people before Christmas about this preprint and its implications. And again, this is a throwback to the way things used to be. They just said, go for it. We didn't have a budget. We did not tell them how much it would cost because we didn't know. We did not tell them how much effort it would take because we did not know. We didn't have a design, but they just said, do it. And later that year, we submitted a proposal to study parity violation at the weak interaction level using this source about which we knew nothing. So, how did people make polarized sources then and up until actually quite recently? They used what basically was a thermionic emission gun, except they replaced the cathode, which is on the end of that long cone, with a gallium arsenide wafer instead of a thermionic emitter. And you needed some additional stuff. You needed a cesium source. You needed some way to clean and ultimately cool the cathode. So there were a few differences, but basically if you looked at this from the outside and didn't look too carefully, you'd assume it was just like one of SLAC's regular electron guns. But it was not so. We ran into a very large number of problems. There's no way I can share them all with you, but there's a few that are sweet enough that I have to mention. First of all, there were no lasers. This gallium arsenide needs to be illuminated with very particular light, and there were absolutely no lasers commercially that did anything like what we needed. And so we had to not only build the source, we had to build a laser as part of building that source. And in those days, dielectric mirrors were just beginning to come into their own, and there were lots of small coating houses around. And so you'd write a spec for a mirror in terms of curvature and reflectivity, and hopefully find somebody that would make it for you at a cost you could afford. And I remember being very optimistic about getting some very lovely mirrors that should have made everything wonderful. And I turned the laser on, and the laser made an audible sound. The mirror made an audible sound when the light spurt hit it. And so I put in another mirror, and it went again the same way. So much for that. These sources require quite exceptional vacuum that was very difficult in those days with the technology of those days to achieve. And one part of achieving it was to bake the entire system at high temperature, 250 C typically. And hopefully that didn't take too long, but you had to bake until the pressure stopped decreasing. And our first bake out took 30 days. And some months later, when we opened up the particular area, one particular area on that gun, we found a beautifully carbonized human hair, which is how come the bacon take in 30 days. And then there was a problem of getting the beam around the 90-degree bend. Why do we have a 90-degree bend? Well, we were afraid of the weight on the ceramic insulator from all this stuff we anticipated hanging on the cathode end of the gun. So we put the ceramic insulator vertical so that we wouldn't have any worry about that. And so that meant we had to take the beam around 90 degrees to get it into the accelerator. And some of you may have seen the early pictures of what the first SLAC source looked like. And if you looked back earlier, you would have seen an earlier version and noticed that this magnet is different. There it's a rectangle, and here it's a C magnet. And you know, we were very struck how carefully we wanted to be to get everything right on this source as we built it. And so we made that bend magnet into a field index 1/2 magnet so that it would have equal focal lengths in both planes. Now, that being said, we didn't run any STASI programs to look at what the field looks like. We should have known without any STASI program. The bend radius was 5 centimeters and the gap was 3 centimeters, so Laplace's equation was not our friend. So, as I say, reluctant to abandon a bad idea, we replaced those beautifully machined, this was, by the way, before the days of numerical controlled lathes and stuff like that. So these beautiful hyperbolic poles were really a work of art from our machine shop. So we didn't want to abandon that idea, so we replaced them with circular pole tips. It's hard to imagine a worse idea than that. And so, when we saw the terrible things the circular pole tips did, we decided we needed edge focusing, and so we made a complicated little set of widgets that held soft steel pieces on the edges of the poles that we could, in principle, move around to get the focusing right. Finally, at long last, we just put in a plain old uniform field dipole with nickel magnetic mirrors at the input and out bases, and no more problems. But we still had years to go. It took us from January 75, when we started, until the summer of 77, 2.5 years before we could put the source on the machine. But by 1977, we were beginning to make fairly good quantum efficiency photocathodes. We measured polarizations of 45%, which wasn't so bad. We demonstrated a peak current of 1/4 of an amp, which was quite nice, much more than SLAC could tolerate. We had run 60 milliamp pulses into the Mach polarimeter. We did a long run to show we could do it, 85 hertz, 10 to the 11th electrons per pulse. And we got to move into SLAC's injector in July of 77. And our first parity violation result got published in late 77, which was, so it was basically a 3-year effort to do that first source. So, moving on, as Herman used to say, I left SLAC and joined CBAF in September of 87, and one of the first jobs I had here was to figure out what do we do about a polarized source for CBAF. Unfortunately, this may be something that at least some of you don't know, a polarized source for CBAF was not in the project scope. And what that meant was that DOE would not allow you to spend any money on it at all. So my first several months here was spent talking with DOE people, none of whom, I mean, they were great people. They were fine people who wanted to be helpful and were easy to work with, but they had no idea what an electron spin was or why one would want it. I spent a lot of time talking with them, and late in my first year here, we get this unsolicited by me, I don't know whether someone else had solicited it, but basically a letter from Larry Cardman saying that the University of Illinois proposed to develop a polarized source for CBAF. And my initial reaction wasn't too warm, I guess I have to say, but in fact, it led to a very good collaboration that worked very well over a number of years. And in 1993, they delivered a polarized gun, a spin rotator, a Mach polarimeter, all of this based basically on every improvement that we could think of to the original SLAC source and the Mainz proposed spin rotator. And this is that source. Electron gun there at the top, inside an aluminum shroud to keep curious fingers from touching 100 kilovolts. And the beam comes down, goes through a right angle bend and through this strange shape off to the accelerator off here. And this gun was pressed into service delivering beam to the accelerator in 1997, early 97, before we intended to do that. And the cathode lifetime was dismal. I mean, it basically was a full-time effort on the part of people to keep a cathode functional in that gun. And we made, entirely by accident, the discovery that when you turned on even a modest average current from this gun, the vacuum just went to hell. And this led actually to one of the great advances in polarized source work. Bruce Dunham stayed with him and put little thin-walled guider tubes all the way along the beam tubes there and discovered that electrons were hitting all over, and that's what was ruining the vacuum. The question is, where in the world did they come from? We had a cathode that was sort of a centimeter plus in diameter. We were illuminating it with a beam that was 1.5 millimeters in diameter, and there wasn't any straight light. Where were these electrons coming from? Well, Dunham took the next step and started modeling in detail the region around the cathode. And what he found was that these electrons that were hitting the walls originated from where the flat cathode came up against the focusing electrode on the gun. And in this region, there are some very high transverse fields, and if electrons should come from there, I mean, mind you, all these electrons are born with zero velocity, they get a transverse kick and they go through the gun and the lens and hit the wall. So how did they come? That's a complicated tale. It turns out it's trapped recombination radiation, and I don't want to get in that. But once we discovered where these electrons were coming from, we made a cathode in which it was not possible for electrons to originate from that troublesome area. And I still remember as one of the high points in my life, the first time we tested it. Happily, it was late on a Friday afternoon, and we put that cathode into service and started to run high average current beam, and there was not a whisper from the vacuum system. I went home very high that night. But there was another big problem besides those electrons at large radius, and that was that this system is littered with short focal length lenses. It turns out these two things that bend by 90 degrees have 10 centimeter focal lengths at their input and output. The magnet down there that you can just barely see that bends the beam into the horizontal plane had a 10 centimeter focal length on its input and output faces. Well, if you think of all these short focal length lenses stacked up in a row, and you realize you've got a little alignment error from one to the next, all of a sudden the beam goes through a short focal length lens and it's like this. It's getting focused, but it's headed in the wrong direction. Well, if you've got a corrector and you know about it, you have a way to know it, you can fix it. But we didn't have ways to know this. This whole apparatus here, these two 90-degree electrostatic bends and the 8 silver cylinders, which are solenoids, was used to orient the spin as it went into the accelerator so that the people receiving beam in the hall had the proper orientation. Wow. They'd call up and ask for a new spin orientation, and it was hours of frustrating frogging around, trying to blindly grope the beam through this undiagnosed stretch with far too few correctors. It was a nightmare, and we realized we had to get rid of it. And this really, between that 97 start, and then when we realized about the large radius electrons, and then we realized about these damn short focal length elements, the few of us that were working in the polarized electron business at that time sort of went into high gear, and we built several guns in a built and installed and ripped out this thing in a very short period of time. So the first one that we did was this vertical gun. Here you can see it without a high voltage shroud around it. We completely got rid of that so-called Z spin rotator and replaced it with a Wien filter, which is here, which is much more gentle electron optically. And we enormously improved the pumping. That gray cylinder you see below the ceramic insulator has several thousand liter per second pumping speed for chemically active gases. And this source actually went in and served several experiments very well. The first parity violation experiment here was done with it. And we began using high polarization cathodes in August of '98 with this. But I still wanted to finish the job and get rid of those. Oh, before I get there, let me talk about ion back bombardment, because it now became, and I believe it is still true, that this is the only physical phenomena we know of that is eliminating cathode lifetime. If you think what can happen, an electron leaves the cathode, There's nothing that happens to the cathode when the electron leaves, but if it hits an atom, a molecule, on the way and ionizes it, the ion gets accelerated back and smashes into the cathode, and it can do damage. But it can only do damage between the electrostatic center and the place from which the electron originated. So there's a characteristic pattern. You would expect if ion-back bombardment is the damaging phenomena, it happens only in a region between the electrostatic center of the cathode and the illuminated point. It will dig a trench over that region. And lo and behold, that's what we see. These pictures are, these little mesas are measuring the quantum efficiency, and you'll see we've dug a trench in the center of it, but the rest of the cathode is unharmed. So we can move to a new spot and dig a new trench, and move to yet a new spot and dig another trench. And that's exactly what was happening when I last knew, and I think it's still true that this is the only remaining phenomena that limits cathode life. So anyways, here's the final step in the story. You can actually, I was amazed, you can see a picture out in the front. We put in not one but two guns. We put them in the plane of the accelerator because we're no longer worried about breaking these ceramics. And we moved them onto the accelerator axis with an optical element that had a 3-meter focal length. So, problem solved. These guns were used for some number of years. In general, they did not need attention. They could deliver, 20 coulombs a day, basically what the accelerator could handle. They were very reliable. If you changed the cathode, you did have to break vacuum and rebake them, but that was the only thing. I mentioned lasers only peripherally, but all the time this work was going on, we also had people, Matt and John in particular, working hard to develop lasers, because it's still true, you can't buy lasers that are suited to this application. So we had not one, not two, but 3 lasers, each one illuminating the cathode, each one delivering polarized beam to a particular hall. And it was similar to the gun work. It was a prodigious amount of effort in a short period of time. So, is there a future for polarized electrons? I think absolutely. And I will just tell you a couple ideas I have. I think high current is going to be something that people will want at some point in the fullness of time. And I point out that Cornell has operated with 60 milliamps, not microamps, that's not a misprint, for 9 hours from a gallium arsenide cathode. That's coming up on 2,000 coulombs. And they basically stopped because they were tired, not because the cathode was dead. And I believe you can expand on this. And in particular, I believe you can make the operational lifetime longer than a Cornell gun by improving vacuum. And I think we know how to do that vacuum. Both of the gravity wave detectors, LIGO and Virgo, have achieved exceptional vacuums. LIGO is pumped at one end of a 2.5-mile long tube like this with a single pump. And it's not even a big pump. So we know what we need to do. And that's been tested and demonstrated in a number of places. There's also higher polarization. Given the polarizations that people run here now, 86%, give or take, there's only another 35% to be gained in IP squared. Your experiment isn't going to die for lack of it, but you'd take it if you had it. But there are materials that, in principle, give 100% polarization. There's whole classes of materials. And we all know that the techniques of material science these days are making materials that you could only dream about in years past. There's another thing that is done. The cathodes that are used today are strained superlattices, layers of semiconductor with different lattice constants that produce strain. And they've been optimized empirically to give this 86% polarization. Some few years ago, I met a young lady from Los Alamos who had applied genetic algorithm optimization procedures to another layered structure, layered semiconductor structure, terahertz lasers. And she had shown improvements like you can't imagine to this material, and then tested them, and lo and behold, it worked. I would love to see that applied to the materials we use here. I am only 95% confident it would bear fruit. I should also, before I quit, just mention a couple spin-offs. Early in the game, we realized that gallium arsenide could deliver enormous current densities, far more than you could get from any other practical electron emitter. And that reality has led to the use of photoemission cathodes in a lot of state-of-the-art accelerators these days, like the one at Cornell. And also, it's true, gallium arsenide, and to a lesser extent other photocathodes, produce very low emittance, that is to say, high brightness beams. And again, this leads to photoemission cathodes being widely used in state-of-the-art accelerators. So, none of this has ever been a single-person effort, I can assure you. And I've worked with a lot of great folks over the years. I hope I didn't forget too many of them. And also in other labs that built sources following on from this. And since I'm doing acknowledgments, I can't forget DOE and its predecessor agencies that paid all the bills. When Larry Gardman joined us, the NSF started paying a share. And I have to say, as a final thing, and I realize that many of the younger people in the audience don't need to have some old geezer stand up here and tell you how good the good old days were, but the good old days were good. There were two labs I worked with, two lab directors that really established a culture that made this work a lot easier. Anyways, that's all I have. Thank you.
All right, questions about the good old days?
Questions? Good.
If there's no questions at all, let's thank Charlie again, congratulate him. And move on to the next phase of the award presentations. Thank you. Yeah, is there something?
All right, it's back to me. We have two additional prizes this time for the postdoc and for a thesis award. See this one? This JSA Postdoctoral Research Award was established back in 2008 by the user group as a way to recognize a pathway towards excellence within one's educational training and preparation. And over the years, the prize has helped to encourage students to see their excellence is recognized at every level, and that's important. Some of us got stuck in postdoc period longer than others, but it's a pleasure to announce the award that goes to Nobu Sato. Is Dr. Sato here? Come on down. Currently at the University of Connecticut, but he was here at the lab for quite some time. I'm going to hold off on this. Let's do both, and then we can move on. So just a second, we'll get everybody up here. We'll be efficient. forward. Also the thesis prize. This is something that was established in '99 by Sarah from the user group. An opportunity to recognize some of the best theses that came out of the JLab Science program. And the prize for 2000, and the prize continues since 2007 under the JSA Initiatives Fund, and it goes to Piyushri Roy. Dr. Roy is here. Good, great. There's one thing about these two. They both go back to FSU for their graduate training, so that's nice. It wasn't planned that way, but it turned out to be that way. We appreciate all of our members and the strong people that they bring forward to work not only here at JLab but other places as well. So let's give these two, we'll bring up our team of photo op folks, dignitaries. We'll let you have one. We'll let Bob have the other. So Larry, yes, we've got everyone here. And let's give him a round of applause.
Now, as you know, I'm going to get several of these, so I get at least one that we can use. And I'm going to try number 7, just in case. And keep smiling, I know it's painful. Okay, thank you.
Okay. Thank you very much.
All right, we're going to conclude the program with a talk by each of the prize winners.
All right, well, it's an honor to receive this prize. So I'm going to be talking about the project that I've been working on and how this prize really, helped us on this. So this is about something that I call, or a group of people at the Theory Center called the universal analysis of pattern distribution functions and fragmentation functions, and it goes under the umbrella of something called Jefferson angular momentum collaboration. So to start with, I think it is important to say something about why I care about this. Okay, and so I just cherry-picked 3 points, which I think are quite interesting. The first one is, how does the quarks and gluons carry the spin of the proton? If you conceptualize the proton as a collection of a very complex system of quarks and gluons, each of them carries some spin. How does that overall collectively give rise to a spin one half of the proton? The second one is the so-called the origin of the non-perturbative spin. That's one of the challenges in JLab 12, which is basically to understand how that happened. It is a known fact that the amount of d bar and u bar in the proton are not the same. And this is something that people cannot understand from perturbative QCD arguments. So there are several models to explain this, and this is one of the challenging tasks of the JLab 12 program. And the last one, which is kind of my favorite right now, is about how hybridization actually works. And the reason for that is because when we talk about high energy collisions, we basically break out the proton into partons, collectively quarks and gluons, in a distance scales of 10 to the minus 15 meters. They only exist only on that time scales, very short time scales. And then afterwards, it becomes again hadrons. So the question is, do we understand this? And well, those are actually the key motivations for keep doing the research that I'm doing. So what are the tools to actually to be able to understand this? And it turns out that I don't actually need many tools. Or I can conceptually classify those tools into three pieces. So the first part is actually have a bunch of experimental facilities from which I can actually obtain data from electron-proton or proton-proton or proton-antiproton or electron-positron annihilation experiment. And I will have a bunch of a data set which allows me to study those questions that I posed at the beginning. The second tool is more theoretical tool. So it is not enough actually to start with the Lagrangian of QCD and try to address those questions. Those questions directly from the Lagrangian can be addressed, say, in lattice QCD. But at present, it's not enough right now to be able to achieve the accuracy that we want. So in the meantime, we have actually a fantastic procedure called QCD factorization, okay? Upon which we can, out of which, define objects that we call parton densities, polarized parton densities, and fragmentation functions. And once we have those tools, we can actually combine them into a systematic, computationally intensive framework, which is quoted typically as a global analysis, okay? And the idea is that these functions that comes naturally from factorization actually are those quantities that we cannot calculate from first principles and contains information of those questions that I posed at the beginning. And so the idea is to be able to extract those functions from the data within this framework. Okay, so since for many of you the concept of factorization and PDFs might not be actually, the day-by-day thing, so I just prepared a couple of slides that will give you sort of a taste of what do I mean by that. So to start with, let me start with this, basic reaction of electron-proton going into electron. Whether I measure or not a final state hadron, that will differentiate between the process as inclusive DIS or semi-inclusive DIS. And we consider the reaction to be described in terms of a diagram that looks like this. So the left-hand side is the amplitude, and then the right-hand side is the conjugate of that amplitude. So that will be the probability density, and from which you can actually link with what we call cross-section. So the idea of the factorizations is, in essence, to be able to work it in one single photon exchange, to be able to understand this blob here, okay? And so the way to do this is to actually separate the blob into certain regions. Basically, it's a classification of Feynman diagrams, okay? And then once that classification is done, one can identify parts that can be calculated perturbatively, which is this so-called the hard part, and parts that we cannot actually calculate perturbatively, okay? And so what we can do is actually perform a systematic Taylor expansions, basically. And then we can actually disentangle an object that looks like that in terms of parts that we can calculate and parts that we cannot calculate. So this lower part here is defined to be the parton distribution functions, okay? And depending on whether you actually have a polarized environment, you are accessing either the polarized or unpolarized parton distributions. And so what actually is it? Well, it can be interpreted as the probability density for a quark deuterium momentum fraction along the icon relative to the hadron momentum, okay? And you can see that this picture is quite simplistic, because if you're an experimentalist, you might say, well, this electron line is not like that. Electron line has relative corrections, it's more complicated. Well, the same is true also for QCD. All these quarks that lives here also has QCD radiation. So all those effects are actually can be calculated by something called by the renormalization group equations, and essentially give rise to the scale dependence of these particle densities. Okay. So this part here is related with the target of the system. So I have an electron, a proton. So it's associated with the nucleon structure. Similarly, if I actually cut in the final state, if I measure a hadron, then I can define something called fragmentation functions, which is essentially encodes what's the probability of a given hadron that I measure to carry a momentum fraction z of the parent quark. And this actually contains information of how hadrons form in a given reaction. So you can see that all the questions that I put at the beginning somehow encoded into this picture. So one interesting aspect of this is that the factorization is in some sense universal. So here I'm listing the two processes, inclusive DIS if I don't measure the final state hadron, or the semi-inclusive DIS if I measure the hadron. And so this is what is related with the electron-proton collision. But nothing prevents me to actually replace this upper line by another block here, and then that will become a proton-proton scattering, like this one. And this is basically what happens every day at the LHC or Tevatron. Okay? So this is the typical diagram for the Brownian production, so it's electron pair here. And you can also measure the same thing like a semi-inclusive analysis where you actually tag a final state hadron. And all these blobs are actually the same. So it's in this sense that these parton distribution functions are universal. Complementary to these processes where in the initial state we have hadrons, we also have electron-positron annihilation, in which we can actually also produce hadrons in the final state and describe the process with the same fragmentation functions. So fragmentation functions, PDFs, polarized PDFs, actually are inside of many, many processes, and that in order to constrain them, we need to actually do the global analysis. Okay? All right. So our group, a few people are counted in my hand, wants to actually perform a universal fit as opposed to global fit. The reason is because in practice, what has been done so far is to actually extract the parton densities independently of fragmentation functions. Okay? And it turns out that, as you can see, the color code goes for the different reactions, okay? And all those lines actually tells me that each of these functions receive contribution from all these processes. So in order to actually have a to test the universality, it's actually important to actually perform an analysis where everything has been extracted simultaneously. Why? Well, because then we will be able then to actually correlate those uncertainties associated with the electron-positron annihilation or series observables. Everything will correlate, okay? Because data is not infinitesimally precise. And obtaining these distribution functions are going to be actually the baseline for the upcoming TMD analysis. Because so far, the distribution that I've been mentioning is only the longitudinal. Once you involve the transverse distributions, well, actually, those observables are described in terms of this collinear distribution. So we need to actually have a robust and consistent set of PDFs and fragmentation functions in order to interpret the upcoming JLAB12 data. Okay, so I mentioned the theory, I mentioned the experiments. Now the third tool that I mentioned was sort of the data framework. How do I combine those? And it turns out that this is actually not a very simple tool to handle. And the reason is because there is a lot of things that's going on inside of the so-called fitting. And I pose this problem as a science of fitting. And so let me just illustrate what do I personally believe is fitting. So suppose you have an observable like the path of distribution function. I need to actually parameterize in terms of something. So those A's are the parameters. We all know that we can associate to those parameters certain probability distribution given by the data. This is achieved by the Bayes theorem because we can actually link this to the likelihood function. Okay? So essentially, this is basically a textbook formula. If you want to actually obtain the expectation value of an observable, you just perform this multidimensional integration. Typically, in the global analysis scheme that I'm thinking of, there are about 100 shape parameters. So this is a 100-dimensional integration. Okay? And if I want to understand what is the uncertainty associated with this observable, well, then I have to perform the same integral. So 100-dimensional parameter space is kind of challenging, in trying to perform these integrations. So in the past, people have been clever to basically address this integration in a simple way, which is basically, let me actually use the value of the parameter such that this product density is the largest. That's the same thing as chi-square minimization. And then let me approximate my expectation value by evaluating the observable at that point. Okay. Okay, and then what about the error? Well, the error, we are going to just look, the minimum around the chi-square and try to get some profile, and that's it. I claim that this kind of activities is actually very dangerous to keep track, especially if you go to really higher and higher dimensionality. The reason is because these methods actually assume Gaussianity. And Gaussianity does not need to be prevail everywhere. So in order to actually tackle all those non-Gaussianity behaviors associated in these methods, we actually need to perform this integration in the way that we know best in particle physics, Monte Carlo methods. So the idea is very simple. The idea is to basically construct a set of parameters which are the Monte Carlo representation of that probability density. And then once you know those parameters, you can actually perform this integration in the Monte Carlo way. So this ought to be more robust than this, and it should give us a better confidence of what do we know and what do we understand about pattern densities, etc. So in GEM analysis, we actually have innovated a mechanism to basically construct these Monte Carlo parameters. And essentially, it goes by taking the original data, constructing a pseudo data set, partitioning to training and validation, and then we basically train each of these samples of the parameters with the training data, and then we obtain the posterior. So if it's too confusing, essentially we start with some sampler of the parameter space, we construct some priors out of it, and then we perform many fits. Many fits requires a lot of computational power. This is where the price will help me to actually get more computational power. And then from that, we can actually construct a bunch of posteriors, which is basically will resample the probability density of the actual likelihood function. There are several key aspects of that. Is that we can avoid things like overfitting because we are doing cross validation. We try to be as agnostic as possible about the parameters, so we don't assume anything about the exponents. And at the end, we actually end up with a reliable estimate for the expectation values and the biases. So the milestone so far in this project has been the following. So before I show all the lines, so we have performed in 2016 an analysis to include all the spin-dependent data from inclusive DIS all the way up to the 6 GB data sets. And that was actually summarized in this paper here. Later, we move into an analysis of fragmentation functions using all the available electron positron annihilation data. And more recently, a few months ago, we finally performed the first ever combined analysis of inclusive DIS semi-inclusive DIS, and electron-positron annihilation data, which is in this paper. And hopefully by the end of this year, we will have some progress to actually also incorporate for the first time the unpolarized PDFs into all this game. Okay, so let me actually briefly go into those 3 milestones that I mentioned. So this is all the global set of inclusive DIS data that we use. Typically, in doing this analysis, one needs to actually put a strong constraint on the W square, which is the invariant mass of the final state system. And the reason for that is because one needs to avoid, there are theoretical issues like higher twist and value mass correction and so on and so forth. So in a typical analysis, people put a cut here, which basically eliminates the entire JLab data. So we were bold, and then we tried to put as much as theory we could, so that we can lower this W squared cut up to 4 GB. This was the maximum that we can do. And then basically the data set doubles, essentially, after including all the JLab data. So I'm just going to flash a couple of results from here. So these are for all the asymmetries from the old EMC experiment until the recent COMPASS experiment. You can see how beautifully all the theory is described in the data pretty nicely. This is for the transverse symmetries. And then here I'm showing, in particular, some of the analysis done for the JLab 6. And one of the key features was that we found by looking at this experiment, we found that there was significant deviation from the so-called leading twist. So this was a big thing because for the first time we can actually underpin the higher twist effects that is inside of the inclusive DIS. Okay, so there are some more. And so these are the results, okay? So those polarized PDFs that I mentioned at the beginning, from the Monte Carlos, it looked like that. And after we performed the expectation value and the variances, they look more or less like this. Okay, and then these are the higher twists, which I don't have time to talk about. But what I want to show is essentially that, interestingly, just using inclusive DIS, we were able to actually get some good constraint on the gluon distribution, which was consistent with other analysis that has used just data. So that was very encouraging for us because the methodology seems to work. But one of the puzzling effects is actually this piece here, which is the strange polarization, okay? So it turns out that if we use only inclusive DIS, the strange PDF is actually negative. And it turns out that there is a group called DSSB09, they actually get positive. And they get positive just because they use semi-inclusive DIS data. So it turns out that there has been a lot of controversy around that. It is called the strange puzzle. And it has been said in the literature that, well, it depends on which fragmentation function you use. And we go again to the same idea that people are doing the analysis completely separated, not integrated within a uniform framework. So we have to fit fragmentation functions. So that's why we went to this business here. So we went and we performed a new analysis, the first Monte Carlo analysis on fragmentation functions for a variety of data sets from the old lab experiments until the recent Bell and Babat experiments, which are located here. So actually fragmentation function is quite challenging to fit, but nonetheless we managed to get somehow a reasonable chi-square, quote-unquote, 1.31. And you can see that there are tensions between data sets. Literally, data set that lives on the same kinematics, has basically completely different shape. Nevertheless, since we don't have more data set to distinguish between them, we just have to stick with it and assess what's the uncertainty. So this was for the high fragmentation functions. This is for the K-ion fragmentation functions. And this is how the fragmentation functions that we extract from the data looks like. What happens is that these distributions, you can go and read the paper more carefully, but there are a couple of interesting parts. So specifically this function here, the K-ion distribution, is going to play a significant role for the strange polarization. And we were after about the shape of this distribution. And it turns out that they agree with the DSS analysis, we show a positive flip of the polarized strength distribution. So for us, it was surprising because then we would say, well, then if we actually put this stuff, then we will actually get a positive strength distribution. So, but of course, we have to do these things seriously in a combined manner. So that's why recently we finished the first ever combined analysis of all these data sets. And here is what we found. So if you look at the strength distribution, this was what we obtained. And it turns out that it's basically consistent with 0. So one can actually get a different answers depending on which data set you use. Okay. Well, if you don't include the CDs data. So essentially, this blue here is only inclusive DIS data, no CDs. And the red here includes semi-inclusive data. Now, theoretically, this function here should not actually get constrained by the inclusive DIS data. The reason is because inclusive DIS data is not sensitive to it directly. So we have to put an assumption, which is basically the SU3 symmetry, which comes from a constraint of the hyperdome beta decays. If you put that, then we get a distribution that looks like that. But that's an assumption. So we relax that assumption and we replace that by the semi-inclusive DIS, and this is what we get. So the almighty data from semi-inclusive DIS that exists that is supposed to actually constrain, anti-quads and so on and so forth, actually has at present very large uncertainties, which does not allow us to say much about it. Okay? There are some hints, for instance, about the asymmetry on the U-bar and E-bar, which seems to be positive at this small X region, but the errors are still large, and this is where the upcoming JLab data on the canyon measurements can actually make a good impact. So as I mentioned, in the previous analysis of the Gen 15, we imposed the SU3 symmetry. That's a value of 88, which is sitting here. But we relaxed that. We actually allow a larger sampling and ask the data, what do you think the AA should be? And the data collectively tends to peak around this region, which is about 20% below the nominal value of AA. However, you can see that the uncertainties are still large, so to claim that there are visible SU3 symmetry breaking is still premature. So again, in a few years, once we get the KU data from JLab 12, we will be able to actually convert this green thing into maybe a much narrower thing. Perhaps it will agree with the SU3, or perhaps it will provide a significant deviation for the exact symmetry. Okay, and last thing is that the strength distribution is negative actually because there has to be some data that wants that. And then we have identified that data set to be the K minus from the neutron from Hermes data. And it's actually this handful of points here that is very close to 0, but tends to favor a positive strength. So if I don't put the cities data, it will be this blue band here. But if we put the cities, then this data set will try to pull it. Should we believe in this? Well, I think we need to actually have more measurements of K minus on the neutron in order to be able to see whether or not this is actually consistent or this is some systematic effect in the compass experiment. And this is very important because otherwise, what we call a strength distribution is pretty much fictitious. So one of the hard tasks of this game of global analysis is to be able to distinguish what's fictitious and what's actually real. And that's the challenge. Okay, so let me just conclude here. So we have the so-called the JAN master plan, which is basically implement the Monte Carlo fitting methodology to encompass all the available experiments to extract uniformly PDFs, polarized PDFs, and fragmentation functions. And our to-do list, which is in the upcoming months, will be to finish up the unpolarized analysis and combine with and perform a uniform combination of everything. And most importantly is to be able to identify and understand kinematic regions where the data cannot be described and then propose the solutions, because at some level it could be only experimental issues, but another level could be also that we are stretching too much about the theory and we need to think about how to improve it. And this will actually pave the way to be able to repeat the same into TMD physics. All right, thank you.
Questions for Nobu? Everybody knows it's the second to last talk. Let's thank Nobu again and congratulate him on their work. Okay, and our final talk that concludes the user group meeting is by Priyashi Roy, and she'll talk about her thesis prize research.
A very good afternoon to all of you. I'm really honored to receive this very prestigious award, and I would like to thank DOE for financial support. I did work very hard on this research, and so it does feel really nice that work has been appreciated. But I must say that no scientific research is a lone endeavor, and therefore I would like to thank the entire FROST collaboration for the excellent teamwork and for providing this successful experiment. I would also like to thank my thesis advisor, Professor Volker Krede, without him this experiment and this work would have been impossible. Also, my special thanks to Eugene Pasiuk and Kenneth Livingstone for their valuable guidance. I'm currently a postdoc fellow at the University of Michigan, but I did this work at Florida State University, and I'm very glad to present my work here. I extracted polarization observables in vector meson for the production. The data came from the FROST experiment, which used the class detector. And so I'll now straight away dive into the introduction. We know that baryon spectroscopy is an important tool. It's a very important tool for understanding the strong interaction in the non-perturbative energy regime. How quantum chromodynamics gives rise to excited baryons is still a very open question. And it leads to further questions such as what is the origin of confinement? How are confinement and chiral symmetry breaking connected? What are the relevant degrees of freedom? How do they evolve with energy? So various phenomenological models have been proposed to describe the effective degrees of freedom. The constituent quark model has 3 degrees of freedom. Now if you also include gluonic excitations, so constituent glue, then we will have more than 3 degrees of freedom. On the other hand, we can have 2 degrees of freedom if 2 of these 3 constituent quarks are frozen with respect to each other, and if this frozen pair remains the same with time, then such a model is called the static quark-diquark picture. And there's another picture which says that the excited nucleons are generated dynamically by the interaction between ground state nucleons and a meson cloud. Now, complementary to these phenomenological models, we also have first principle calculations from lattice QCD. And what we want to do in baryon spectroscopy is that we want to map out the excited states of the baryon spectrum and identify the underlying pattern, which would be in the form of multiplex. And hopefully we will be able to answer some of these open questions that I just mentioned. So here I'm showing what I mean by underlying pattern. So over here, I show the constituent quark model predictions for n star. Here are the quantum numbers for those resonances. And this is an old picture. It's taken from 1986 publication. And on the right-hand side, I show recent lattice QCD computations on n star. It was published in 2011 by Edwards et al. And what I want to show here is that there is an underlying pattern. The excited states can be accommodated in various excitation bands, which are highlighted here as well as here. And it's also interesting to see that the level counting at each JP quantum number in each excitation band, those are consistent between the constituent quark model and the lattice QCD computations. And now I would like to show how these underlying pattern give us an idea about the effective degrees of freedom. So let us concentrate on the 72 plus. in the constituent quark model, we can describe the spatial part of the wave function as consisting of two harmonic oscillators. And in the 72 plus, it requires that both of these harmonic oscillators are excited, which would mean that this multiplet is inconsistent with the static quark-quark picture. Now, how much evidence do we have for this multiplet? Well, the quartet of this multiplet can actually be filled with experimentally observed resonances. The member 1900 3.5 plus was in fact recently promoted from 2-star to 3-star rating, and that was because we saw further evidence for this resonance from kaon lambda photoproduction reaction and polarization observables CX and CZ for this reaction. These results were impressive results from the class collaboration itself. So this shows that understanding the underlying pattern gives us an idea about the effective degrees of freedom. So far so good. But the fact is that we do not understand the baryon spectrum, particularly at high energies, above about 1.7 Jeff, where we have many more predicted states than what we have experimentally seen. So here, the blue lines, they show the predicted states, and the same is the case here. And the colored bars in this picture, are the experimentally observed resonances. So there are still many more missing states. And in this direction, the vector meson and multi-pion photoproduction reactions will help in a better understanding of the spectrum. So here I'm showing the table, which I took from PDG 2017, so this year's publication. And this shows the n-star resonances, their overall rating, and their rating in various decay modes. So what we see here is that mostly we have seen these resonances in the pion-nucleon scattering experiments. But if these resonances are indeed true and their decay into these vector mesons are allowed, then we should see evidence for these resonances also in these decay modes. But as we can see, this table shows that these decay modes are currently underexplored. So if we explore these reactions, we can get further information on many poorly understood properties of these resonances. In addition, these high mass resonances, many of which are missing or have not been experimentally observed, they preferably decay to heavier mesons like these vector mesons, omega rho phi, or they decay sequentially to multi-particle final states via intermediate resonances. That is, nature invests in mass rather than momentum. So all these reasons inspired me to look at two different reactions, the omega vector meson photoproduction and the pi plus pi minus photoproduction on the proton. And this reaction actually gives us two information. It gives us information on the decay of resonances to p rho, where rho is the vector meson. And it also gives us information on intermediate resonances in sequential decays. So this is what I mean by sequential decay. The proton is excited to an excited state, and then that excited state decays to an intermediate resonance via emission of one pion, and this intermediate resonance then goes back to the ground state via emission of another pion. So we have the 2 pion in the final state. Now, baryon spectroscopy is much more complicated than atomic spectroscopy because the baryon resonances are broad and overlapping, unlike what we see in atomic spectroscopy. And that's why we need more information than what we get from unpolarized measurements. So we need polarized measurements in order to disentangle and reveal the baryon resonances. It gives more information and we can reveal more stuff. So this is what basically happens. The unpolarized measurements are sensitive to the sum of the squares of the scattering amplitudes, whereas the polarization observables are sensitive to the phases of the scattering amplitudes. So once we have this data on unpolarized as well as polarized measurements, after that we need sophisticated data interpretation tools to extract the underlying resonances. Just by looking at these results, we cannot infer all of the underlying resonances. We need these sophisticated data interpretation tools. And since the polarization observables are very important, there has been a worldwide effort to extract them. And in this direction, the FROST and STAR program has contributed significantly. It was conducted in Hall B of Jefferson Lab, and the maximum electron beam energy was 5.7 JeV. The main goal of the Frost experiment was to perform double polarization experiments, so all kinds of beam polarization and all kinds of target polarization. And here I'm listing all the polarization observables that we have for omega reactions, so that's on the top table, and the polarizations that we have for pi plus pi minus photoproduction reaction. And as you can see, I have color-coded the polarization observables here. Those that I show here in red, I extracted them in my analysis. So I extracted 13 polarization observables in total. But of course, I'm not going to show all of them here. I don't want to bore the audience. I also don't have so much time to show all these observables. And as you will see, these observables look like a bunch of wiggles. So I will show a few, and I will have a qualitative discussion. Also, here I show observables in blue, and we have final or preliminary results for these observables from the Frost collaboration. So these two tables nicely show that we are getting close to completing the set of polarization observables for these two reactions. And now let us look at the highlights of the Frost experiment itself. The Frost experiment, as I said, was conducted using class which had large acceptance for charged particles. So it was well suited for spectroscopy. And the experiment was taken between March and August 2010. Since it was a double polarization experiment, the photon beam was linearly polarized for some data and circularly polarized for the rest of the data. The data that I analyzed had transverse target polarization. The target was a doped butanol target, and the covalently bonded hydrogen atoms were transversely polarized. I mean the protons in the covalently bonded hydrogen atoms were transversely polarized. The energy range covered in the linear data was from 1.4 to 2.1 JeV in center of mass. So we see that it covers the energy above 1.7 JeV, where we have the problem of many missing resonances. And in case of the circularly polarized data, the energy coverage was from 1.5 to 2.5 JeV. Here is a plot which shows the quality of degree of linear beam polarization. It varied between 40 to 60%. In case of the circular beam polarization, the electron beam had a polarization of 87%, and then the photon beam polarization depended on the electron beam polarization and the fraction of photon beam energy to the electron beam energy as shown in this graph. The main component of the Frost experiment was a frozen spin target apparatus. As we can see, it has many components. It looks very complicated, but it was a very beautiful apparatus. It had the butanol target, which was transversely polarized, and in addition, it had two unpolarized targets, the carbon and the polyethylene target for background studies. The butanol target was polarized using dynamic nuclear polarization technique, which required a high field and low temperatures. So here's the polarizing magnet, and once the desired polarization was achieved, we needed a dipole holding magnet to hold the transverse polarization. So here's the picture of the dipole holding magnet. It had a field of 0.5 Tesla, and the target was kept at a temperature of 50 millikelvin. So the offset angle for the transverse polarization that was obtained in this method was about 116 degrees from the x-axis in the lab frame, and an impressive transverse target polarization was achieved. The average degree of polarization was about 81%. The relaxation time was 4,000 hours without beam, and it reduced to 3,400 hours with beam, but we polarize the target every week, once every week. So now I'll move on to the data analysis and results, but I'll chiefly focus on the omega photoproduction reaction. For the omega reaction, I reconstructed omega from pi plus, pi minus, missing pi 0. And this decay mode has 89% branching fraction. I identified this topology using kinematic fitting. As for the p pi plus, pi minus photoproduction reaction, I identified 3 topologies, and the final observables were weighted averages over these 3 topologies. And then I applied standard cuts and corrections. But the two main unique features of my analysis were that I used an event-based technique for signal background separation, and I used an event-based technique to extract the final observables. So for signal background separation, I determined a weight factor for each event. Let's call it as a Q factor. And that factor gave the chance that the event came from a signal distribution. To do this, I used a nearest neighbors approach. So I will show here the quality of the event-based signal background separation technique. So the top picture shows how it worked for the omega data. So here is the 3-pion invariant mass. And before I applied this technique, I got this black signal distribution, which had both, black total distribution, mass distribution, which had both signal and background. And when I weighted each event with its corresponding Q, then I got a nice signal peak at omega. When I weighted those events with 1 minus Q, which gave the chance that those were background, came from background. Then I got this blue distribution, which we can see doesn't have any peak-like or dip-like structure near the peak. It's very smooth, and it shows that the method worked well. And one thing I would like to emphasize here is that this method did not impose that I would be getting a very smooth background distribution and a nice peak. I had to optimize the code to get that. So in the end, it shows that the optimization was done well. And for the 2-pion reaction, here I'm showing the missing mass distribution for this topology where we had a missing pi minus. So here is the mass distribution for missing pi minus. When I did not apply this method, I got this total distribution from the butanol target, which contained both signal and background. And when I weighted with Q, I got this nice red signal corresponding to the pion peak. When I weighted with 1 minus Q, I got this blue distribution, which showed the background. And in case of this 2-pion reaction, I had enough statistics to also make use of the carbon target to cross-check my signal background separation method. So here is the unscaled carbon target distribution. And then I had to determine a scaling factor to scale it up. So I went far away from the signal region where it had only background. And then I found the ratio of the green distribution far away from the peak and the ratio and the unscaled carbon distribution. That gave me the scale factor. I scaled it and I got this magenta curve. And as you can see, within fluctuations, the magenta curve agrees very well with the blue background distribution that I got from the event-based method. And finally, to extract the polarization observables, I had to fit angular distributions in azimuthal angle of the recoil particle. Instead of using the conventional least square fitting, I used the event-based maximum likelihood method, and I extracted these polarization observables. So now I will show the results. So far, for omega reaction, we have these many published results. Omega reaction is also an isospin filter, so it's sensitive to n star only, and it basically reduces complexity in understanding this reaction. So here I show the unpolarized measurements, the measurements on the unpolarized cross-section and unpolarized spin density matrix elements. I also mentioned which collaborations published them. And then here I have the polarization measurements, mostly from the ELSA collaborations, and the measurements on polarized spin density matrix elements. And actually a lot of these measurements, and mostly all of the polarized measurements have come out after the year 2000. And some of them are as new as last year and the year before that. So these are very new results. And now to that we have added results from the Frost collaboration. So my results, I have extracted 5 polarization observables for this reaction, and 4 of them are completely new, first-time measurements. So these observables have significantly added to the world database of polarization observables. But what do we learn from these results? And for that, I will take help from the Born-Gachina interpretation, so Born-Gachina partial wave analysis. In 2016, the Born-Gachina group included all of the data from the ELSA collaboration, so all these data from ELSA, and also very high statistics results on the beam asymmetry from another class experiment. And then they got partial wave solutions and we can refer to that as the Bonn-Gachina 2016 partial wave solutions. So these the 2016 solution was not entirely unique. Other acceptable solutions also existed. And additionally, based on the 2016 solution, they were able to predict how the observables T, F, H, and P would look like. So, and then I extracted these observables from the frost data, and I show them here as the data points. And as we can see, their 2016 predictions did not match the data very well at all. In fact, in some cases, it's completely in disagreement, right? So this shows that these new observables carried more information and carried a lot of useful information. So now the Bonn-Gachina partial wave database has these new observables, and now we have the latest Bonn-Gachina 2017 partial wave solution. It will be published sometime later this year. And before I move on to the Bonn-Gachina 2017 solution, I would like to show the frost results themselves. So here is the beam asymmetry sigma. The sigma beam asymmetry is associated with the linearly polarized photons and an unpolarized target. Here, the x-axis is the theta of omega in the center of mass frame, so this particular angle. And I'm showing my results in 100 MeV wide energy bins, all the way from the reaction threshold up to 2100 MeV. The total cross section in the presence of polarization observables gets modified like this, and here is the term which contains the beam asymmetry. As we can see, this term is only proportional to the degree of linear beam polarization. The frost results are shown here in red. And one thing that we right away see by looking at this picture is that the red data points are in very good agreement with the green data points. These green data points are the new high statistics results from class collaboration. And so it's very nice to see that both of them are in very good agreement because they had used the same detector, the same class detector. Also, there are other published measurements for beam asymmetry, but only at low energies, so from threshold to about 1500 MeV. And I'm showing those results here. And as we can see, the frost results agree fairly well with all other results. The only data points that stick out are these blue inverted triangles. These were published by Graal in 2015, and why these don't match many other of the results is currently unresolved. The black curve that we see here are the latest, the Bonn-Gachina 2017 partial wave solution. And now here are the first measurements on the double polarization observables, F, H, and P. The F observable is associated with circularly polarized beam and a transversely polarized target. I'm showing some energy bins here. Again, the energy bins are 100 MeV wide, and the x-axis is the cos of the angle in the center of mass frame of omega. The H and P observables are associated with linearly polarized beam and transverse target polarization. One thing I didn't mention is that these results, we have written up a paper, and the paper from Sigma is currently under ad hoc review. And for these observables, we are preparing a paper right now. So I'm showing the observables H and P for selected bins. These observables are not as big as the beam asymmetry, but they do have, they are non-zero and they change in shape as we go to higher energies. And the solid curves here are again Bonn-Gachina 2017 curves, and we see that these curves are in better agreement than what we had in 2016. So now I will discuss how the polarized measurements helped in a better understanding of the reaction. So when we did not have any of these polarized measurements, class performed partial wave analysis that was done in 2009 using their measurements on the cross-section and unpolarized spin density matrix elements. And I'm using this constituent quark model spectrum for visual guidance only. So once they performed the partial wave analysis, they were able to identify strong evidence from these three resonances and weak evidence from this 2-star resonance, the 2000 5-half plus. But the main problem that they had was, since they didn't have any polarized measurements, they were not able to understand the T-channel background very well in this reaction. And this reaction has a dominating T-channel background because omega carries the same quantum numbers as the photon. And then there came along all these polarized measurements, including the frost measurements, and the Born-Gachina partial wave database, partial wave analysis was done on all these polarized measurements. And as we can see, after we included all these new polarization information, the Born-Gachina group were able to identify many more resonant contributions. That's because they were now able to better understand the T-channel background, and so they were more sensitive to the resonances. What they saw was that in the T-channel, the Pomeron exchange was rising as the energy increased, and it reached about 50% for the total cross-section. They also found that there were basically 4 main partial wave contributions, the 3½ plus, 5½ plus, 3½ negative, and 5½ negative. So the 3½ plus, it remains the leading resonant partial wave contribution close to threshold, with a strong peak at 1720 3½ plus. So this particular resonance, and actually we can see that peak right here. Then the 2000 5½ plus, the 2-star resonance, the contribution of that has increased by 1.5 times between 2016 and 2017. And that is after adding the frost data. For the 3½ negative, the contribution of these 3 resonances has not changed much between 2016 and 2017, except for the 1875 3½ negative. Its contribution has decreased by about 70% between 2016 and 2017. And then finally, for the higher energies, the 7½ partial waves are important to describe the spin density matrix element above 2.1 Jeff. Alright, so now I will show just one observable from the 2-pion photoproduction reaction because I have limited time. I would like to say here that the 2-pion reaction is more complicated because it has 3-body final state instead of 2-body final state, and it has a large hadronic background. I extracted 8 polarization observables in total. I'll be showing one of them here. So here is the beam asymmetry IS in the 2-pion photoproduction reaction. The IS, actually this reaction has 2 beam asymmetries instead of just 1. And also we need 5 kinematic variables to completely describe this reaction. Because Frost had high statistics, we were able to bin in 3 out of these 5 kinematic variables. So the x-axis, this is actually a 3-dimensional plot. The x-axis is phi star, where phi star is the angle between the center of mass plane and the 2-pion decay plane. Each of these bins is a cos theta star bin, where theta star is this angle between 1 pion and the z-axis in the 2-pion decay plane. And I'm showing one energy bin here, between 1.3 Jev and 1.4 Jev. The Frost results are shown here in red, and I'm comparing these results with another result from a class experiment. This has not been published yet, but we can see that the 2 results are in excellent agreement. And here, the solid curve that I have, these are Fourier sine fits to the beam asymmetry IS. And I have done sine fits here because of parity invariance, we know that the beam asymmetry is going to have odd parity with respect to phi star. And that's what we see here. And in here, I'm showing preliminary fits from Born-Gachina to IS. The data points here are the blue data points that are shown here. And we see that these preliminary Born-Gachina fits describe the data well. And since there is an excellent agreement between the blue data points and the Frost data points, so the Born-Gachina fits would definitely also describe the Frost data very well. But this work is currently ongoing. So with this, I would like to summarize that photoproduction of vector mesons and multi-pion final states is essential not only to discover new resonances, but also to better understand poorly understood properties of known resonances. And in my analysis, I have many first-time measurements for these 2 different reactions. And these high-quality Frost results are expected to put tight constraints on the data interpretation tools. For example, we saw in the case of omega, there was certainly an improvement between the 2016 Born-Gachina partial wave analysis and the 27 partial wave analysis. one thing that I didn't mention was that between 2016 and 2017, the partial wave solution that Brown-Kachina has, they have reduced ambiguities. It's closer to a unique solution. And then finally, we should not forget the bigger picture that we will have information on N-star members for the light paradigm spectrum from FOST, but that's one piece of information. With that, to that we have to add more information from other collaborations. We need information on the strange members for the light paradigm spectrum from BlueX at Jefferson Lab, Panda at GSI, BESS at Beijing, and when we put together all these information, then we will be completing the study of the light paradigm spectrum, and that hopefully will give us more insight into the phenomena of color confinement in the system of light quarks. Before I conclude, I would like to tell you what I'm doing now as a postdoc fellow. So at Michigan, I am in the cryo target group, and our responsibility is to design, fabricate, and install liquid hydrogen cryo target for MUSE. So the MUSE experiment aims to resolve the proton radius puzzle. It will be conducted at PSI. And here is a target cell prototype that I have made in the lab. This is the chamber design that we have recently come up with. What is very interesting about MUSE is that it's going to be the first experiment which is going to simultaneously measure, simultaneously perform muon and electron scatter elastic measurements. And so they will be able to compare the two results from these two different leptonic probes with reduced systematics. And this is the Q-square coverage that we will have in this experiment. The experiment is scheduled to take place at PSI later next year and also the year after that. So I'm very excited for this experiment. I'm really looking forward to it. With this, I would like to thank you very much for your attention.
This is your last chance to ask questions for the user group meeting. We actually finished ahead of schedule. So I'd like to thank all the speakers and congratulate all the prize winners again.
No.